radiation, he was thinking of radiation in very physicalistic terms. What if it undergoes a fluctuation such that all of that energy is now contained in a volume, V, a subvolume of V0? So because he has the expressions for the entropy, and now using this reversed engineering from the Wien law, we've got the entropy S0 and S. I seem to have lost my. There we go. We've got the entropies for the initial volume of radiation in V0 and the final volume of radiation V. We can look at the entropy change. And now look at this magic, turn it into this expression here, and let n equal E over k beta nu or E over h nu. And so this is, and the further observation that when you've got a ratio of volumes of this kind and you're looking at a power, some n particles, if you've got anything like n entities, then this is something we're familiar with, and it's what you get with a gas. Okay, and this was Einstein's conclusion. From this we conclude monochromatic radiation of low density. This is all at single frequency, by the way, well, in frequency interval. Monochromatic radiation of low density within the range of Wien's radiation formula behaves thermodynamically as though it consisted of a number of independent energy quanta of magnitude h nu. I've emphasized the independent there. This notion of independence of these entities, the light quanta, really persisted right through Einstein's thinking up until 24, 25, and those Einstein papers. It's also interesting that when Einstein derives this expression, k log v over v0 to the n, he derives it modeling an ideal gas. He there speaks about point particles. And some have thought that he really is committed to the hypothesis that radiation consists of well-localized entities, not just entities that are independent, but are localized, because after all, they've got to get into that subvolume V0, and you could take that subvolume to be extremely small. So there was some sort of argument like this. John Dorling published a paper on this in the early 70s. That also was endorsed by John Norton more recently. But he doesn't say that when he states his conclusion here. And I think actually that's also a red herring. So I think that's not what the argument shows at all. But it is supposed to show independence. Now, why is this important? So look at the volume measure on phase space. So that's what these W's are. We're using combinatorics to determine the volumes. But the phase space is, the idea is it's a Cartesian product of n one-particle phase spaces. And with volume measure proportional then to the three-dimensional volume to the nth power. So this notion of independence really just involves this structure to the phase space that we're talking about. But it's not the only structure to phase space that we could consider. And now I'll help myself to Gibbs' two concepts, specific phase and generic phase. Specific phase is what Boltzmann had, it's what Einstein was using, it's what Planck used. But there was also this generic phase space where one takes the quotient of the phase space under the permutation group for those n particles. And the volume measure there is volume to the nth power, but divided by n factorial. And this structure is not a product of independent one-particle phase spaces and cannot be written as such. So there's a real question as to, well, what did Einstein show? And the crucial point is that if you look, if you do use the generic phase rather than the specific phase, because the number of particles is not changing, the n factorial expression cancels out so that you get exactly the same formula, the same expression here on the left-hand side, if you use the generic phase as the specific phase. In other words, Einstein's argument was insensitive to the distinction between specific and generic phase. Now, why does this matter? I mean, the first point is because of Gibbs paradox. I mean, the real underlying problem or interest of it all is this lack of independence that is introduced by taking this quotient. But let's just look at why Gibbs introduced it in the first place. And it is this issue, again, this isn't a fluctuation now, this is just a representation of a situation where you've initially got a gas, you've got some sort of a partition, two sides of the gas, volumes VA and VB, NA particles in one, NB in the other. Remove the partition, you've got a volume, total volume V, the sum of VA and VB, and now you have a total number N of particles, the sum of NA and NB. Consider the entropy before and after removing the partition. So this is straightforward entropy of mixing question. Do you have an entropy of mixing? Now, if the particles are independent, you must have a failure of extensivity. Think of it like this. The NA particles are now contained in volume V. If they're independent of the NB particles also contained in volume V, then it must be indeed the product of the entropy of the NA particles in volume V with the sums of the entropy here, but the product of the expressions W, because we're looking at the logarithms. So you have this right-hand expression for what happens with the partition removed. Before the partition's removed, you've just got the product of the V to the NA, V to the NB for the initial entropy or the W measure for each side of the partition. So because of the failure of equality in these two, you have a change in the entropy. And this is not restored on looking at the logarithms and using the Stirling approximation. Contrast what happens with the generic phase. Before the partition is removed, you then have the generic phase expression here for the W, the thermodynamic probability for the NA particles in volume VA, likewise for the NB particles in volume VB, divided in each case by the factorial, the factorial expression. The product of the two is that initial total entropy. After the partition is removed, we now have this rather different expression on the right-hand side. And in the situation where the densities, the number of particles NA divided by VA and NB divided by VB are approximately the same, under that condition, we now have using the Stirling approximation, so really you have to take the logarithm of the two, we now have equality. We get an extensive entropy. And why is it only approximate? Well, the point being, with the partition in place, you've got exactly NA and the particles on one side, NB on the other. With the partition removed, you can have some variation in that number of particles. So it's not exactly the same. There is some small increase in entropy, but with certainly for large numbers of particles, Stirling approximation and so forth, no problem. Okay, so let's just now think, all right, fine, we solved Gibbs paradox, but who cares anyway? Not everybody thinks Gibbs paradox is a problem. There are other ways of solving Gibbs paradox. It was far from the interests of pretty well everybody at this point. What was happening with quantum was far too exciting and interesting. Think of it this way. The correct volume measure is Planck's. And in the Wien regime, we have this expression here, that when V is much greater than N, and we have, it approximates V to the power N divided by N factorial. In other words, the correct volume measure for the Wien regime is the generic phase. It is not the specific phase. Photons in the Wien regime are not statistically independent from one another. Okay. So we really ought to just rule out, just on that basis, specific phase. And Einstein just got it wrong about the independence. So this might seem, well, it's sort of fun. It's an interesting footnote. But what really hangs on it? Why does it matter? Okay. So a number of questions. One is, what happens on working from Planck instead of Wien? Remember here, everything that Einstein was doing was using Wien's law. What does the generic phase mean? Interesting question. When was the connection with Gibbs paradox recognized? And why the failure of statistical independence? So a number of interesting questions. And let me just quickly give the general view, I think, certainly at the time, but I'll comment later. When you work from Planck instead of Wien, well, this is actually just takes you back to what Planck did. So bottom left, I've now given the analogous reverse engineering from the Planck distribution. And if you go through Einstein's argument, you'd get something like a ratio of these expressions here, this Planck combinatoric expression. And this was actually calculated by Ehrenfest and Camille-Ons in 1912. So it was not without, without the sort of capabilities of deriving this thing. But Ehrenfest and Camille-Ons made no further comment on it, and demonstrated it almost as a foolishness, as an absurdity. And that went with the derivation of this combinatorics expression using a simple argument, which they thought was a great joke. So this is Ehrenfest being adamantly opposed to whatever is going on with the analysis of the combinatoric expression in terms of what came to be called indistinguishable particles, where permutations of particles restore the same state. So I'm going to be saying much more about that in a few minutes. So that's one comment. Einstein could have done this. He may have made this calculation himself. As I said, Ehrenfest and Camille-Ons did, but no further comment from Einstein anyway. Now, what does the generic phase mean? Answer, people mostly think it doesn't mean anything. It's formal and it has no physical significance. This wasn't only thought at the time, it was, I think, thought for most of the period since. So we've got almost a century of debate on quantum foundations, quantum statistics, and it remains the case that many, I would probably, I guess, a majority, think that Gibbs' generic phase is purely formal, has no physical significance, and in particular has no application to classical particles. When was the connection with Gibbs paradox recognized? Well, I don't think it ever was. It wasn't at the time. There was one comment that Einstein made in his 25 paper, second gas paper on extensivity. He didn't mention Gibbs paradox per se. Nobody did. And almost nobody has since. So this is really surprising, a very peculiar situation. And I struggle to explain it. And of course, one explanation is I've got it all wrong and I'm deeply confused. But let's hope that's not the correct one. I think one explanation, an immediate one, is the reason nobody thought Gibbs paradox was relevant to any of this history is because none of the people mentioned it at the time. It's a very good reason. People like Planck and Einstein and Ehrenfest and so forth never mentioned Gibbs paradox. Why think it could be relevant to their discovery? So, there's sort of some logic to that. But what it went with is a determination that whatever is going on with indistinguishability, and it's relevant to Planck distribution, of course, it has no application classically. And then the question of why the failure of statistical independence. Well, insofar as it's acknowledged that there is a failure of statistical independence, of course it is acknowledged with Bose-Einstein statistics and so forth, it's supposed to be due to quantum. Okay. So let me just give a list, really, of how indistinguishable quantum particles are viewed I think, by the majority today. This is, I'm calling it an orthodox view. So first off, and this is in quantum particles. First off, they have no trajectories, so you cannot have indistinguishable classical particles. So there's a book by Bach called Classical Indistinguishable Particles, and it's a mathematical text, and it's all about classical indistinguishability qua probability distributions. And only at the level of probability distributions was Bach prepared to grant that classical particles can be thought of as indistinguishable. And he even gave a theorem that classical particles, you forget about the probabilities, if you just look at classical particles, they cannot be indistinguishable because they can be distinguished by their trajectories. Okay, so this book came out 25 years ago. I did try to contact him to discuss it, but I couldn't locate him actually. So further are not statistically independent, and often because Einstein supposedly showed that they were statistically independent in the Wien regime, perhaps statistical independence in the Wien regime. I think people who know about quantum optics would say no. Are entangled. Okay, and this explains the statistical dependencies, and it's linked further to EPR and Bell non-locality. Don Howard in particular has made quite a lot out of the connection between Einstein's gas paper, the second gas paper, where he notes the failure of statistical independence, cites de Broglie, says there's something peculiar going on here, influences Schrödinger, who's closely following this work on gas statistics, and thereby pointing Schrödinger to de Broglie's thesis. Within a few months, Schrödinger has the wave mechanics. So there's a very interesting line there of connection between this failure of statistical independence and Schrödinger's work. And it supposedly connects to Einstein's sense of something non-local going on in quantum theory with his photon box thought experiment, which was a sort of precursor to EPR. So this is something that I hope people are familiar with, and I don't have to go over it. Okay, are indiscernible. So also quantum indistinguishability means you observationally, as it were, you can't tell these things apart. And Heisenberg uncertainty relations imply these are needed in order to make it the case that you cannot tell them apart and so forth. The thought that you've got a blue photon going that way and a red photon going that way, and of course you can tell them apart, is one of those things that people seem not to engage with. So as often the case, when you don't really know what to say about something, you just skip on to the next question, really. So has no classical counterpart, well, see above, were prefigured in writings of Boltzmann, Planck, and Natanson. Natanson particularly comes up. Max Jammer made a big case for Natanson as being the crucial thinker who first really understood the nature of indistinguishability relating to photons. Not all historians have agreed that Natanson has that significance. Anyway, most historians do grant that the concept was prefigured in Boltzmann, Planck, and Planck at least. Several primary papers cited Planck. Okay, have nothing to do with Gibbs' generic phase. Almost all historians, none of the primary papers cited Gibbs, and have nothing to do with Gibbs paradox. Okay, experts, Ehrenfest, Van Kampen, Jeans, my chairman. So I fear how he will control the discussion, but I'm sure he'll be totally scrupulous. Beaks, anyway, deny that quantum mechanics is needed. Okay, so I've given you this list because almost every single claim is wrong. Every single claim, the possible exception of this last. Because my claim is you can solve Gibbs paradox without quantum mechanics. You do so classically. Okay, so I should add that I mean, there is another way to solve Gibbs paradox other than what Gibbs was doing, which is what this tradition beginning with Ehrenfest, and it's very much a Dutch school really, but beginning with Ehrenfest, another way, there's a sort of duality that works between Boltzmannian statistics and indistinguishable statistics, in the classical case anyway. And that's a very interesting question. And of course, if you're going to apply statistical mechanics to things like stellar nebula and large macroscopic bodies or colloids, where you've got very complex molecules, the molecules are really quite different one from another. And so what are you going to do to get an extensive entropy out? There is another way of doing it. Okay, I'm not going to really talk about that, but that's part of what's going on. So I want to now drill down a bit. And this is going to be slightly horrifying, but I'm afraid these are the expressions that anybody who really is going to understand this history needs to master. And they are, interesting because on the right-hand side, one's got integers. But if you look at these expressions that are being summed, they don't look like they need to be integers at all. You're taking ratios of these integral numbers, and who says those ratios are integrals? As soon as you interpret the expressions physically, it becomes obvious. I think I'm not going to talk you through the way to interpret them, though. It'll just take a bit too long, and we don't really have to go into the applications. But may I just note that this last one, very interesting and very different from the previous two, is what Bose, it's how Bose arrived at the Planck distribution through a combinatorics calculation, which he thought was the traditional Boltzmannian one. Because if you look at this thing, it looks rather like the Boltzmannian expression, and yet it delivers the Planck expression. And that's because, I mean, if you're looking at what you're summing here, well, no, I won't go into the details. All right. Let's see how those expressions played out between the key figures. So on the top left, I've got Planck and Debye. It's Planck, I think, 1901, who made this a bit clearer than in his 1900 paper. But Debye, I think, made it clearer of all. What we're doing with radiation, we're considering a frequency range, and I've now got a subscript S. We've got a number of light quanta, let's call them that, in that frequency range. We've got a number Z subscript S of cells among which they can be distributed. We've got the Planck expression, and that's giving us the thermodynamic probability W for that frequency range. And then the total thermodynamic probability, so the total entropy will be the logarithm of this, is then just the product. Okay. Now, if we do this with Boltzmann, we replace the Planck expression by the Boltzmann expression here, Zs to the power ns. And you might think, well, that's for frequency range S. When you go to consider all of the frequencies, you just take the product of all of those things. I've got a question mark because that's not actually right. But look, this is the crucial thing. What is replacing the Planck expression is this. Okay, now let me correct the thing on the right. What I've added in there is what's often called the Boltzmann permutability expression. This is to give those additional states, configurations of these distributions of particles in these different frequency ranges, where you consider permuting different of the total n particles. Different ones are assigned to different frequency ranges. Okay, so you n factorial, you multiply the whole thing by n factorial for all of the permutations involved, but then you divide by those where you are just permuting particles within a given frequency range. Yeah. Okay. And now here's the way that they are equivalent, approximately equivalent in the Wien regime. Okay, so on the left-hand side, I'm now just putting in the simplification of the Planck expression in when Zs is much larger than Ns. We then pick up this expression here, and we can write it like this. So everything's a product, of course, so I can just take all of those, the product of all of those Ns's outside of the product here. And guess what? This now looks like this, except for a total factor of n factorial. So in the Wien regime, with the sole exception of this overall factor of capital N factorial, we have agreement between Boltzmann-Einstein computation and the Boltzmann computation. Now, the crucial point, well, can I just say, if we look at now what Gibbs did, we have the same expression, Zs over Ns factorials. We take the product, and we now have exact equivalence with the Maxwell-Boltzmann expression up again to the total n factorial. So Gibbs was very easily reconciled with Boltzmann's combinatorics. Nobody, and this is just a claim, and I really would love it to be welcome to be proven false. Nobody pointed this out. And I think the reason why I'm confident that nobody pointed it out is because the Ehrenfest did not point it out in their handbook articles. So Paul and Tatjana Ehrenfest, which was a study comparing Gibbs statistical mechanics with Boltzmannian statistical mechanics. And the reason that they did not, or could not have been aware of this, they missed it, is because they looked at this expression here, and they just set it equal to a constant. It's a degeneracy expression, and they just said, oh, well, to simplify, we'll just set it equal to a constant, the same constant across all different ranges of momentum and so forth. So it's looking at gas particle statistics rather than radiation here. So if you do that, then you'll just be blind to this equivalence between Gibbs' reasoning and Boltzmann's reasoning. And I think this is why Gibbs, this last chapter of his book, was just so ignored. It just did not compute. It could not, it seemed, connect in any satisfactory way with what Boltzmann did. It seemed to make nonsense out of what Boltzmann did. Because in a sense, what Gibbs is doing, Gibbs would make nonsense out of Boltzmann. Because in a sense, what they understood it was to do is setting this thing equal to 1. And that's not really the point. I mean, yes, that thing is equal to 1, but the crucial thing is this thing replaces this. And this is what's hidden in this expression here, which was by the Ehrenfest set equal to 1. So I think had the Ehrenfest been aware of this equivalence, they would have stated it. I just think it's a complete no-brainer. Had they known, had they realized, they would have stated it. They didn't, and nobody else did either. Okay, so now let's just jump ahead a little bit and look at really what Bose-Einstein amounted to. It was what Gibbs did, I'm saying, exactly the same ideas. Consider, except that to consider Zs, this number of cells in a given frequency range, as no longer being much larger than the number of light quanta. Okay, so as soon as you do that, then we're essentially replacing what with Gibbs was a one-particle phase space with a continuous measure by a one-particle state space which is discrete. Actually, a finite number of cells. Okay, and once you do that and you ask for, when you permute particles, you get back exactly the same state, then you are led precisely to the Planck expression. So that was obvious in Einstein's second gas paper, but now working with material particles rather than with a gas of photons. And the Planck expression there was very visible here. Clearly stated, Einstein knew what he was doing at this point. it is the Cartesian product of all of these finite dimensional one particle phase space, so the analog of phase space is Cartesian product. And now look at what Dirac did. He turned each of these finite spaces of states into a vector space, but that wasn't actually so new. I mean, already it was a vector space in the case of photons. The one photon state, modeled classically anyway, involves these configurations of the electromagnetic field, a vector space. You sum these things, a superposition principle is operating and so forth, although that would be a real vector space rather than a complex vector space. So this was the important difference, complex vector space. And also that it is no longer the Cartesian product, it is the tensor product. And indeed, when you quotient out the permutations, you end up with the Hilbert space for a given frequency range. This is in a finite volume, and the dimensionality of that Hilbert space is just the Planck expression. So this Planck expression has been wandering its way through all of this work right up until Dirac in 26. Okay, so look, let me just come back to Gibbs. I've got to speed up a bit. I'm running out of time. So let me come back to Gibbs and ask the question, well, why was it thought to be so unintelligible what Gibbs was doing? Why did it seem only when you go to quantum mechanics that the thing made any sense, or at least, I mean, it's not that people really understood what was happening in the quantum case either, but it seemed that the failure of independence and so forth and indistinguishability was somehow acceptable. So look at Gibbs. First off, this is just statements from Gibbs' chapter where he's stating and uses the term indistinguishable for the first time in this context. And the idea is it applies to states, not to particles. Okay, it's not that the particles are independent, it's that the states are independent. So if the particles are regarded as indistinguishable, meaning that we identify states where particles are permuted. Okay, so this is the sort of mathematical machinery that Gibbs would have used. He would have been perfectly familiar with this. And on the right-hand side, I've just got a fairly standard and conventional representation of the specific phase. This is just take two particles, a one-dimensional phase space. And we can imagine coins, heads and tails, the usual sort of thing. On the right there, I've got the quotienting out the permutation of those two particles. So that a point on the right-hand side is just an unordered pair of phases. On the left-hand side, it's an ordered pair of phases, where the position in the ordering tells you which particle it is. And actually, it's worth noting, well, this is Gibbs, really just a comment on why, despite introducing this notion of the quotient space, he continued to work with the specific phase space. It's just easier to do calculus on it. The topology of the quotient space is quite complex. Okay. But it's worth just pointing out that the probability of heads and a head and a tail using indistinguishable classical, think of them as coins, flipping classical coins. And if they're indistinguishable, still the probability of a head and a tail is twice the probability of two heads, twice the probability of two tails. We have the volume measure. That volume measure for that square is twice what it is for the two heads or for the two tails. And this is something that really came rather late, at least the philosopher's imagination. It was with Nick Huggett's paper in 1999, was it 2000, one of the two, in Journal of Philosophy. David Albert remarks on this in his book, Time and Chance. Oh, you know, this observation, my goodness. You know, we'd thought that if you have classical indistinguishable coins, you'd get the Bose-Einstein statistics. No, not at all. So worth reflecting on this. Where does the quantum statistics, where does the quantum make itself felt, as Einstein said in 25? And the answer is when you've got not just that you've got a discrete state space, but it is the quotienting out. Because if you've got a smooth volume measure, you don't have a discrete space, a smooth volume measure, then the statistics and probabilities are exactly the same when you go to the quantum case, go to the discrete case or not. And the reason is, think of it in terms of counting the discrete state space, count the number of points. Now, when you count that number of points and you don't take the quotient, you've got a good approximation to the volume measure if you had a continuous measure. Okay, the continuous measure is just proportional to the count of the number if you don't take the quotient. When you take the quotient, that is no longer the case. Okay, and you can just look at that on the left-hand side there. You count that number of points, you get a different number. It's not half the volume as it would be if you had the continuous measure. Sorry, let me just go back here. So the quantum makes itself felt not merely, it's not merely discretizing the state space won't do anything to the statistics, but also taking the quotient does. This is just also a comment on those who say taking the quotient is just a convention. And indeed, the extensivity of the entropy is just a convention. It may seem that way classically, but you quantum case, you take that convention and you add to it the discretization of the state space, and you've got something empirically distinct and different. So I think this shows really a Kleinian point that talk of conventions in physics is often not very helpful at all. Okay, so the key point, what is going on with the taking the quotient and so forth? It is passing from ordered pairs to unordered pairs. And in quantum mechanics, it's passing from an ordered list tensor product to an unordered list. Call this anti-factorism. I think it was Jeremy Butterfield who came up with the term. And this is work of myself, Colton, Butterfield, Bigage, and a new take on what is going on with symmetrization in Hilbert space, but equally taking the quotient classically. You're really eliminating factor position as playing a role in both the kinematics and the dynamics. It plays no role in the dynamics insofar as the Hamiltonian is a symmetric function of its arguments, but it plays no role in the kinematics either. That is what is going on. Okay. Now, that's too formal. Conceptually, one still thinks there's something strange about what Gibbs is doing. And if you look at the entropy of mixing, I've now drawn diagrams for particle trajectories. When the particles, same kinds of gas, particles look the same. After the mixing, you've got what you think to be an entropy increase because there's more states available for the particles to explore. On the right-hand side, I've got a sort of, I've switched them back again. I've carefully redirected all the particles so they go back to the side that they came from. So that ought to be restoring the initial state. Okay, now does it? Gibbs is saying, yes, the particle at the state at T2 is identically the same as the state at T1. The angle at which all the lines cross the horizontal bar, that gives you the velocity, the position you've got there. And as you see, every particle that crosses this line, there's a particle here, this particle here, this particle matches this one matches this, and so forth. But they're difference in particles. So the whole question comes down to this. Gibbs paradox for two particles. Can the state of two things be unchanged when the state of each is changed? Okay, so it's a very simple question. And I think for a metaphysician, it seems no. The state of the two things must be different because each of them is changed. How can two things be unchanged if each of them is changed? I think it's a very natural way to be led to that thought. But look, we're doing physics. We're talking about a state. The state does not encode history. It could not encode history. The whole point of the dynamics is to give you the history from the state. unless you have a record, of course, in the history, which is present at a given instant. So the state does not encode history, and there's no reason to think that because the history may be different, the state is thereby different. Okay, so if you can accept this, and I think this is the sort of core conceptual difficulty that people had with Gibbs' ideas insofar as they really thought about it, this is what it amounts to. Okay, now when we go to quantum mechanics, we've got something similar. We've got, I'm symmetrizing now these two states, but we can have a unitary that evolves phi to eta and eta to phi, interchanging the two things. The state at the end of this is exactly the same as the state before, mathematically. That's just a fact. But it's equally with the quotient space when you quotient out permutations in classical phase space. I mean, this isn't quite right. We do need a continuous, if we're going to mirror what's happening classically, we do need a continuous unitary evolution that takes the state phi continuously over to the state eta, eta continuously over to phi. And in this way, we match what was happening classically. Right, so this is the claim that almost everybody makes. Indistinguishable quantum particles have no trajectories. And I hope to have shown that to be false. Anyway, what also goes with this is that entanglements produced by symmetrization are trivially entangled. And this, again, is more recent work. This is partly perhaps why these ideas were not so available until the last 20 or 30 years. So this is Gherardi, Marinato, Rimini, myself, Penrose, Colton, a number of people, that entanglements merely produced by symmetrization are trivially entangled and cannot be used to violate any Bell inequality. That was Adam Colton's work recently. Right. So where have I got to? I think let me come to an end. I want to end though with well, what happened next? So Einstein, not appreciating the connection with Gibbs, never citing Gibbs anyway, seeing the failure of statistical independence, he's working in the quantum case, thinks it's bound up with something funny with quantum, says so in his paper, cites de Broglie's thesis. Schrödinger reads that. Schrödinger also thinks that it's unacceptable, this failure of independence. Works very hard for the whole of 25, trying to get out the Bose-Einstein gas without the funny statistics, without the failure of statistical independence. And he's led to a field theoretic way of thinking about it. So it kind of connects with some of the ideas in de Broglie, but I think really not much. And when he finally frees himself from this gas theory, and this would be by, I suppose, January of 26, he then looks at de Broglie just with the point of view of, can we use differential equations with boundary conditions in order to give quantization conditions? And that is the crucial step that led to the wave mechanics. What I hope you learn from my talk is that the failure of statistical independence is not a quantum effect. I mean, that's the crucial point. It is not a quantum effect. It is a classical effect. And one needs to understand that better, and I don't think we actually have as good an understanding as we like. And I'm going to close with this photograph. This was taken in Caltech in 1932, 31, I think. And this is Paul Epstein. But Paul Epstein, 3 years later, wrote a very lengthy chapter, the first time looking at Gibbs' notion of indistinguishability. It should have been the point where the threads were drawn together. Here he's talking with Einstein. They could have spoken about it right here and did not. And we know they did not, because what Epstein had to say, this was in a 2-volume work of Yale University Press devoted to Gibbs' writings. His chapter was all about why Gibbs' ideas are inconsistent with a finite state space. So completely, I think, failing to understand the connection. Okay, so it's been a complex story. I hope I've given you this thread that runs through it, and there remain open questions. I don't pretend that it's a sole set of questions, but that's as far as I've got to for now. Thank you. Yeah. Thank you, Simon. You've got 7 minutes for discussion. I'm sorry.
Well, the microphone's coming around, so wait to speak until you have the microphone in your hand and put it close to the mouth.
Thank you for the very interesting talk. You presented what can sound like kind of a sad story for those of us who are fans of Gibbs's. You explained why and how Gibbs was ignored for a while. What is the positive side of the story? When did his work come to be widely recognized? How did it come to be that in our undergraduate statistical mechanics classes, we now learn about the Gibbs paradox? How was that discovered and welcomed?
Yeah, so it's an interesting story, the question of this paradox. I think what happens in standard physics courses when you're taught Gibbs paradox is you need to divide by n factorial, and this is a quantum effect. And it is a residue of quantum that you have to divide by n factorial. So that is what I'm saying is wrong. Okay, it's already classically you divide by n factorial. It's the right way to do it because you identify the state of two particles if they change positions and momentum. Why? Just a further point on what Gibbs did. So this is Van Kempen. He calls this notion of identifying states with differ by particle interchange mystical. Or James, he calls it the writings of an old man in ill health, because he died the year after. He was only 62 or something, and he died the year after from a sudden illness. So so extraordinary lack of charity, really, in trying to understand Gibbs. But I think every textbook I've looked at, I would love to find one that differs, says divide by n factorial, it's a quantum effect.
My question was, how did Gibbs's work come to be instead of, since as you argued, it was originally ignored and spat upon, how did it come to be widely recognized and welcomed as it seems to be, at least to me today?
But I don't think it ever has been. So, I mean, I'm interested in what you have in mind. The paradox, it has been well, how to put it? I mean, it's been carried through, people are aware of it, and so forth, but understand quantum is the solution to it. And so I don't think any physics text teaches Gibbs' solution to it. Of course, Gibbs did so much else in StatMech. All of that, hugely important, dominates contemporary statistical mechanics, but not this bit, this generic versus statistic phase.
I mean, you touched on this yourself, but I'm still worried about stars and colloids.
No.
I mean, it feels like there's at least a bit of the narrative that says this isn't a quantum effect, but it is a consequence of the genuine, if you like, metaphysical indistinguishability of particles. And of course, as you know, there are plenty of situations where the particles are manifestly distinguishable at the metaphysical level. It's just not dynamically salient to the problem at hand. And we still divide by n factorial. So I'm sort of struggling to understand how the narrative comes together. I mean, there's one reading where we have a fundamentally disjunctive reading of what's going on, but I don't find that attractive, and I'm surprised if you do. So can I invite you to say a bit more about how the colloids and the stars fit into this?
Yeah. I mean, I think one way of looking at it is that one thinks if the dynamics is blind to the distinctions, then the Hamiltonian will be the symmetric functions of the coordinates. But the question is whether the kinematics is relevant. And this for me, it remains an open question. I mean, there's a way, as you yourself have shown, David, you must publish that little paper that you wrote. Really, come on, you've got to. I know you were not entirely happy with it, but you must publish it sometime. There is a way, there's a sort of a dual way of understanding it within open systems, whereby you can, treating them Boltzmannian specific phase, one can recover an extensive entropy. But I don't think that works for a closed system. That remains controversial. There have been claims that you can do it for closed systems. Swinson is someone who's written on this the last 15 years. And indeed, it was an edition of the journal Entropy that I published with a collection of papers in it, which have these arguments. Even for a closed system, I think they fail. So there is in open systems theory, there is a way of recovering extensivity. It's consistent with a specific phase, but for closed systems, I don't believe there is.
We still divide by n factorial when we're
classically.
Yeah.
Yes. The way to deal with closed systems classically is the Gibbs way, identifying states that differ by permutations. So that works for a closed system. Now, take a colloid as a closed system. And can you get out an extensive entropy for it? I don't know that you can. I'm not sure that you can. So that's.
Thank you. Simon, just a comment. I think there's something missing in the history here. I'm not sure how important it is. But as you mentioned, Einstein and Schrödinger both read de Broglie's thesis. I'm not sure how widely known it is that in de Broglie's thesis of 1924, chapter 7 is about black body radiation. And of course, he has at that time, he has his one-body pilot wave theory, has photons with the guiding pilot waves. And he tries to derive, he claims to derive the Planck distribution. And Darrigol has pointed out, I think, some mistakes in what he does. But there's an interesting comment that de Broglie makes. He says that if the photons have the same pilot waves, or say you have two photons that have the same pilot wave, they can no longer be regarded as independent in their motion. And so from the point of view of probability, they cannot be treated as, in his phrase, separate units. I thought it might be at least an interesting footnote to what you're talking about.
Yeah, I mean, it wasn't only in de Broglie's work. There was a whole set of papers, a slew of papers. People like Planck were involved in this, where they were speaking of sort of molecules of light. When you get lots of essentially light quanta in a single state, it acts as a single molecule and then can be thought of in terms of Boltzmannian terms as a specific phase. So there's a debate about this that went through the years 1918, 1920. So not just in de Broglie. I think de Broglie was important. You're the person who can tell me this. I mean, what did Bose do? It is always a question. How is this person able to be immortalized forever on the basis of a single two-page paper with a fairly elementary calculation that should have been obvious to everybody? How on earth did that happen? But what Bose did, and I think it was genuinely new to him, but possibly de Broglie too, was to think that the light quantum had its own state space. That was this crucial move. I should have perhaps made this point more clearly. Looking at this business, we've got this state space for the one light quantum, one photon state space, which is finite. So that idea was really from Bose. But before then, nobody thought of a light quantum as able to change in its properties, its momentum, its position, and still remain the same light quantum. But I think de Broglie had that conception too.
Yeah, I think there's, if I remember right, I think Abraham Pais somewhere suggests that de Broglie had this before Bose, but I don't remember the detail. The references are all in on my. Yeah.
Thanks, Simon, again. What's the matter? Just wait for the mic.
Sorry I was late. I unintentionally was wandering through non-zero meadows. Non-zero other colleges. Test, test. All right, there we are. Hi, everybody. So it's a pleasure to be here. Thank you to Chris for the invitation. And I know I promised some of you guys that I saw at the Perimeter Institute that I'd be speaking about a paper I'm working on called To Beable or Not to Beable. I don't know if it's because you're my friends, but I keep getting pulled out of the metaphysics and into history again. So I'm going to be speaking on wave particle duality for electrons and just more the experimental side. Dovetails nicely, I think, with some of the things Simon was discussing. So one of the reasons I want to introduce this history from the experimental side is because I've been also doing a bit of work on Hertha Sponer, who was probably one of the first quantum chemists. And this is part of an ongoing project that is Women in the History of Quantum Physics. And she did some important work in the sort of trajectory toward understanding the duality of matter that I wanted to reintroduce. So this is a nice way to do that. But it was interesting to see that doing the research for this talk over the last day, that's not quite true, but not quite not true either. The experiments themselves had various interpretations of what this duality really meant. And I suppose this is unsurprising that a century later we're still debating what it means, though we may have clear evidence of particle-like or wave-like phenomena that we nevertheless don't know what this means or how to ascribe these properties to the world. So, all right. So let's remind ourselves quickly of the usual story about how we moved from a purely corpuscular theory of matter to something dualist. So Schrodinger has this little paper in the Scientific American in 1953. It was based on a talk he gave for a conference in Geneva. And so this is the English translation, but I think in the original French he uses the word ass. So I'm going to use the word ass. But let's start with this text on the far right. It's a condensed version of the story. So he says, according to Einstein, a particle has the energy mc squared, m being the mass of the particle and c the velocity of light. In 1925, Louis de Broglie drew the inference, which rather suggests itself, that a particle might have associated with it a wave process of frequency mc squared divided by h. The particle for which he postulated such a wave was the electron. Within 2 years, the electron waves required by his theory were demonstrated by the famous electron diffraction experiments of Davison and Germer. This was the starting point for the cognition that everything, anything at all, is simultaneously particle and wave field. Thus, de Broglie's dissertation from 1924 instantiated our uncertainty about the nature of matter. Both the particle picture and the wave picture have truth value, and we cannot give up either one or the other, but we do not know how to combine them. Well, maybe Antony does. So he also has this nice little quip on the left. So like Cervantes' tale of Sancho Panza, who loses his ass in one chapter, but a few chapters later, thanks to the forgetfulness of the author, is riding on the dear little animal again. Our story about matters has contradictions. Sancho Panza's ass will return, for I shall have to ask you to believe neither in corpuscles as permanent individuals, nor
in the suddenness of the transfer of energy of quantum. Discreteness is present, but not in the traditional sense of discrete single particles, let alone in the sense of abrupt processes. So this is Schrödinger sort of shrugging his shoulders and saying it's unclear what the ultimate interpretation of this dual picture is. He does have this very nice experimental side-by-side of light interference on the left, and then I'm guessing it's, although he doesn't say, it's from von Laue and others who've been working with really nice crystals and doing crystal diffraction with electron, that you get this electron interference pattern on the right. Okay. So a little bit more meat on the bones of this story. We have from one historian, Rousseau, who's writing in the 1980s, that the discovery of electron diffraction was announced in 1927 by two American physicists, Davison and Gamow, and at the same time by the English physicist Thomson, who was at Aberdeen. So the discovery, again, this is another version of the canonical story. The discovery represented a direct experimental proof of the wave properties of matter, suggested for the first time in 23 and 24 by Louis de Broglie, formalized in wave mechanics by Schrödinger in 26. The subsequent probabilistic interpretation of the wave function proposed by the physicists of the so-called Göttingen-Copenhagen school will give the general conceptual framework in which the wave corpuscle dualism finds theoretical coherence. Davison and Thomson received the Nobel Prize in 37 for their discovery. Thus far, the usual story. Let's do the story again, but this time with a bit more nuance. So looking back to Ramsauer's original diagrams, and I think this is from the 1921 B paper. A was just a talk that he gave. He found, in case we're not remembering, right, an unexpected very small scattering angles for very slow electrons in some but not all noble gases. So according to classical theory, the line G there is what we would expect. And instead we get cross sections that are vanishingly zero toward the left-hand side for argon. Not for neon. Neon sticks pretty close to the classical electron theoretic description. Helium's a little bit wonky, but not like argon. So something very strange is going on here. It looks like electrons, when they're very slow, hardly interact at all, are basically transmitted in modern parlance. So Ramsauer is often left out of the histories, I think, because we tend to focus on less on experiments and more on the sort of the Knabenphysik and the interesting development of theoretical work. But Ramsauer in particular, sense that he's not included in some of the histories because at the time people were very fuddled. In fact, his data were considered, his results were considered spurious by many, except with a few physicists in Göttingen. So Born and Frank and Hund and a few others did take seriously the Ramsauer results and worked very hard to try and find an explanation based on classical electron theory. And when that failed, using the correspondence principle to introduce some of Bohr's principles. But it was unsuccessful. So nevertheless, while this theoretical work is, I guess, failing to explain the Ramsauer results, a whole suite of other experimental data are presented. So we have, I've already covered this. Let me say a little bit more. In 22, 23 in particular, Hund, who's a student of Born's, sort of takes up this puzzle of what's going on with the Ramsauer results. And Frank is involved as well. And this part is not in the history a lot, but Martin Jenert has a very nice little 2019 book where he gives a very thorough description. An entire chapter is dedicated to the way that Frank and Hund moved from a classical electron theory description to something that was quasi-classical using the correspondence principle, but in the end it's no good. So quoting from Martin here, he writes, Frank and Hund abandoned their initial approach to the Ramsauer effect in the fall of 22 and developed a new interpretation on the basis of the correspondence principle. Instead of explaining the effect by manipulating the classical force field of the atom, the new interpretation assumed that slow electrons actually ceased to interact with the atom. But this also fails. And so by the end of 1922, even in Göttingen, so the story goes, they had given up trying to explain these results. Nevertheless, the experimentalists continue on with it. So Ramsauer continues this work. We also have Meyer, Townsend, and Bailey almost at the same time as Ramsauer are doing scattering experiments with slow electrons, low energy electrons. We have Hertz doing work, I think, on argon. Davison and Kunzmann, which is an important result, happening over at Bell Labs in my hometown of New York City. And then Townsend and Bailey and Davison and Kunzmann continue to give a series of papers. So the electron diffraction game is alive and well, despite the lack of theoretical understanding. So let's go back to the usual story a bit. So as has been mentioned a bit already, de Broglie in a series of papers in 23 and then in his dissertation of 24 worked out the first sort of guiding wave theory, I guess we could call it, and he's postulating that and stressing the optical mechanical analogy that body in motion ought to exhibit diffraction phenomena, so matter as well as light. Einstein, as we heard already from Simon, is excited by this. He works on his ideal gas theories, the second paper of which is about matter. And Schrodinger gets involved. They're all very excited. They're working on wave mechanics, blah, blah, blah. Not the story I'm telling here. Meanwhile, a young graduate student, 21-year-old Walter L. Sasser, tells the story about how he's sitting in the library at Göttingen and he's just heard about Einstein's second paper on the ideal gas theory, and he's been reading Broyle's thesis, and he also has been talking to Frank and Hund about the Ramsauer stuff, and it all synthesizes in his mind in a beautiful way, and he has an aha moment and realizes not only that what Ramsauer is doing in his scattering experiments is showing the same kind of phenomenon that's being seen by Davison and Kunzmann, who are shooting electrons at a nickel plate and at crystal gratings. So not only are they showing the same thing, but what they're showing is evidence that de Broglie asked for already back in 1924, namely evidence for interference and diffraction phenomena for matter. So the results, he says, and in his little letter that he writes up for Die Naturwissenschaften in 1925, are qualitative at this point. They don't entirely fit the equations, but nevertheless, he makes this radical suggestion. Interestingly, this paper wasn't going to be published, but Einstein intervened and said, I think this kid is onto something. Go ahead and publish this little note. Back in the main story, as Anthony and Guido have written nicely in their Solvay book, you can read de Broglie's presentation and his discussion of some preliminary results on the wave theory and Diamond's results were later seen to be spurious. But there is some discussion in the discussion at the Solvay conference about whether there is sufficient evidence for material waves. And it seems that the consensus is not yet. And so there's a lot of skepticism around this. But again, as the story goes, by the time we get to the very end of 1927, Davison and Germer published their results. They're at Bell Labs, again in New York. And everybody is very convinced, no more questions about it. We have electron duality, the end. So let's revise this story. For one thing, let's put Hertha Sponer in the story. So who was she? And this bit is a bit of a repetition from my previous talk, so apologies to those who've heard it before. But as Catherine Brading once told me, never underestimate how fun it is to hear about something you already know. So you're welcome. So who is Hertha Sponer? She was born in 1895 in the Silesia region of Prussia. She studies physics in Friedrich Paschen's lab in Tübingen, but then she begins working with Debye because the war messes things up and people's labs close and so forth. She follows Debye to Göttingen and does her PhD with him in 1920. And interestingly and importantly for this historical story I'm working on, Paschen and Debye and the others that she's working directly under were early adopters of Bohr's quantum theory. So it's not surprising that she too, who would later demonstrate extreme, prodigious theoretical prowess, was quick to understand and to take up Bohr's quantum theory and think, yes, this is the way forward. In her experimental work in spectroscopy, she's mostly looking at the dissociation energy of diatomic molecules, but she's always giving alongside her data theoretical underpinning for these results, and that theoretical underpinning is often citing Bohr's quantum theory, or the Bohr-Sommerfeld quantum theory. Okay. So I just note here that it's not till 1919, 1920 that women in Germany are first given the right to qualify for the Habilitation, which is what allows you, even if you have a PhD, to then teach at the university and advise. And they're also given the right to become Privatdozentin. Okay. In 1920, she's an aide to Hilbert briefly, and I would really like to have an aide of this sort. I mean, Hilbert just gave them the hot off the press theoretical work and said, go learn this, come back, explain it to me in simpler terms. And she loved this and thrived at it for a while. And in fact, so much so that she went to Dubai and said, I would like to become a theoretical physicist. And he said, no, don't be crazy. I paraphrase. This is not just because she was a woman, although that's certainly part of it, but because there weren't any theoretical physics jobs at the time. So a lot of people who were finishing their physics degrees at this time were sort of encouraged not to pursue theory, though she was very good at it. So she works with Frank and Haber at the Kaiser Wilhelm Institute in Berlin, but then she comes back to Göttingen. And in fact, when the Physics Institute #2, which is the experimental institute there, gets set up and Born is brought in as the head, Frank brings in Sponer to do the work of the labs. And in the Archive for the History of Quantum Physics, interviews that Kuhn and Maria Goldberg-Meyer do with Frank and Sponer, because they do get married later in their life. Frank says, I didn't really do any lab work. I mean, he did the running of the things, and he also ran between the Physics Institute 1, where Born was the head, and the theoreticians lived, and the data that Sponer herself and her students and assistants were producing at the lab. So he didn't, he says, get his hands dirty with the experimental work, despite being the head of the experimental institute. All right, so she gets her habilitation in 1925. There's a brief sojourn to Berkeley as one of the first Rockefeller Fellows to work with Burge, who was a really famous American spectroscopist at the time. He, while she's there, tries to preach the gospel of the quantum. And I note that this is long before Oppenheimer is even around. I mean, he's a baby at Harvard at the time, so Oppenheimer did not pace the story that Christopher Nolan would like us to believe, introduce quantum mechanics to the West Coast. Sponer was one of the folks who did. And in fact, she argued with Gilbert Lewis, who was at Berkeley at the time, and one of probably the leading chemist, went to his seminars and would sort of bother him, proselytize him afterwards and say, look, this quantization stuff like that we're dealing with in Göttingen, this is the right way to go. And she said, I never could quite convince him. He tried to do the same thing with Burge, and Burge refused. In fact, the paper that they co-wrote after her time here, and is still a very famous result for a new precise technique for measuring these dissociation energies, is so good and precise because it is taking Bohr's quantum theory to heart. And when Sponer not only these support this new technique and gave the theoretical underpinning in the paper, Burge wrote to Campbell, another famous American physicist on the East Coast, and said, I really don't think that this quantum stuff should be involved. I also don't think it's right for this theoretical explanation to be in our paper. It should just be about the method and the data at the end. And Campbell says, no, she should let her do that. And in fact, those pieces of the paper are the parts of the that Sponer contributed. The quantum theoretic explanation and the new technique were developed all by her. She also interacts with Condon, who's there. Condon was originally working on something else for his PhD. She convinces him to think more about quantum again. And so he ends up working on what would become the Frank-Condon principle. So he does a fully quantized version of what was the semi-classical Frank principle, and gets fame for that. Okay, so that's her brief trip to Berkeley. In 1929, she's offered a research, or she's going to be given a research position at the Kaiser Wilhelm Institute in Berlin. In fact, the head of a small group, but various folks, including friends of hers like Haber, Frank, Hahn, and even Lise Meitner, who was a close friend, persuaded each other that she should not have this opportunity. And I haven't seen their letters about this in detail, so I need to figure out more about it. It would be an interesting historical pace because these were folks who understood that already at this time she was internationally renowned, Sponer that is, was an internationally renowned experimentalist. And so that they actively blocked her from getting this position is worth looking into. But she was also blocked for clearly misogynist reasons by Planck and others. They outright said women should not be doing physics. Okay, so she, back in Göttingen, ascended the ranks, became basically equivalent to an associate professor there. During the war, she goes to Oslo. When Frank and others leave the Göttingen Institute for political reasons, while she's in Oslo, she writes a really important textbook on the application of molecular spectra to chemistry problems. And then when she comes to the US in the 30s, is appointed the first female professor of physics at Duke. And then that's where she remains. So much of the work that's done on Sponer concerns her American career at Duke. And Duke has her archives, and she in fact did a lot of really interesting stuff while she was there. And of course, not as interesting from the perspective of the history of quantum. So I've been trying to recover a bit for contributions in these early years. One of the contributions I won't discuss today, but I've mentioned elsewhere, is that it looks like she's one of the first, if not the first folks, along with Frank, to take quantum tunneling seriously and apply it to explain hitherto unexplained chemical phenomena, like saying that quantum tunneling can explain these strange like rotation energies for diatomic molecules. So again, this is fitting with her theme of being an early adopter, that quantum explanations are going to be correct ones. But we want to understand her role in this story about the discovery of matter waves. Right. So here's an image. Hertha Sponer is on the far left there, and you will recognize some of the other folks in this picture. Pardon me. So there's Einstein. The Franks are sitting next to Einstein. Lise Meitner is, the only other woman in the picture besides Mrs. I think Inge Frank and Hertha Sponer. In the back row, we've got Walter Grotrian, Westphal's there, Otto von Bayer's there, Peter Pringsheim, and Gustav Hertz on the far right. I showed in an earlier talk this funny image I found, funny depressive, not ha-ha funny, like sad funny, image of the Göttingen Institute #2. She was running it, but there she is. Can you find her? And their backs are literally turned to her. But I was looking at some more of the archival pictures the other day, and I found this other image. Same one. I mean, she's wearing the same outfit, but there she is in the center, but it's blurry. So maybe that's why, like, this is the one that they use. Just the fact that she looks, unhappy. There she is, happily ensconced. Okay, so let's see if we bring her stories back into, bring her research back into this, keeping in mind not only that she was a famous experimentalist working on this slow electron matter in and amidst all of those various electron diffraction experiments, but she also had this deep investment to theoretical, like, understanding of why they were seeing what they were seeing. Okay, so we've already seen the Ramsauer, the Meyer, the Townsend-Bailey, Hertz, Davison, Kunzmann. But in 1923, Sponer and Rudolf Minkowski are collaborating, and they publish a suite of papers. And in particular, it's the 1924 paper where they not only new electron diffraction data that they have found, they summarize all of the previous results. And not just summarize them, but evaluate them carefully and say, okay, of these results, they're all showing something similar. But Ramsauer and Davison Kunzmann are doing the best, and what it is they're doing is entirely quantum mechanical. So I'm going to say a bit more about that in a moment. Okay, so there are a few historians who have included Sponer in the story. So here's this Rousseau. He was the guy who was telling us about Bell Lab. He mostly has written about the history of Bell Labs. So he's writing about Davison's part in all of this and how Davison got the prize. But he mentions that well before de Broglie's work was known in Göttingen, two young experimental physicists working there, Minkowski and Sponer, had been strongly interested in Davison and Kunzmann's results. They suggested a relation between the American experiments and the so-called Ramsauer effect. Now, I highlight this because usually Elsasser's 1925 note in Die Naturwissenschaften, the one that he needed Einstein to sort of promote, is the one where people say that he was the first one to realize that these electron diffraction experiments happening on the continent were demonstrating something like, well, diffraction of electrons, but that should be interpreted as wave-like. Whereas Davison-Kunzman is typically understood to be showing interference because they're working with crystal gratings. Here we see that these are already understood as showing something that is the same about the electron by Minkowski and Sponer. So continuing on, Minkowski and Sponer too had experimented on the Ramsauer effect, and after reading Davison-Kunzman's 1923, published a detailed analysis of the results. And this is the 1924 paper I'll say a bit about in a moment. They attempted to explain the Ramsauer effect as well as Davison-Kunzman's patterns on Davison's atomic model without, as Sponer would report, any help from the theoretical people. So though they were buddies, with the Institute 1 folks who were doing the theory and trying to grapple, like Hund and Frank were, with the meaning of the Ramsauer results, here they were over in their lab, also trying to understand these and working out an explanation for them. So adding a bit more to the Elsasser story, not that he was just sitting in a library and, they'd been talking about de Broglie and Einstein's new theory of gases, but also the Ramsauer effect, and it came to him, right? Sponer and Minkowski were also talking with Elsasser, and they were, in fact, the ones, according to Elsasser himself, who told him that Davison-Kunzman, the interference effects they were seeing were in fact interference effects, and that this had something to do also with the diffraction scattering of the diffraction of low energy electrons being done by the continental folk. Okay. And in fact, this conversation with Sponer is partly what inspired him to write the little note, because he was not quite satisfied. He agreed with Sponer and Minkowski that this was a purely quantum phenomenon, but he didn't like the explanation that they gave and wanted to go a bit further on it. Okay. Some other folks who knew about the Sponer-Minkowski 1924 paper and their research was, Heisenberg. Not surprising, Heisenberg was also interacting between both the Institute 1 and 2 in Göttingen, and interacted a lot with Sponer, says she spent a lot of time conversing with Heisenberg. Again, her theoretical interests and prowess are sort of the reason that she's often sitting between the two institutes, even though she's physically running the one. This is my translation. Heisenberg writes to Pauli. This was already in 1926, so it's a bit late in the game, I guess. But he says, the new Einstein paper on atoms moving in accordance with wave theory. So this is the second 1925 ideal gas paper by Einstein. Apply this theory to slow electrons and you get the Ramsauer noble gas curves. Or even better, you shoot slow electrons onto a crystal lattice and get a spectrum of first order, second order, etc. These experiments were done a long time ago and are in the article by Minkowski and Sponer. So there's some institutional knowledge, I guess, at the time that this work was being pursued. Okay, so what is the story that Frank and Sponer themselves tell about it? In their oral history with Kuhn and Goppert-Meyer, which was done in over a couple of days in July 1962. In the archives, these interviews, although they are both with Sponer and Frank, are just labeled the Frank interviews. It's interesting because Sponer is not quite mentis compos at this point, and so she needs a lot of prompting. There's a bit of dementia coming on. So Frank and Kuhn and Goppert-Meyer have to sort of cue her at a number of places. But nevertheless, Frank goes out of his way to sort of say how much of a contribution she made. So Sponer, I guess, is like wandering in and out of the room during these interviews, and particularly when they start speaking about Elsasser and the Ramsauer effect, because of course Kuhn had been asking Frank about the Frank-Hertz electron diffraction experiments, which were for an entirely other purpose, but are part of this long train of electron diffraction work. Frank says that he remembers Elsasser coming to him after having read Einstein's paper and reading de Broglie and saying, it'd be nice to show the wave character of the electron. And Frank says that he responded to Elsasser, well, this has already been done by Davidson and Kuntzmann, although they themselves don't know it. But then I'm prompted by Kuhn, who says, is that really right, Frank? He changes his mind and said, oh, right, maybe it was Elsasser's idea to connect Ramsauer and Davidson-Kuntzmann. And at this point, Kuhn again corrects Frank and says, actually, your wife was the one who did it first. And she had connected Ramsauer and Davidson-Kuntzmann already in 24. He comes into the room and then she says, oh yeah, that's what I remember. We've been thinking about how to interpret the Ramsauer effect for a long time, even though many people thought it wasn't worth thinking about, and that they'd worked out the theoretical bits themselves. So this is the quote that Rousseau had given earlier. Okay, so let's look at this just a few bits from the Sponer-Minkowski 1924. I really ought to translate the whole thing because it's a really fascinating paper. But we're going to skip to the explanatory bit. I mean, so they've just given a catalog of all the different diffraction experiments and some of the scattering interference type experiments, and argued for why a number of theoretical interpretations, for instance, by Hertz, and they mentioned Hoon's dissertation, fail. And in fact, they say that these explanations for the diffraction data fail because they are still trying to use some kind of classical explanation. They're still appealing to classical electrodynamics. So in summarizing all of this, they write the following. One assumes the validity of classical electrodynamics for describing the motion of an electron in an atom. Then in the field of an atom, an electron experiences a deflection due to electrostatic attraction between the nucleus and the electron, and at the same time, a loss of energy through radiation due to acceleration. This is the familiar Bremsstrahlung phenomenon. At low speed, on the other hand, this is again still according to the classical electrodynamic description, energy loss becomes increasingly considerable, ultimately exceeding the kinetic energy. Then the electron can't leave the atom. It has to move on a path that gets closer and closer to the nucleus and finally falls into the atom. This conclusion is obviously in open contradiction to experience, that is, the experience of all of the data they've just cited. Therefore, it's expected from the outset that a description of these processes at slow speeds cannot be achieved assuming the validity of classical theory. In summary, it can be said that despite validity of energy and momentum conservation law, the collision of electrons with atoms are completely unmechanisch, and apparently can only be described according to the laws of quantum theory. Now, I've been trying to understand what they mean by the unmechanisch thing, and I think it might reference to de Broglie, because de Broglie's theory is explicitly entirely mechanical. I'm not sure. This applies, back to the quote, this applies not only to the so-called inelastic collision, which stimulates quantum jumps in the struck atoms, but also to elastic collisions, in which so-called elastic collisions, in which the incident electrons penetrate into the interior of the atom and dissipate there under the influence of the nuclear charge, effects which at high speeds indeed can be adequately described without quantum theory, but which at low speeds deviate completely from what is expected. So this is the first interpretation of the diffraction and of the interference phenomena for electrons. That is pointing out it must be entirely quantum mechanical. But still being unsatisfied with this, Elsasser will then propose that no, it's not just that it's quantum mechanical, but it's evidence of particle wave duality for the electron. Okay. So I want to skip over just for the last little bit to sort of this larger question of what the experimentalists thought they themselves were doing, because even when Elsasser, boldly says in his little note that we can understand the electron diffraction experiments with slow electrons to be just that, diffraction, that can only be described in using wave equations. But that the Davidson-Kuntzmann experiments were interference. This is clearly wave. These are clearly wave phenomena. Ergo, we must understand electrons to have the same duality as lights. And after all, is this so surprising? Are we so confused? But that we can give that electrons give rise to these dual or complementary phenomena is not the same thing as understanding why they do that. And there is, again, no settled question on this, but the experimentalists themselves didn't agree And I haven't dug into this as much, but it's an interesting project perhaps for posterity. Davison and his colleagues, so Kunzmann first and then Germer later after the war, were not at all investigating the nature of electrons, right? They were looking at crystals. They were trying to develop also thermia. They were building vacuum tubes at Bell Labs, right? It was very pragmatic. They were fighting over patent issues, and they were in this lively competitive atmosphere. There's an experiment that goes awry at one point, like a canister explodes and oxidizes the nickel plate that they're using to reflect the electrons off of. And that when they're trying to fix that remove the oxidation, when they put the crystal back and run their experiments again, they get really wonky data. But this informs them that the crystal structure itself, the crystal labs, had been affected by this oxidation removal process, right? And so they start thinking a little bit more about, well, what does it mean when we're doing these experiments? And can we say something about the electron itself, not just the nature of the crystal we're trying to explore, right? More interestingly, there's a side story about Davison. I mean, so Davison is the one who, Davison and Thompson, again, who I mentioned is at Aberdeen, get the prize, the Nobel Prize for electron diffraction. Not Davison Kunzmann and not Davison Germer, just Davison. But in 25, he sends some of the plots and the graphs. They're really like bad. They're undergraduate style, like data points, right? And a little bit blurry, not great. Sends them to Bohr in his capacity as an expert on crystal interactions. And Bohr is really unimpressed, but then later on changes his mind. It says, only after discussion with Frank did we both realize that such a pattern could be explained by diffraction of electron waves by atoms in the crystal. But again, this looking back and saying we realized that this was the case is not borne out by the evidence. But okay. Nevertheless, we also learn that Davison came to Oxford, and here we are. So I thought I'd introduce this bit of the story. So Rousseau, the historian, says that it's likely electron diffraction would never, I guess we should call it electron interference, maybe, would never have been discovered at Bell Labs had Davison not spent a holiday in England with his wife in the summer of 26 and seized the opportunity, which I'm sure his wife was pleased by, to come to the British Association for the Advancement of Science at Oxford. And it was there that he learned about de Broglie's theory and the various attempts to test it in Europe. In fact, Bohr is giving a talk at this conference where he brings de Broglie in with Schrodinger's wave mechanics that's being developed at the time. And in this context invokes Davison's old results, much to Davison's own surprise. Like, why are they talking about this old data and in this new context? And it gets him curious. And so he borrows, Davison that is, borrows Schrodinger's papers from somebody and spends the trip back to New York, again, I'm sure much to the pleasure of his wife, buried in the papers of Schrodinger and understanding what it is that the wave mechanics are saying. And it is on that point that he changes his experimental outlook and says, okay, let's really test this thing, right? And so he does this with Germer, and these are the results that supposedly change everyone's mind about duality. But whence the duality? So at the end of their famous paper in December 27, they write this is up there. Because of the similarities between the scattering of electrons by crystal and the scattering of waves by 3- and 2-dimensional gratings, a description of the occurrence and behavior of the electron diffraction beams in terms of the scattering of an equivalent wave radiation by the atoms of the crystal and its subsequent interference is not only possible, but most simple and natural. It is, of course, was not. I mean, clearly their lab was a bit of a disaster. I mean, they were exploding canisters and deoxidizing things and whatever, but okay. You write your papers in poetry and you do the experiments in prose. Okay. Interestingly, after winning the Nobel Prize and in writing popular talks about what he'd done, Davison describes what he'd done in the following way. He says things like this. There must, it would seem, be comprehensive modes of description applicable to all electron and X-ray phenomena. But what these are, we do not yet know. We do not yet know whether we shall eventually believe with de Broglie and Schrödinger that electrons and X-rays are waves that sometimes masquerade as particles, with Duane that, I don't know who Duane is, I should look that up. The electrons and X-rays are particles that sometimes masquerade as waves. Actually, we shall believe with Bohr that we're dealing in cases with actual particles and phantom waves. I believe, however, that for the present and for a long time to come, we shall, in describing experiments, worry but little about the ultimate realities and logical consistency. We will describe each phenomenon in whatever terms we find the most convenient. Which is another reason why we maybe don't talk about the experimentalists so much in the philosophy and history of quantum mechanics. But he's sort of shrugging, right, and saying, we don't know what these mean. I will conclude here by just putting, I told the story about Thomson, who in Aberdeen at the same time, but using an entirely different method, and by trying to prove the Royal correct from the outset, whereas for Davison it was kind of this realization that they could use the experiments they'd been doing for these pragmatic ends to also discover something about electrons. Thomson goes poetic in an even greater degree. I mean, so in the paper for which he's given the Nobel Prize, he says, we now leave the sure foothold of experiment for the dangerous but fascinating paths traced by the mathematicians among the quicksands of metaphysics. Okay. But in later letters and in popular writing, he tries to describe what the meaning of these phenomena are as follows. And this is, quite beautiful. The wind catches the filament and the spider is carried. I guess the spider is the electron, right? And it's it's the filament is the wave, right? Okay. I would like some Bohmians, by the way, to pick up on this beautiful analogy. Are you listening? Okay. So the wind catches the filaments and the spider is carried where the filaments take it. In much the same way, the point which represents the energy of the electron is guided by waves which surround it and extend possibly to an indefinite distance in all directions. If the waves pass over an obstacle, like an atom, their direction is modified, and the modification is transmitted back to the electron and affects its path. Thus, the waves act as an intelligence system to the electron and enable it to guide its path in accordance with the distribution of matter which it finds around it. Isn't that pretty? So, I hopefully have given you a bit more of a rich story about the experimental side. There's a lot more that could be said about the particular data that they found, and to go back and look, in fact, at what was it, even before we have these beautiful, the image I showed you from Schrödinger's popular lecture in Scientific American, where you can see the interference fringes of the electron waves, which happens in the 50s and later, and now we're doing, Hackermuller and others already in the early 2000s are doing decoherence on very large molecules. And so they're looking at matter waves and using decoherence models to understand interference effects there. But even the experimentalists themselves had very different interpretations of what the underlying reality meant. So thank you very much. My watch is still on New York time, so I think we have a lot of time for questions.
Yeah. Thank you for finishing on time. Anthony,
I rarely do. No questions. Oh, hi, Matt. I didn't see you. Oh, we okay, good.
Thank you. It's a fascinating topic. This whole period of physics. There's something that, I mean, as you mentioned, I wrote this book with Guido years ago, and in parts of it we looked at this, some of this stuff. And there's something that puzzles me. It still puzzles me. You could put it this way. Bohr in 1923 was the first person to predict electron interference and diffraction using a theory of particle trajectories guided by waves. This prediction was verified some years later. And yet, for the rest of the 20th century, this phenomenon was routinely cited as proof that you cannot have particle trajectories. Okay, which is just, it would be like, Einstein predicting the deflection of light by the sun in 1915. This is seen in 1919, and then the result gets quoted as evidence against Einstein's theory. Something went terribly wrong with the history. Now, at the time I wrote the book with Guido, it seemed to me that part of the problem was that most people had simply not really read de Broglie's papers or his thesis. They tended to lump de Broglie with Schrödinger while he thinks that electron can somehow act like a wave.
Right.
Just not really understanding that he had a detailed theory of trajectories guided by waves. Yeah. This somehow got lost. But still, it seems like a major mystery to me. How did this? I mean, the only answer we gave in our book is that, well, it seems that people just didn't really read the book, and that was it. But maybe, do you have any? Can you shed light on this?
You mean for why people understand Schrödinger's wave mechanics as like a fulfillment of de Broglie's work, even when it's quite separate motivation?
What I'm really asking is, how is it that de Broglie first predicted this phenomenon with a theory with particle trajectories, and then the phenomenon gets quoted by physicists for pretty much a century as evidence against trajectories? How on earth did that happen?
It's, Pache, the physicists in the room, they're not always the best historians. Even the figures in this history themselves are interpreting the data in different ways, right? So I guess I'm not that surprised that people have incorrectly understood it. I don't have a particular story to point you to, but I don't know. People make mistakes.
It seems like a lot of people made the same mistake over and over again for a whole century. I mean, it does sound to me, it looks to me like something that's crying out for a good historical explanation. But
yeah, well, I'll have to talk to the good historians I know. Yeah, it's surprising. It's surprising. I mean, you learn in textbooks, well, isn't it amazing that electrons have duality in the same way that photons do? But what the hell does that mean? And you can give an interpretation of these things where you recover the phenomena within one coherent picture, coherent to some, like Royal Bohm theory or something, right? But yeah, we haven't settled on any particular picture yet.
Yeah, again, thank you for this. You made it clear that the story is a lot more rich and interesting than the stories that come down to us. You had this quote in the previous slide from Davison. What year is that from?
The bottom one?
Yeah.
I believe it's still the 30s.
Oh, okay. I was struck by that for similar reasons to having to do with Anthony's talk, because he's determined to born this idea of actual particles guided by waves, and on the next slide you've got Thompson talking about particles guided by waves. Is it perhaps part of the story that more people were actually thinking about particles guiding the waves than the standard story tells us?
Yeah, and I think that's quite. I was very surprised to read that. I was like, where is he getting this from Bohr? So to be seen, but definitely not something I've seen answered well yet. I mean, Derrigal has a nice paper on aspects of this, but his focus is really more on quantization of electromagnetic waves. So it's a little bit different. But yeah, to be continued, right? Interesting.
A very nice talk. So a lot of discussion then about diffraction and interference and what does it all mean. No discussion at that stage about tunneling. Did that not come for another year or two?
Tunneling Hund is the first to theorize about tunneling in the early 30s.
Yeah.
And again, it's not surprising if you know that Hund had struggled with Ramsauer for so long, and he's thinking of and then he hears from Elsasser or whoever, he's like, matter can exhibit wave-like properties. It's then a very small step to say if we can have imaginary indices of refraction for light, then maybe there's something analogous that happens with matter waves, and boom, you have quantum tunneling. And in fact, yes, this is another part of the literature where Sponer is a contributor, and she gives a talk at a conference in is it Leiden or Leipzig? Which one was Debye at? Can't remember. Anyway, she gives a talk where Nernst and other chemists of renown are, and says that, this is 1933, clearly we can explain some of these chemical phenomena that we've been noticing in terms of quantum tunneling, and there's a bit of an uproar. She says, but Frank and I already said this in 1929 in the Göttingen report or something. So, sorry, not 1931. Okay, pretty early on. Okay, so it's the next step in the story, but we're not there yet in the experimental mid 1920s. Sorry, mid 1920s. It would take another few years before Hund would get to quantum tunneling. Yeah.
But there's a curious connection with Donald Trump, isn't there?
I hope not.
His uncle did some of the pioneering tunneling experiments.
Oh, at Bell Labs or elsewhere?
At MIT.
Oh, at MIT. Okay.
You didn't know this. It's good.
I didn't
dig into the literature.
Yeah, thank you very much. I'd like to ask you a question about de Broglie and his thesis.
I may not be the right person. You might ask Guido or Anthony sitting next to you, but go ahead anyway. I'll do my best.
I mean, the question is this. De Broglie, of course, was concerned with the fact that the phase waves that he introduced on relativistic grounds were superluminal. Their phase velocity was superluminal. So he solved the problem, if I remember correctly, by introducing wave groups.
Yes.
And showed that the group velocity was subluminal. The trouble is, how do you justify going from a monochromatic wave to a wave group? And it's, if I remember correctly in the thesis, this is done by simply saying, well, you don't know precisely what the wavelength is, and so you might introduce an uncertainty in the wavelength, and you use the range within that uncertainty to describe a wave group. But that makes the wave group look like something epistemological rather than ontological. And I think this was something of an incoherence in the thesis. Now, to what extent this was picked up by people, I'm not sure. I mean, if people weren't reading the thesis, well, then it wouldn't have made any difference. But if some, perhaps, of the early pioneers were looking carefully at the thesis, they might have spotted this. And maybe that's why his particle plus wave guidance picture might not have been universally accepted. I'm just throwing this out as a possibility.
I mean, I will defer to those who have more expertise on de Broglie's work. I didn't reread the thesis, just I reread secondary, so Guido and Anthony's book and Tony and Michel's books on this. It is a coherent framework, but I think primarily because he's not attributing reality to the waves. So if they're not real, then you don't get contradictions. So I don't know. Guido, Anthony, want to weigh in? I mean, if the picture is that the waves are not part of one's ontology, so to speak, but are guiding influences, then that picture of the world can coherently explain why you get for certain larger sized systems, right? For larger bodies, something that looks corpuscular. No?
Well, I'd like the experts to say something about the thesis.
Yeah, I'm not sure how the kind of these theses, from what I remember, I mean, this is going back 20 years, it wasn't completely clear what the Freud's position was ontologically about waves. Were they just formal, were they real, not really obvious?
Difficult to understand how they could be unreal if they give rise to diffraction interference effects.
Yeah, no, I mean, fair enough. But okay, I think, I mean, maybe in 1927, de Broglie is more explicit, but it's not really clear.
And this is part of the historical story that does need to be uncovered more carefully, right? I mean, I could be mistaken again, but I think part of Einstein's excitement about de Broglie is because it uses the waves, but in this as a calculational tool, right? So it's not, I don't know. They're not talking about it in terms of ontology and epistemology, right? I still don't know what it means to talk about a guiding wave, to be honest. So if you could help me with that, that'd be great.
There's some wonderful publicity shots of the Davison-Germer experiment. Clinton, Davison always holding the vacuum chamber, Lester Germer never allowed to hold it. And in one of the shots, he's standing next to a large waste bin for oily rags. So you get a sense of the chaotic nature of the laboratory. I was just wondering, because you gave this sense of the Davison-Germer experiments with Davison not really knowing what the experiments were about until talking to Bohr and coming to Oxford. What was his motivation for doing that series of experiments? I mean, what was he looking for?
Before the trip to Oxford.
Yeah, before the trip to Oxford.
Yeah, they were trying to look at crystal. Yeah, they were trying to look at the nature of the metals, the nickel plate, the platinum plate themselves, as far as I know.
But why? What was the motivation?
Oh, it was some technological thing. I can't remember. Yeah, building more efficient vacuum. I don't know. I don't remember. But it was they were racing to get patents for it. So I mean it was entirely industrial, I guess.
I just wanted to make the comment just in answer to Anthony's. Sorry, I just wanted to make the comment in answer to Anthony's question about why wave this sort of de Broglie bone picture wasn't orthodoxy. I mean, surely it was Niels Bohr's complementarity principle, I guess, in the late 20s, which said you can't think of them simultaneously. You either have to think of one or the other, and not both. And you know, the sort of Thompson quote here that the waves and the spider exist simultaneously is would not have been considered in that picture, not being considered the correct way to think about it. Isn't that how the community developed along Bohr's?
The story, right? But I mean, Christian Camilleri has a nice paper from, I guess, almost 15 years ago now, where he's saying that even how Heisenberg understood complementarity in wave-particle duality when it gets to matter is not the same as Bohr. So I don't think it's as clean a story as we've been told. Maybe Diana knows more about it.
Yeah, can I put a finger on this? Yeah, so I think that part of this story is maybe the fact that, well, what is behind Schrodinger's derivation of the wave equation is that, well, he came to learn about de Broglie's work, and then he gave a talk about it, and then the guy suggested, well, if there are waves, then there should be a wave equation, right? And then Schrodinger found this wave equation, and then he tried to show that with them you can mimic particle trajectories, but the waves don't stay together, right? And then that is what allowed then people like Born to say, and the others from the Copenhagen Göttingen group to say, well, there are really particles, and the waves just are probability waves guiding the particles. I think that maybe this is related to the story.
On that point, what one could ask Schrodinger looked there is, why did he drop the trajectory? Why did he break it? He looked at the full wave because he did wave equation to the wave, but he dropped the trajectory.
Yeah.
Why? Seemed like the other people didn't really notice that in the Broglie species there were also trajectories. But that's how the Broglie ended up getting lost in Schrodinger.
Right.
Yeah, but the Schrodinger does say exclusively that he rejects this duality in the Broglie's work, right? For him, the ontology is purely wavy. Yeah.
Could we direct question via the chair, please? Sorry.
Yes, thanks. Elise, I have a historical question that is about the experiments that were being done during the same era of the 1920s. And the extent to which the conversations you've been discussing intersected with the conversations about spin, right? Gauss-Mitten, Uhlenbeck is what, 25, 26? And were these experimental communities talking to each other? They're all shooting electrons at different things, and you think that they might be discussing these things. And it turned out to be a pretty complicated and related factor in the whole physics.
So I can't point to specific data, but yes, they're going to conferences, they're talking to each other, they're sending students back and forth. But I mean, even on the points about spin, I mean, Stern and Gerlach in a sent a postcard with the image of the magnetic field turned off and the magnetic field turned on to Bohr and said, we've confirmed the theory. But of course they haven't, right? That's not what the Stern and Gerlach apparatus shows. So yeah, I mean, part of the methodology of digging back into this history is just that by bringing the experimentalists themselves, not just the experiments, back with more richness in the history, we will recover some of these interactions, some of these stories, and understand the conceptual trajectory of some of these questions more clearly. So I can't give you a definitive answer, but it's a question worth finding an answer to.
I think it's about time for our coffee break.
Yeah.
We will convene in half an hour, quarter to 12. So that's about it.
Thank you.
worth reminding people that the point of the microphone isn't just so they can be heard, it's so they can be recorded and transmitted.
I could definitely do that.
Do you want me to get started in order to people are sort of trickling in? How time? Are we happy to start 5 minutes late?
Start 3 minutes.
3 minutes. Okay, 3 minutes. In 1 minute. All right. Excellent. Oh, I'm so sorry. Just realised I couldn't make this morning work and be in Oxford for 9. I just. All right. I'm going to start talking to encourage everyone to sit down so we don't run too late. I've been asked by our illustrious organizer to remind everyone that the reason we have microphones is not just because your voices are very quiet, but because it's being recorded. So in the Q&A, if we could actually wait for microphones, otherwise the recording doesn't work. That'd be wonderful. And with that small point out of the way, I'd like to introduce Guido Bacigalupi, who is winning extra points for a rhyming title, which I really like. Guido.
Thanks, Eleanor. And I'm delighted to be here in Oxford with this weather, and delighted to be one of the first speakers, so then I can relax and enjoy. Thanks, Chris. So, going to talk about Niels Bohr. We've got a big project on Bohr running currently in Utrecht, and title is supposed to be a bit provocative. And this is the sort of about Bohr's journey and so on. Bohr is reputed to be obscure, and many of you will know this. There's this sort of running joke that when Wheeler and Zurich edited their volume about quantum theory measurement. They actually mixed up two pages of Bohr's reply to EPR, but it didn't matter, because many people, before me, for decades, have been actually pushing back against this narrative of Bohr being obscure. Don Howard, famously, a lovely PhD thesis by Ellen Katz, which is not very well known. And I've basically plagiarized the title of Catherine Chevalet's paper. And the idea is, she said, I wish to show that the basic reason why we find Bohr obscure lies in the reconstruction and distortion of his original line of thought. Basically, the joke is on us. We find Bohr obscure because we come with false expectations. We think that Bohr is the exponent of the so-called Copenhagen interpretation, which, however, some kind of jumble of ideas, taken from various people, put together maybe by Heisenberg or whatever. And also, particular difficulty for philosophers, we try and pigeonhole him, into sort of existing philosophical positions or philosophical debates, positivist, Kantian, the realism, anti-realism debate, and none of that is particularly helpful. And then sometimes he uses, strange terminology, like the fact that, the quantum of action is, the irrational element, in quantum physics, and that we think, that actually, comes directly from Emile Meyerson, who's got this idea that, we come with sort of rational expectations, but, nature doesn't always cooperate, and so there's an irrational element, when we do science, and so there are some peculiarities, in Bohr's language, which knowing the context, can be understood better. But what I want to focus on, and it's us. You recognize, my people in the audience, and there's other people who are doing some splendid work, trying to really find the right way to understand what Bohr is saying, also in the right context. Well, what I want to focus on today is something that's sort of very crucial, and something that I'm following in the steps of Don Howard, the Bohr's use of classical concepts. Well, not just Don, Schrödinger already was pointing out that this looks like a really crucial thing that we ought to understand in order to understand what Bohr thinks. I'm quoting Schrödinger here. Keep expressing in the most definite terms the conviction that measurements must be described through classical concepts. Also here, he's commenting on a sort of draft of the Bohr's reply to EPR. You speak again of the indispensable use of classical concepts in the interpretation of all measurement. It must be very definite, clear reasons that prompt you to repeatedly assert that one must interpret observations classically, that it is utterly part of their essence. It must be part of your own most firm beliefs, and I cannot understand what it is based on. You see a lovely book by Elise and myself on the EPR debate, which just came out, plug. Now, this is what Bohr replies to Schrödinger, which maybe the first time you read it is a bit frustrating, might have been frustrating to Schrödinger. I must confess that I cannot share your misgivings. My emphasis on the unavoidableness of the classical description of experiments in the end just reduces to the apparently self-evident fact that the description of every measurement setup must essentially contain the arrangement of the apparatus in space and its functioning in time if we are to be able to say anything at all about the phenomena. The argument is in fact primarily that the measuring devices, if they are to serve as such, cannot be included in the proper domain of application of quantum mechanics. Now, I won't try to attempt to answer Schrödinger's question of why Bohr insists that one must use classical concepts, and just focus on how actually is it that Bohr uses classical concepts. I mean, we've got a sort of working hypothesis for why. Here's Abraham Heiss, writing that the correspondence principle is, I think, Bohr's greatest contribution to physics after his derivation of the Balmer formula. His first manifestation of what would remain the leading theme in his work, classical physics, though limited in scope, is indispensable for the understanding of quantum physics. So here Heiss is starting from the idea that classical concepts are essential to sort of talk about the correspondence principle. So, if we read him backwards, really, the use of classical concepts, starts with, the correspondence considerations in 1918, maybe back in 1913 even, and my postdoc Janis doing some great work on that stuff, and that was Bohr's strategy in trying to construct quantum theory, and it was a very successful strategy, and everything else had failed him, and that's our working hypothesis, that this just was the way ahead, and we should stick to it. Okay, so how is how is Bohr supposed to be using classical concepts? And so this is not how he actually uses them. This is the kind of sort of standard, Mickey Mouse version, of how we sort of present it in textbooks. Well, classical concepts, those are indispensable, because there's some kind of fundamental division between sort of quantum realm, classical realm, and the fact that the apparatus is classical, must be described classically, whatever, enforces the collapse of the wave function. There's going to be this sort of stochastic transition of the quantum state, which essentially disturbs the system every time we make a measurement, even so-called ideal measurement, as a sort of very, very dramatic, intervention in the system. Now, and by the way, that's a kind of intuition that modern measurement theory is sort of based on. If we think that whatever by letting an apparatus interact with the system, we are inducing a collapse. We're inducing transformations of the states. Maybe we can sort of generalize, the notion of ideal measurements. Let's break things down into sort of quantum interaction, between the system and the apparatus, and then, a collapse onto the sort of point observable. Then, if we generalize the interaction between the system and the apparatus, we get a nice generalization of the notion of measurement. We introduce POVMs and so on. I'm not sure any of this, fits what Bohr's actual work. So, he's saying somehow that it is of the essence, of a measurement, that we use classical concepts, in particular how the apparatus is arranged, spatiotemporal, how it functions in time, how it operates, how it interacts with the system. It is of the essence, of a measurement. It is to serve as such. If it is to give us, information about what's happening with the system, that we be able to analyze its functioning in classical terms. There we've got a quantum interaction, there totally untransparent and mysterious how the thing functions. That's not what Bohr is actually saying. Now, there's a straightforward way in which we can think of measuring devices, as serving their purpose, if we are not describing them quantum mechanically. We assume some unknown value of unobservable for the system, and we design, the apparatus to interact in a way that, through analysis of how it interacts with the system, we can then sort of infer back from the reading of the device to some property of interest of our system, and ideally not even disturbing the system. That's sort of the straightforward, naive way we think about measurements when we are not doing quantum mechanics. Now, let's go a little bit more formal. Bohr never wrote down a measurement theory. Pauli did, in his famous handbook article of 1933. and we actually find, this kind of phrasing, in Pauli. So what Pauli does is, what we think we know and love from modern measurement theory. Takes a system, takes an apparatus, couples them quantum mechanically, and in fact, initially he allows arbitrary, unitary coupling between the two. So he could be developing measurement theory as we know and love it in full generality. Then he says that we must restrict the allowable interactions. And the way he describes it is that only those interactions will count as measurements that allow unambiguous retrodiction to a value of the measured observable. And he generalizes this sort of ideal case to allowing also for measurements in fact disturbing the state. We can unambiguously retrodict the initial value, but maybe we don't leave the system in an eigenstate of our measured observable. So formally, we get what he does is slightly more general than this, but never mind. Formally, he gets these two kinds of interactions corresponding to measurements of the first and second kind. And essentially, what this restriction amounts to is these are in fact interactions which where the quantum description of the interaction is a sort of superposition of an entire process of this kind. We've got an initial of the system, which then gets mirrored in the final state of the apparatus. And we've got this superposition. So that's the sort of quantum mechanical description of an interaction. But let's focus on this last bit. I mean, what I'm suggesting is that we should take Bohr and Pauli at face value when they talk about analyzing the interaction in such a way that it allows us to unambiguously retrodict something about the phenomena themselves. These final states could be read backwards in time, as states that must have evolved from some originally unknown state there. Okay, right? We might need to let this sink in, but instead of just thinking abstractly about it, let's just look for this in concrete examples. So, and let's start with something that's very familiar to most in this audience. There's some suspended slits that Bohr discusses in his reply to EPR. The setup is we know the initial momentum of the particle and of the slit in the vertical direction. That's conserved. So when the particle and slit interact, its total momentum remains the same. If the particle gets through to the other side, then we also know that the position of the particle is perfectly correlated with the position of the slit. The difference in positions is 0. So the total state is one of sharp total momentum and sharp difference in position. It's an EPR state. Then after the interaction, we've got the choice of measuring either the position or the momentum of the slit. And that allows us to compare to use EPR's phrase, predict with probability equal to unity, what the position or the momentum of the particle will be if we go and check that. Now, how does Bohr describe this in well, he actually says, in the first case in which we measure the position of the he says, oh yeah, applying the picture of spatio-temporal coordination. He is saying that the particle has passed through the slit at a certain spatial and temporal location. And so measuring the position of the slit, in fact, reveals what the position of the particle is. And that's a nice classical analysis that we apply in this case. Now, in the second case, in which we measure the momentum, he says we can apply the picture of momentum conservation. And he talks in terms of the particle and the slit exchanging a definite amount of momentum. We measure the momentum, final momentum of the slit, and therefore we can infer that exchange was and infer what the momentum of the particle is. And in neither case is there any mechanical disturbance of the particle. The particle and the slit have already interacted, and then we manipulate just a slit. We're just revealing something about the particle. This is the language that he uses. Here's another example, which is somewhat less familiar, but also very, very explicit. It's less familiar because it's history that's been largely erased from the history books. Because this is Einstein being conned by Emil Rupert, who later on was exposed as the biggest fraud in the history of experimental physics. For 10 years he had been making up all of his results. He had this enormous reputation at the time for being a wizard, doing experiments with canal rays, all fabricated. And so Einstein, because of these results that Rupert allegedly got, was very interested in getting on board, for experiments which would probe certain aspects of the sort of particle versus wave nature of light. So Einstein had in mind so that's sort of the thought experiment version. You've got an atom that's moving and emits a photon while it's moving behind a slit. So that gives us a sort of small window for the emission of the photon. So, for instance, the experiment was then supposedly done with sort of hog wheel moving to sort of limit the limited time of emission. Anyway, originally Einstein was expecting that experiment would give a sort of particulate answer. He thought he was associating this idea of, well, if a photon is emitted, we are going to have sort of this sort of instantaneous process, and a photon of a definite frequency is going to be emitted. But then he changed his mind, and partly through analysis of a previous experiment by Rupp, but then he provided sort of an independent sort of theoretical argument that led him to expect that in fact a wave-like prediction, would be confirmed. That the small time window of emission, would lead to a spectrum of frequencies, when you then detected the photons, and lo and behold, we've got that result. Now, did I? Oh yeah, yeah. Didn't mention the letter yet. So, when Bohr, first wrote to Einstein, telling him about, Heisenberg's results on uncertainty, the way he presents Heisenberg's work is in the context of Einstein's worries, about, essentially, this sort of energy time uncertainty, about, Einstein's worries, about in connection with, the nature of light, with his in his collaboration with Rupp. So, the Einstein's theoretical considerations and the alleged results of the experiments showed that the wave picture of light was applicable. Small window emission, gives rise to a sort of spectrum of frequencies that we're going to measure. So, Bohr says, well, now what Heisenberg is showing us formally, is in fact that we can also apply the particle picture. If we do so, we can think of the process as one in which the atom might be sort of undergoing some radiative recoil, and that is going to explain why we get a spread in frequencies. So we can reconcile the spread in frequencies at the statistical level with exact conservation of energy at the individual level. And well, if you read that, Bohr is clearly thinking that even though we're making a sort of measurement of the frequency of the photon over here, we can explain the result of that in terms of specific exchange of energy between the atom and the photon during the process of emission. So that's very, very explicit, and this measurement is just a sort of revealing. If you apply that, then you can analyze the measurement as a sort of revealing, what went on in the interaction as described, using the particle picture. Here's okay, and this is sort of less direct. I'm not talking about Bohr directly. I'm talking about Grete Hermann, but also very, very explicit. Grete Hermann, one of my big heroes. He had a lovely book that I wrote with Elise. Implicitly attributes this view to Bohr. He says that according to Bohr, we ascribe quantum states to systems always relative to a so-called context of observation. By the way, if you read Max Jammer's book, he says the same. In fact, he treats Bohr and Hermann together, in the same chapter under the heading of relative nature of the quantum state. So we don't just, in fact, that was something that Hermann sort of came to realize. I mean, originally, like all of us, she thought originally that quantum states sort of pertain to quantum systems in some sort of intrinsic way, and that somehow they collapse during measurement. And she thought, well, if that's what happens, we should be able to ask for the reasons for a specific collapse, rather than something else. That was when he was criticizing quantum mechanics, the claims that one can prove that quantum mechanics was complete. How could you, if you've got these processes, surely you can ask the question, whether there are some additional quantities that we haven't taken into account, that explains the particular collapse that you have. And she realized, after Weizsäcker had told her about his version of the gamma ray microscope, in which depending on the context, depending on how you use it, you can prepare eigenstator position or eigenstator momentum of the electron. He realized, or she had this insight, that in fact quantum states do not pertain to quantum systems that are intrinsically absolutely, but that quantum mechanics gives different physical descriptions in terms of different quantum states, depending on different contexts of measurement. So we've got these different descriptions, which are applicable and well, depending on what the physical situation is, but for instance, when we are sort of changing from a context in which we have sort of originally prepared a system to a context, that where we are sort of now doing another measurement, that what looks like a collapse of the state, is just a change of description, because in the new context, we are going to need to use new quantum states, because that's how quantum mechanics describes system relative to the context that we've now set up. So collapse is not a physical process. It's a change of description. We had prepared our system in a certain quantum state, and if we stick to that description, then we see how it gets entangled with the apparatus and so on. Now we are interested in different description, one that allowed by the physical setup that we've realized, and in that physical setup, we are going to assign a certain eigenstate of the observable interest to the system. We don't know which one it is. It's in retrospect that we find out from the result of the measurement which one that was, but we are going to describe the system and the interaction in a sort of quasi-classical way. We've got this unknown state, and the system interacts with the apparatus in a certain way that is transparent. We've got these, for instance, the picture of spatial-temporal coordination, or the picture of conservation of momentum that we can use, drawing upon sort of classical ideas. So that's the picture, and she explicitly attributes this. So, for instance, in the Einstein group example, if say we're measuring the narrow window of emission, And the description that we give in that context is the superposition of different frequencies. Well, we could stick to that if we want, but it makes sense if we are in fact measuring the frequency that we switch perspectives. We switch to a perspective in which we're going to assign a particular frequency to the photon. We don't know yet. Sure. But in that text, then we tell the story of a particular radiative recoil and so on. The story that Bohr is telling. By the way, we don't need to worry about fixing the system retrocausally. It's not that. We choose to measure the frequency, so we change retrocausally the state of the system. Collapse is not a physical process. We are just choosing later on to adopt a description of this interaction, which well, is an interaction that has happened already, but we've got some good reasons why we might want to describe it one way rather than the other. And that change between descriptions is not a physical process, so we don't need to worry about affecting things in the. And in the case of a suspended slit or EPR, okay, there we've got sort of three contexts. The original context in which we prepare the EPR state, and then we've got two alternative contexts that we might set up. Now, we are free to set up one or the other, and one of them is going to exclude the other. Switch from the initial one to the final one. That's still not a physical process, and if we do so, then we tell this particular story or that particular story about the interaction between the particle and the slit, and our choice does not affect the particle at a distance. There is no distance collapse. Collapse is not a physical process, and indeed Hermann complains against those who think that a wave function is an objective description of a physical system, because then collapse would be an objective physical process, and in general it will be superluminal. He's one of the few people who really understood the EPR argument at the time. And by the way, note the similarity of Hermann's account with what Don Howard proposed already a long time ago. He talks about he's analyzing the use of classical concepts in Bohr's reply to EPR, and he says, Bohr is substituting appropriate mixtures for the entangled state of system and apparatus. Well, that's what Hermann says Bohr is doing. Instead of using we are switching from using the entangled state to using one of these product states, but we don't know which. So we are switching to using a mixture, and that's just a change of description allowed by the context that we have set up. So I'm endorsing Don's views here. Now, I hope to have made at least a prima facie case that this is actually what Bohr is thinking, and that actually it's staring at us in. Why don't we usually see it? And, here is a possible answer, we are very much conditioned by the sort of usual analysis of the Bohr-Einstein debate. I mean, take photon emission. In fact, let's take it in the case of in the much more familiar case of the photon box rather than Einstein Hertha. If Bohr says that a measurement of the frequency of the photon, in fact, can be understood in terms of particular mechanism of radiative recoil or whatever. That means that the photon already had a definite energy at the time of emission. Isn't that just conceding Einstein's point that quantum mechanics is incomplete? Bohr can't be meaning that, can he? Or, in the case of a suspended slit, to admit that, if we measure the position of the slit, that tells us what the position of the particle was when the particle passed through the slit. Well, that measuring the momentum of the slit tells us what the momentum of the particle was, when the particle and slit exchange momentum. Isn't that conceding Einstein's point? That the particle must have elements of reality corresponding to. Bohr can't really be meaning that when he says it. That conclusion too. I mean, the conclusion that Einstein, Podolsky, and Rosen draw, from these considerations, follows only if we admit Einstein's separation principle. That although wave functions, can vary according to sort of the context of measurement, the real state of the system can't. The real state of the system can't depend, it is intrinsic to that system, can't be defined with reference to something else, and can't be changed by stuff we do elsewhere. But Bohr rejects the separation principle, and he precisely rejects the separation principle by insisting that these wave functions, these states that we ascribe to the system, are in fact the real states of the system. So, they're defined only contextually, relative to a context of observation, and that's why this is a radical revision of our attitude to the problem of physical reality. Physical reality is not something absolute. States of systems, real states, pertain to systems intrinsically. No, the real state of systems are contextual, are relational in a sense, and that's what Bohr is, and that's why he blocks that's how he blocks the EP argument. And in fact, that's really important to Bohr, because that's the solution to the problems that he and Einstein have been struggling with for years. Or how these different descriptions might be combined. How do you combine exact conservation of energy, with the superposition principle? While Einstein is prepared to say, well, the quantum mechanical description is incomplete, we should look for elements of reality, which are clearly not just the wave functions. Wave functions are not the real states of the system. Bohr instead, has been using, these classical ideas as a guide to understand what's happening in the quantum realm, but until now he couldn't quite fathom, how to combine, these contradictory things that seem to come out of the experiments, and then he has this idea of complementarity, and this is how he ties it in with Heisenberg's uncertainty, in that same letter to Einstein, the new formulation, Heisenberg's uncertainty. Through the new formulation, we are presented with the possibility of bringing the requirement of energy conservation into harmony with the consequences of the wave theory of light. Since according to the character of the description, here's complementarity. The different aspects of the problem never occur at the same time. We've got different contexts of description. In this context, we're giving one story. In this context, we're giving another story. That's how we can combine the two, because neither of them is an absolute description of the system. They apply in different kinds of descriptions. They are different kinds of descriptions that apply in different contexts. One could go on, exploring this story further. I mean, the way that Heisenberg's uncertainty relations fit into it, is by illustrating how, in fact, the limits of observation coincide with the limits of definability of these concepts, and a couple of years later, development of QFT, lots of problems. Bohr sort of revisits these ideas, and with Rosenfeld, he analyzes the measurability of quantum fields to try and see if also in quantum field theory, the limits of observation coincide with the limits of definition, or if we need to sort of rethink how things work. Maybe the ideas that we're applying in atomic theory need to be revised completely when we go to quantum field theory, but he convinces himself that no, actually it still works. Sort of Bohr Rosenfeld stuff, that's something I want to have a look in detail with my other postdoc, Stefano, over there. So this is all work in progress, but I think what I'm telling you now is already pretty solid. And by the way, this is Pauli, writing to Schrödinger, commenting on EPR. And this was a passage that Elise and I found a bit cryptic, but I think it makes sense to me now. In changing the state of A, that which is predictable of A, lies within the free choice of the experimenter. He's talking about the EPR case, even without directly disturbing A itself. And then he says, this circumstance required by quantum mechanics appears to me indispensable in order to avoid contradictions if the conservation laws as well as the superposition principle are valid. I think this sort of mirrors Bohr's phrase here, bringing the requirement of energy conservation into harmony with the consequences of the wave theory, superposition. And of course, this is precisely the difference as compared to the classical concept of state. Classical concept of state is something that's sort of intrinsic to physical systems. The quantum concept of state is something that's contextual. So, I'm not necessarily a Bohrian. I may have come across as an enthusiastic supporter. Actually, I don't think that Bohr's views do really apply or are quite satisfactory. Fact that we now have POVMs that we know and love. We consider more general experiments than what Bohr and Pauli considered to be allowable measurements. I think if we want to tell a Bohrian story about these more general experiments, these nice stories fail. There isn't a nice story you can tell in terms of classical concepts, about transformations described by arbitrary, completely positive operators. So I think there are, some, significant limits, to the applicability of these views. My main point is, actually, if you look fully at what Bohr is actually saying, it makes sense. Thank you very much.
Can you hear me? Okay. I have 3 points to make. One has to do with retrodiction, one has to do with the concept of a state, and the third has to do with in what sense is observation provide a context. Retrodiction, I was a little puzzled by what you said there. If you think a state is assigned to a system relationally, as you're inclined to think Bohr did, and I do, then you also agree with Pauli that when you talk about the state of A, i.e. that which is predictable of A, then how does retrodiction come into it? Because when you're reassigning a state subsequent to a measurement, that state is itself something which refers to predictions. It's nothing to do with what happened in the past. So the issue of retrodiction never arises because you're not retrodicting to the previous state on the basis of your observation. You're only assigning the new state relative to the newly instituted concept of observation. So retrodiction is just irrelevant if that's right. Shall I continue or stop there and continue with that second part of the question?
As you please. I can reply to that. But retrodiction is explanatory. You observe the result of the measurement, and that explains. And you retrodict. You tell retrodiction, the story about what happened in the interaction, and that's explanatory for, why you got that measurement result. And not only, if you think of sort of EPR cases, you can then use that same story to do other predictions. You can now make a measurement on the distant particle, and that story that you've reconstructed, after doing this measurement, allows you to predict now what will happen if you do a measurement on the other particle.
Thank you. That's very helpful. I think it's rather a hokey explanation that you're offering in the first case. But the EPR example gives me further food for thought. Let's move on to the context of observation. Thank you. Let's move on to the context of observation. Bohr feels very comfortable talking about observation because he thinks everybody knows what he's talking about. But people who have scruples don't know what he's talking about. I have a view of making more precise the notion of observation. What do you think about that? And do you think that Bohr is bothered by his scruples about what constitutes an observation, or does he just think everybody knows what that is?
First of all, as I said, Bohr might talk about observation, measuring devices, measuring measurement agencies. But he doesn't talk about observers. It's not important that somebody actually uses this setup for measurements. It's just we just have some physical conditions that could in principle be used for unambiguously predicting some value of an observable. So you can, I mean, if you want, you can think of that in analogy to quasi-classicality criteria, in consistent histories, or think of Everett. Everett has got relative states all over the place, but he's particularly interested only in those relative states that appear in connection with memory registers of certain servo mechanisms, which are sort of abstract models for observers. So you can think of these conditions defining measurements, which Pauli spells out formally as and they may need to be supplemented with something more. I mean, Hermann is maybe more explicit about the fact that the quantum description must allow for description in terms of quasi-classical states. So there must be some notion of quasi-classicality, which is not quite spelled out. And Bohr does talk in sort of vague terms about amplification, practical irreversibility, and so on. So I guess there are some further details to be fleshed out there. But I think sort of the general picture is fairly clear. Does that help?
Thank you. And so the great Steven Weinberg, in his last writing on quantum mechanics, said, "I'm not so happy as I once was." He said, when experts disagree with one another, that's a bad sign. So, so Guido, I also think the Bohr was perfectly clear, but unfortunately, I don't know that we can be correct about that. So may I just try to really push what I think is the thing I think Bohr was clear about, but you seem to be disagreeing, namely that there is no quantum reality other than what is set by a context. And that indeed, if you look at retrodiction, by the choice of present context, you thereby the reality that pre-existed is thereby determined insofar as it can be determined at all. And so this does seem to be retrocausal. In EPR, it does seem to be definition at a distance, as it were, of what the remote system is. Sure, there's no quantum reality independent of context, but by choice of context, I change what the reality is at a distance. I think Bohr was committed to this. But you seem to think, no, it's merely revealing something that pre-existed. But that notion of pre-existing, some pre-existing entity that has both position and momentum, that is what Bohr rejects. So there is no such entity. But still, he's a realist. There is an entity, but it's one whose properties are constrained by context, and specifically by making a local choice of apparatus, I change what is possible to say about the remote system and thereby what that remote system is. So I don't see a way around this, but you seem to. So please clarify.
Good question. well, again, I don't see that as something causal. I do see it, and maybe we can agree on that, as something constitutive, of what that reality is. But I'm not sure that we can apply causal talk in that way. So causal, and maybe I'm following Herman too much here. Causal talk is in the description of what happens in these contexts, but and of course there's causal talk in the sense that if I set up a measurement in such a way that's causal, and that's part of the physics, and that's but yeah, the fact that that causal analysis of how I'm setting up the measurement then sets the conditions for the applicability of a particular description rather than a different one, which extends temporally also to some previous interaction and so on. I don't necessarily see that as causal.
Yes, was that perfectly clear? Yes, thank you very much. I found that a really illuminating talk. I've been one of those who thought that Bohr was unintelligible, and I've actually changed my mind. Just one quick question. It occurred to me, listening to the talk, that it might be interesting to think of this in Wittgensteinian terms. So you could identify something you might call a classical language game, which involves us saying that particles have positions and momenta, and then making deductions from that and so on. And what Bohr perhaps is saying is that you keep the basic sentences in the language game, so you can still say things like particle A has position X, but you change the rules of the game, certain of the rules. So there are certain things you're not allowed to say, such as, for instance, particle A must have had both position and momentum before the measurement. And I'm just wondering if you'd agree with that.
Well, I need to think that through, but well, let me just say that it may, I mean, it may be a little anachronistic, or we shouldn't attribute that to Bohr as from a historical point of view. Ove Peterson, did think that Bohr's thought had a lot to do with language. So maybe something in the vicinity of that might be appropriate. But again, I'm not entirely sure that that isn't Peterson sort of imposing his own what he likes about philosophy of language onto Bohr. But certainly sort of maybe insightful for our way of relating to Bohr to think in those terms.
Sorry that we have there, but you can obviously during the lunch break. We're back here at 2:15.
Good afternoon, everyone. I hope you had an enjoyable lunch. We're ready to get started with our 2 afternoon sessions. Yes, we are ready to get started with our 2 afternoon sessions. And so the first one, I'm delighted that we have Eric Cavalcanti, who will be telling us about locality, causality, and all that. Eric, please take it away.
Thank you. Thanks, Sam, and thanks, Chris, for the invitation to speak here in this very special occasion with a fantastic group of people. I was given an assignment to talk about a little bit of the history of the EPR paradox, Bell's theorems, and related concepts. Now, this will be very shallow on the history itself compared to some of the talks so far. I'm mainly aiming to present a kind of a conceptual synthesis of these theorems and also of some more recent results and how it connects to those earlier results. Much of this will be based on some papers with Howard Wiseman, which I then cite now, and I will cite other sources as we go along. So Bell's theorem has been called the most profound discovery of science. If there's anyone listening online who has never heard of Bell's theorem, I'm sure in the audience that would be incredible. It has led to the Nobel Prize in 2022, not only for its foundational implications, but because the generation and the manipulation of entanglement that was developed as a result of attempting to violate Bell inequalities was instrumental in pioneering quantum information science. And regardless of whether, it's very widely agreed that it's profound enough to be, to deserve a Nobel Prize, but surprisingly, there's too wide disagreement about what it means and what the implications of violations of Bell inequalities are. So one example was in the commemorative issue of 50 years of Bell's theorem, which is already 10 years old, but I think some of these views are still widespread. And I'm using here Reinhard, Werner, and team modeling as the archetypal operationalist and realist based on their contribution to the issue, although they might have changed their views slightly since then, but nevertheless, they are my scapegoats for this talk. So paraphrasing what they said, Werner said, Bell's theorem has 2 assumptions. The first is locality. Quantum mechanics respects this. The second is something else, which I call classicality, but which is also called determinism or realism. Clearly, it is this that we should abandon. Locality is here to stay. Whereas team modeling would say something like, Bell's theorem is only one assumption, locality, or local causality, as Bell sometimes called it. Standard quantum mechanics is non-local. Bell's theorem proves that the world itself is non-local. So let me just first have a show of hands here of who of you sympathizes with the operationalist, the archetypal operationalist here? Any? Okay. And what about the realist version? About neither of them? And both? Yeah, it's interesting that there's some to both. At first, you would think that it's hard to really, well, you might sympathize, but maybe not agree with both, because they seem to be just outright saying contradictory things. And so part of the purpose of the talk is to try to find a conciliation between these different positions. And towards the end, I'll find a reformulation. I'll present a reformulation of Bell's theorem in which at least the 2 camps can agree on the terms and just disagree on what it is that they are rejecting as a result. And the source of this disagreement, although this is not entirely appreciated, is that there are in fact 2 Bell's theorems. And I don't mean just also the Bell-Cote-Specker theorem, which is about contextuality, and that will probably be mentioned in the next talk. I mean really 2 versions of the theorem that's best known as Bell's theorem. one in 1964 and one in 1976, choose different assumptions, and which is the source of some of these disagreements, at least. So let's go back and see what did Bell prove in 1964. So from the conclusion of the paper, he said, in a theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. So in other words, he showed that quantum correlations violate the joint assumptions of predetermination of measurement results and locality, in this sense, meaning that the result of a measurement on one system is unaffected by the setting of a measurement device on a distant system. On the other hand, in 1976, Bell fully developed his notion of local causality, which is that events in one lab should not be causes of events in a space-like separated lab and vice versa. This does not mean that the two sets of events should be uncorrelated, but they could have common causes in the overlap in the backward-like terms. A consequence of local causality is that the outcomes in the two labs having no statistical dependence on one another, nor on the settings of the remote measurement, and here is a key distinction, but only on the local measurement settings and on the common past causes. And so he concludes that quantum mechanics gives certain correlations which cannot be reproduced by a locally causal theory. So let's look in more detail into how these theorems are proved. And in doing this, we'll be engaging in this field that I like to call, calling Abner-Shimony, experimental metaphysics, which in the sense I like to use the term, I mean the field that studies physical theories themselves using the methods of both physics and philosophy, and importantly here, also engaging in philosophical questions. And so we start by describing an operational theory. An operational theory describes physical experiments in terms of laboratory devices like preparations, transformations, and measurements. And what I mean by a phenomenon is just a repeatable instance or a repeatable experiment that can be characterized by the relative frequencies of the outcomes of these measurements, given some choices of preparations and transformations. So here, I don't mean to imply any philosophical adherence to frequentism, just that what we observe in the lab are relative frequencies. We can also further distinguish between some variables which we identify as being settings, which are choices of preparations and transformations and measurements, which in the lab would correspond to directions of magnetic fields or orientations of polarizers, and the outcomes, which are things like the clicks on the detectors, which are the things that we're trying to predict. So, but these are all operational variables or observables in a broad sense. An ontological model, on the other hand, presupposes that there might be some further variables, which we call the ontic states, or that they'll use the term geables for, which may or may not be observable, but are the things which are really real. And an ontological model attempts to explain phenomena in terms of these beables. So Bell said the beables must include the settings of switches and knobs on experimental equipment. Observables must be made somehow out of beables. We'll be particularly concerned with local beables, those which, unlike, for example, the total energy, can be assigned to some bounded space-time region. So we can summarize these ideas as two background assumptions that are necessary for these theorems. One, the absoluteness of observed events, that any observed events, such as the settings of switches and knobs of experimental equipment, is an absolute single physical event, which is part of the concept of a beable, and furthermore, that they can be localized in space-time to be a local beable. So every event can be located in a single relativistic space-time, where we can talk about light cones and so on. So then an ontological model or a theory tries to explain the phenomena in terms of potentially some further ontic variables, such that we recover the phenomenon by some appropriate marginalization of a distribution that's postulated by the theory over all of these variables. And at this stage, I'm making no particular assumption on the properties that these distributions may have. Okay, so Bell's theory in particular is concerned with a phenomenon in this kind of scenario where we have some preparation device that is controlled by some variable C, which prepares two systems that are sent to two distant labs where they are measured with a choice of setting X with an outcome A on one arm of the experiment and a choice of setting Y and outcome B in the other side of the experiment. And a model may also include a description of ontic states or beables in the overlap of the light cones of this experiment. The beables may be associated independently to the two systems, but we'll just denote by lambda the pair of such beables for simplicity. And then Bell's 1964 theorem, the assumption of locality, or sometimes called parameter independence, just implies that the probabilities postulated by the model are such that the outcomes in one side of the experiment are independent of the setting on the distant arm of the experiment once we are conditioning already on, even if we are conditioning already on the beables. The assumption of predetermination is that these probabilities postulated by the model are deterministic, they're 0 or 1. And implicitly, Bell used an assumption of freedom of choice, and that we also call no superdeterminism, that the distributions of the beables is independent of the choices of setting. And here I'm not describing these concepts in words because they get a little bit convoluted and not very helpful, but I will do so with other concepts later. The Bell 1964 theorem then shows that there exists quantum phenomena for which there is no model satisfying these three assumptions simultaneously. And here, in this diagram, I'm representing the implication of these three concepts. These three concepts imply Bell inequalities, and being grayed out here, indicating that there exists quantum phenomena that violate Bell inequalities, as shown by Bell. Even though in the original paper in 1964, these phenomena require perfect correlation, so they cannot be experimentally observed in the lab. So it is really at the level of what theory exists for some idealized phenomena. These are not to be confused with the operational notions of signal locality and predictability, which do not include any assumptions about the beables. And this is maybe not as well known, but also from these two assumptions, you can also derive Bell inequalities. And from that, since signal locality is more widely agreed to be satisfied in our world, the violation of Bell inequalities implies that there are phenomena which are fundamentally unpredictable, which is something that has consequences for randomness generation, for example. Okay, and Bell's 1976 theorem now used the concept of local causality, which is best formulated as follows. If two space-like separated sets of events A and B are correlated, then they have a set of common causes C in their common path-like cone, such that conditioning on C eliminates the correlations. And so if we let these common causes include, or rather, if we assume that the ontic variables, a complete description of the ontic variables give us this common cause, perhaps together with the preparation, then local causality implies that the model probabilities for the outcomes in one arm of the experiments are independent of both the setting and the outcome at the distant arm. And so in Bell's 1976 theorem proceeds by showing that these assumptions imply what we call a Bell local model or a local hidden variable model, which is that the probabilities have this factorizable form. And now one quick observation is that for pure entangled states in quantum mechanics, there are frequencies, there are phenomena, rather phenomena for any pure entangled state in quantum mechanics, there are phenomena which are not factorizable in this form. And so if we consider operational quantum theory in which there are no hidden variables, that means that it violates local causality trivially, right? What Bell was showing was that the only way to maintain local causality is to consider the possibility of hidden variables. So in this sense, it is not an assumption of the theorem, but it's the only alternative to try to maintain local causality because operational quantum theory trivially violates that assumption. And so what he showed was that there exists quantum phenomena for which there is no model satisfying local causality and no superdeterminism. And since the violations of Bell inequalities have been conclusively demonstrated, we can say that nature violates the conjunction of these assumptions. Now, Arthur Fine showed that, well, first of all, we can easily see that locality and predetermination imply local causality, but the converse isn't true, as you can see by just considering, say, separable states in quantum mechanics, which violate predetermination, but satisfy local causality. But on the other hand, Fine showed that any phenomenon, there exists a model that satisfies local causality if and only if there exists a model that satisfies predetermination and locality. And so in this sense, the two theorems are logically equivalent. And so I bother making that distinction. And the reason is that they suggest different implications. The followers of Bell take it to imply that quantum phenomena are non-local. Most quantum physicists only read Bell's 1964 paper, which is the most widely cited, and they conclude that we can keep locality if we give up predetermination. And it's unfortunate that Bell himself added to that conclusion soon after defining local causality. He said, for example, it's important to note that to the limited degree to which determinism plays a role in the APR argument, it is not assumed, but in fact, what is held sacred is the principle of local causality, or no action at a distance. And even here, it's not a very good way to describe what local causality is saying, but no action at a distance better read as the meaning of locality in 1964. There is a widespread and erroneous conviction that for Einstein and his followers, determinism was always a sacred principle. My own first paper on this subject starts with a summary of the APR arguments from locality to deterministic hidden variables. But the commentators have almost universally reported that it begins with deterministic hidden variables. So let's go back to Einstein and Podolsky and Rosen, also completing my assignment from Chris, to see the merit of this claim from Bell. So this comes in the wake, of course, of the famous Einstein-Bohr debates, which Guido gave us a nice summary of, which has been widely reported to be won by Bohr. At the time, Einstein was not yet interested in showing that quantum mechanics was incomplete, but at least in Bohr's account of it, that it was incorrect, that he could find, he was trying to devise various thought experiments which would allow him, he thought, to demonstrate a violation of the uncertainty principle. And Bohr always countered those arguments by showing essentially that Einstein was neglecting to include the uncertainty principle for some parts of the apparatus. And so in the 1935 Einstein-Podolsky-Rosen argument, they revert to targeting the completeness of quantum mechanics, or the completeness of the operationalist description of reality that was proposed by Bohr and Heisenberg and others from the Copenhagen interpretation. Einstein has complained that the paper was written by Podolsky and it doesn't fully capture his views. That the argument was lost in the formalism. And so I'm putting the words in the mouth of Podolsky here. So it starts with a distinction between reality and the concepts of a theory. Yes. They said that any serious consideration of a physical theory must take into account the distinction between the objective reality, which is independent of any theory, and the physical concepts with which the theory operates. These concepts are intended to correspond with the objective reality. And by means of these concepts, we picture this reality to ourselves. In attempting to judge the success of a physical theory, we may ask ourselves two questions. Is the theory correct? And two, is the description given by the theory complete? And so they do not give a definition of completeness, but rather a necessary condition for it, that every element of the physical reality must have a counterpart in the theory. And they're going to say that the usual conclusion from the Copenhagen interpretation is that when the momentum of a particle is known, its coordinate has no physical reality. If both of them had simultaneous reality and thus definite values, these values would enter into the complete description according to the condition of completeness. These would then be predictable. And here I make an emphasis because I'll return to that later. And of course, an element of reality is analogous to Bell's notion of a beable. In fact, Bell said at times that they are meant to be essentially equivalent. They then give a sufficient condition for reality. So now that notion of completeness can only play any role if we have any way of deciding what physical properties are supposed to be real. And they don't, again, don't give a definition of reality, a comprehensive definition, but they say that we can obtain evidence for it from observations, from experiments. And a sufficient condition is that if without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. There is, if the phenomena is such that, so then they consider a phenomena similar to the Bell experiment, rather Bell consider a phenomena similar to the EPI experiment, where we have a preparation of an entangled state going to two distant labs, such that when the same observable is measured on both sides, the outcome at the distant arm of the experiment is predictable given the outcome on one side, satisfying the antecedent of the sufficient condition. And so therefore there is an element of reality corresponding to this observable, at least in the context of the other observable being measured, which I'm just sort of notating this way. And then they give a localistic assumption, which since at the time of measurement the two systems no longer interact, no real change can take place in the second system in consequence of anything that may be done to the first system. So if there's an element of reality for this observable XB in the context of XA, then that element of reality must be there regardless of that distant context. And as I emphasized before, what they take the existence of an element of reality to imply then is that these values must be predictable. And they must now be predictable given only the local choice of setting and without any regard for what's happening in the distant arm. And this is a key part of the assumption. And if you use the same arguments for momentum, we conclude that there's an element of reality for both of these quantities, and so both of them must be that there must be a model probabilities in some theory which makes them predictable given some ontic state. In a complete theory, they will be predictable, therefore there must be some ontic states that such that if one had knowledge of those, the probabilities would be deterministic. But in operational quantum theory, there is no possible state preparation that satisfies both of these conditions, and so we get a contradiction. And so taking the other assumptions for granted, EPR conclude that quantum mechanics is incomplete. Now, what does that have to do with local causality, like Bell was suggesting? That's what his argument started with. Now, it is possible to derive this chain of implications that we require using local causality. The fact that these the outcomes at Bohr are predictable from the outcomes at Alice imply that the model probabilities given lambda must be predictable, must be deterministic. And if we use local causality, we can derive the local predictability that's required for the proof. But EPR's assumptions themselves are not equivalent to local causality. For one, they really only have any bite for perfect correlations. They only have implications for perfect correlations. And their localistic notion, what they had as a localistic notion in the paper, is not local causality, but it's something weaker than that, something that plays a role more like locality or primary independence in the sense of Bell's 1964. So then they claim that it was all along the local causality they had in mind. It may have been an intuition behind that localistic notion, but it was never something they clearly stated. And so if we're calling this a theorem, you would expect it to have clear definitions of what is being proved, and that was not the case. Nevertheless, if they did start with local causality as defined by Bell in 1964, then the proof of incompleteness becomes much simpler. Because local causality implies that the model probability is factorized. And completeness of quantum mechanics for Bohr, we can take that just to mean that the probabilities for Bohr are given by some local quantum state. And similarly for Alice. And so local causality and completeness just implies quantum separability, implies a separable state. And so any demonstration of entanglement is a demonstration of the violation of the conjunction of these two assumptions of local causality and completeness. Even without perfect correlations. Okay, so something like this was developed by Margaret Reed in 1989, where she relaxed EPR's sufficient condition for reality, which we didn't quite state it like this in the original paper, but Margaret was my PhD supervisor, so we have discussed these things many times. And her sufficient condition for reality can be stated as such that if without in any way disturbing a system, we can predict with some specified uncertainty the value of a physical quantity, then there exists a probabilistic element of physical reality which determines this physical quantity with at most that specific uncertainty. And using that relaxed criterion, we can derive, she derived, experimentally testable criterion via the violation of an inequality that involves average inference variances of observable at Bob's given the outcomes of observations at Alice. So essentially, if you violate this inferred uncertainty principle, that's a demonstration of the EPR paradox in this relaxed form. This can also be derived from a formalization of the notion of steering that was a concept that was coined by Schrödinger in a paper in reply to EPR, where he also coined the term entanglement. So in this paper from Howard Wiseman, they defined steering as the violation of a local hidden state model, which is essentially a model which satisfies local causality plus completeness, you can think of it this way, for Bob's system. You can also derive experimental criteria for this phenomenon that we call EPR as steering, reproducing the EPR Reed criteria as a special case, but also more general, deriving more general criteria. It can also be interpreted as a task where a referee trusts Bob of his devices in a task where Alice and Bob are attempting to demonstrate that they share entanglement. Okay, so now back to Bell. So in reply to the suggestion that we can just reject, that we can maintain locality as a well-defined concept, he said, do we then have to fall back on no signaling faster than light as the expression of the fundamental causal structure of contemporary theoretical physics? That is hard for me to accept. For one thing, we have lost the idea that correlations can be explained. So you saw this notion of local causality as being fundamental for the idea that correlations can be explained causally. So what is the history of that? So Bell's notion of local causality can be traced back to Reichenbach's principle of common cause, even though there's no evidence that Bell knew of Reichenbach. But it's conceptually it's part of Bell's notion. Reichenbach's principle says that if two sets of events are correlated and no event is a cause of the other, then we have a set of common causes. Such that conditioning on that common cause eliminates the correlation. Also, interestingly, Reichenbach did a lot of work in the foundations of quantum mechanics. And obviously, he thought a lot about causality and the concepts of time and space, but he never came to Bell's theorem, or Bell's theorem, which I think goes to show how deep was Bell's insight in proving that, even though in hindsight it may sound simple, even for someone that was thinking very hard about those questions. Reichenbach just took for granted that this was a sensible notion of causality that must hold in our world, even though he knew well about quantum mechanics and thought deeply about it. So together with the assumption of relativistic causal error, that any causes of an event are in its sparse-like cone, Reichenbach's principle implies local causality. Now, if we are rejecting local causality, then one way of doing that is rejecting relativistic causal error, which is the direction that the archetypal realists do. But another option could be to reject Reichenbach's principle. But then for Bell, the question is, then what does it mean to explain things causally? We've lost the notion that correlation can be explained. But it's possible to break Reichenbach's principle into two further independent principles. One is the principle of common cause simpliciter, which just says that if two sets of events are correlated, then they must have some common cause that explains the correlation. And the other is what we call the principle of decorrelating explanation, or factorization of probabilities. That what it means for a common cause to explain a correlation is that conditioning on the common cause, correlation factorizes. Now, let's introduce also another assumption of principle of free choices, that it is always possible for any particular experiment to choose experimental settings via free variables. And by that, I mean variables that do not have any causes among, nor share a common cause with any variables that are causally relevant for a given phenomenon. How do we know that we are doing so, that we are choosing our experiments with free variables? That's a hard problem for the experimentalist, but the principle is the assumption that it's always possible to do that if we are careful enough. So now, Bell's 1964 theorem can be reformulated as such, as which was a predetermination, locality, no superdeterminism. We can derive locality and no superdeterminism from these three assumptions of free choices, relativistic causal error, and common causes, and local causality, like I said before, from relativistic causal error and Reichenbach's principle. So fundamentally, we can see the theorem as a contradiction with the conjunction of these more fundamental principles on the top. Now, the operationalists, they reject predetermination, at least the archetypal operationalists that I was referring to earlier. But then we see that that's not enough, because in Bell's 1976 theorem, that is not one of the assumptions. So they must reject something else. Now the realist rejects local causality, and the archetypal realist rejects relativistic causal error in doing that. So before talking about the operationalists, let me also introduce another concept of local agency, which is simpler. It's more natural than locality and no superdeterminism, but it can be used in that place in both versions of the theorem. It just says that any free choice is uncorrelated with any set of relevant physical variables outside the future light cone of X. And so Bell's 1976 theorem can be proved with the conjunction of local agency, local causality, and I'm including here already the notion of absolute events, which is usually kept as background. And the 1964 theorem can also use local agency instead of locality and no superdeterminism. Right, but now the operations must reject something else other than predetermination. They presumably want to keep this notion of local agency, which was the motivation for rejecting predetermination in the first place, and so they must reject local causality. But they also want to avoid rejecting relativistic causal error. They want to maintain compatibility of relativity. So they reject Reichenbach's principle, but it is possible to reject just the degree correlating explanation part. And why would the operationalists do that? Because this is, one could argue, the classicality assumption that Werner was referring to, after all. Not just predetermination, but really the assumption that common causes factorize the probabilities. But it's possible to maintain, nevertheless, the principle of common cause while doing it. For example, one can replace the factorization of probabilities by the factorization of the Choi operators for the quantum channels from the common cause system to A and B. So there's still something that factorizes, which matches the causal structure as we would expect, but it's not the probabilities. And that's the kind of causal explanation that is implemented in the frameworks of quantum causal models. And John Barrett will talk about that, I believe, in the last day of the conference. So I won't get into more details here. But it's an option that is now open for the operationists who are previously either rejecting predetermination or some vague notion of classicality. The notion of classicality, more precisely, is this, and it is nevertheless possible to maintain a notion of causal explanation that satisfies relativistic causality while doing that. So that's a nice resolution, except for the measurement problem. So now I'll talk about a recent result from myself and co-authors on the extended Wigner-Strand scenario. So it's a local theorem based on Bruckner's version of an extended Wigner-Strand scenario, which extended in the sense that it takes a Wigner-Strand scenario where there's an observer being treated quantum mechanically, and use that on top of a Bell scenario. So we have two observers, Charlie and Debbie, besides some isolated laboratories, and some super observers, Alice and Bob, who are performing some measurements on the observers and the contents of their lab. They're called super observers because, of course, depending on the complexity of these observers, they would need very complex abilities to do that. So this theorem proceeds as follows. The protocol, if Alice chooses X, so Charlie and Debbie are performing some fixed measurement in the isolated labs, obtaining outcomes C and D. Alice, say, chooses between various choices of measurements. If X equals 1, she'll just open the lab and ask Charlie what he observed and set her own outcome to be equal to that of Charlie. If X is 2 or 3 or any number of choices of settings, she'll do a different kind of experiment on the lab. And it's always possible to implement it in such a way that the interaction between Charlie and the system, which enacted the measurement, is reversed to the unitary that by which this measurement was implemented is reversed, and now in the process, Charlie loses any memory of having done any measurement, and the system is now back in its original entangled state of the distant lab, and Alice just proceeds to perform a measurement on some compatible basis on that system. And so here in the space diagram, I indicate the various variables, and I note that there are no assumption that there are any variables that are not observed by some observer. All of these variables are variables that are observed by some observer in every run of the experiment. And we call local friendliness the conjunction of these two metaphysical hypotheses, the absoluteness of observed events and local agency. And from these we derive local friendliness inequalities, similar to Bell inequalities, which are constraints on the phenomena that are observable by Alice and Bob. And we show that they can be in principle violated if this technological assumption holds that a super observer can perform close to arbitrary quantum operations on an observer and its environment. And we also did a proof of principle experiment that violates the local friendliness inequalities, and proof of principle because the observer was a very simple system, just another qubit. So very quickly, the derivation proceeds by the absoluteness of observed events implies that there exists a joint probability distribution for all of these variables in every run of the experiment, since they are all observed events in every run, such that the marginals observed by Alice and Bob are recovered. But these are not arrived at by an assumption that there must be some variables that explain correlations by factorizing as a common cause, but just from the assumption that these variables were observed and therefore they must have a well-defined value in every run of the experiment. There's also an assumption of tracking, which is that if when Alice chooses to ask Charlie what he observed, the value that Charlie will report will be the same as the value that Charlie actually observed, which was later called tracking by Matt Lipper and others in a review paper. And the assumption of local latency is essentially the same as the implications of locality and no superdeterminism, but now in this kind of scenario. And so we showed that these assumptions lead to a set of correlations which form a polytope, the local friendliness polytope, which is strictly larger than the local hidden variable polytope, the set of correlations that are compatible with a Bell local model, and which is strictly contained in the no-signaling polytope. And here in red, we have the boundary of quantum correlations. And so here we see that there are some quantum correlations that violate some Bell inequality, but do not violate any local friendliness inequality. This is an actual 2D cut on this polytope, although that statement isn't implied just by this 2D cut, but we derived all of the inequalities in this scenario for 3 settings and 2 outcomes per side. And so this is a consequence of the fact that the LF assumptions are strictly weaker than the assumptions that are required to derive a Bell inequality. And so their violations have strictly stronger implications. Just going back to that concept diagram, comparison of the 2 theorems is that the local friendliness noble theorem now does not need to assume the correlating explanation. So the alternative that was open for the operationalist via quantum causal models is no longer available as a way to resolve this theorem. So if you want to keep local latency, which was the motivation of that camp all along, then we must reject absoluteness of observed events. So just to finish, then let me read this quote from Bell. He said, "For me, then, this is the real problem with quantum theory. The apparently essential conflict between any sharp formulation and fundamental relativity. That is to say, we have an apparent incompatibility at the deepest level between the 2 fundamental pillars of contemporary theory. It may be that a real synthesis of quantum and relativity theories require not just technical developments, but radical conceptual renewal." And so for the archetypal operationist that I've been referring to, who wants to keep local agency as presumably a means to maintain compatibility with relativity, these new no-go theorems suggest that perhaps what is required is even more relativity. Whereas in Einstein's theory of relativity, space and time were found to be relative, but events were too absolute. Maintaining compatibility with relativity would require that events themselves are relative. Thank you.
Thanks very much, Eric. We have about 15 minutes for questions. If you have your hand up, I will take note of you. First question here.
Okay, hi. Thank you for the talk. I have a suggestion for the radical conceptual development, cubism. I have a question. I have a question too. Isn't the formulation of steering, maybe not the term, but the concept due to Einstein in a letter to Schrödinger? So there was a letter in 1935, letter by Einstein to Schrödinger, where he discusses exactly the phenomenon of steering without calling it that, of course.
Right. Well, I mean, that was, in my understanding of it, maybe I don't know that part of the history well now. My understanding was that it was the term that Schrödinger coined in reference to the phenomenon that EPR were talking about. So in the sense of who discovered the phenomenon and the implications of it.
That's not the truth. This was not EPR. This is
right.
Prior
to EPR?
They said, no. Same time as EPR. Also, letter in 35 from Einstein to Schrödinger.
Right.
Used not the EPR argument, but really precisely the steering argument.
Right. But he didn't use the term. Yeah, I mean, I think that mainly it was well, it's not my I think it's fair probably to assign credit for the idea to Einstein, because to the extent that Schrödinger was talking about steering, he was referring to EPR. So, but I don't know of the letters from Einstein to Schrödinger. Yeah, if you can give me the reference, I'll be curious to see what they say.
Okay. Just to let you know, we've got about 5 people in the queue, and now a little bit left in.
Okay, I just want to make a comment more than anything. In fact, it's a plea, actually, because I've written over the years a couple of papers with the word superdeterminism in the title, and I actually regret doing that, because not for the reasons that perhaps people are thinking. Like you, I used the word as synonymous with a violation of measurement independence. And what I learned, to my regret, is that people associate the word with something very specific, which is a kind of unacceptable conspiracy where experimenters, are zombies that just do the bidding of some laws of physics and have no capability of deciding. And the plea I want to make is that we just go back to the basic mathematical assumption. So measurement independence, I think, is links fairly straightforwardly to that mathematical statement, rho lambda given xy equals rho lambda. Because personally, I think there are much more subtle ways of violating that. I don't want to get into this, but I just think there are more subtle ways of violating it than just to say experimenters don't have free will. And I don't think we've explored the implications of that mathematics. So the plea is, don't use that word superdeterminism, because people come at it with a baggage, and I, as I say, I regret doing it because of that baggage.
Yeah, that's fine. I mean, in that more fundamental formulation, I'm no longer using that word superdeterminism either, but just what today I was calling freedom of choice. And that's not an assumption that experimenters have free will. It is, like I said, the assumption that for any experiment, any repeatable experiment, it's always possible to choose the experimental settings via free variables, external variables that have no relevant causes, no causes among any variables, which are also causes of other variables in the same experiment, or that are caused by other variables in the same experiment. Yeah.
Oh, you start. The next question from Richard here.
Yeah, I just wanted to point out that in Bell's later arguments, he states a condition of local causality, which is rather long and complicated. I'm thinking of Landau disease specifically. And he takes that to be motivated by an intuitive principle, which he also calls local causality. So the question arises as to whether the condition of local causality, as he formulates it there, is really an effective way of cashing out the intuitive principle of local causality. And it may be for a theory of local variables, which is supposed to be trying to complete quantum theory or doing something else. It doesn't really matter what it's trying to do. But it's not a good connection, a good inference in the case of quantum theory, which does not give you a unique probability for each particular observable. The probability depends on what you're relativizing it and the quantum state that generates it to. And if you take that into account, the condition of local causality is not a consequence of the principle and therefore ceases to have any intuitive motivation inherited from it. So I don't think it's true that quantum theory violates local causality. It doesn't violate the condition of local causality unless you understand it in such a way that it's not motivated any longer by the intuitive principle of causality.
What do you mean by the condition of local causality?
It's a condition formulated which uses the word causation, whereas the condition does explicitly avoid using the term causation. He thinks that the term probability is clearer than the term causation. I think they're both equally unclear, so I don't think that's much progress. But the connection between them is lost unless you focus specifically on the kind of theory that quantum theory is not.
Yeah. Well, let me say something, and maybe you tell me if I answer your question or not. So first, the principle, like I said, of local causality can be derived from Reichenbach's principle of common cause, which is widely agreed by philosophers to capture some reasonable principle of causality, at least classically, and relativist causality. It's just Reichenbach's principle of common cause in a world in which causes are in the path like random. And so that's just all there is to it. So if you think that it's not a reasonable principle, then sure, that's fine. You can just saying that Reichenbach's principle of common cause is well, I think it's unfair to say it's not reasonable. If it were not for quantum mechanics, I think no one would be arguing that it's unreasonable.
Principle contra.
But it's happened. You may conclude that it's false.
Principle.
Are you trying to say that it's not well motivated? I didn't quite understand that question.
No, my point was that the principle of local causality, the intuitive principle, which includes causal pull, is far
like Reichenbach's principle, for example.
But that's not the principle that plays the role.
No. But like I said, it is implied by Reichenbach's principle and relativistic causality. I may say, well, I refuse to talk about causality at all. It's fine. I mean, that was not Bell's position, that's for sure.
I think I made my point.
Okay.
Right. The next question is from Wayne Yerba.
This is a relatively minor one. So you mentioned this tracking condition in the local friendliness theory. So what happens if you allow small probability of violation of that? Like, because these are inequalities, if there's a small probability that what we transmit will be wrong, then you still get an inequality violated by quantum mechanics. Are there any theorems out there about how big a probability of violation of tracking?
Yeah, it's a good question. It's possible to relax it. So there's been a paper where they derived relaxed LF inequalities, where they allow for possibility that tracking is violated with some probability, and it's quite robust. It's not.
Okay, what paper is that?
On top of head, I forgot, but he included Rafael Chavez as one of the authors.
Okay, I'll look for it.
Yeah.
And then Simon Saunders.
It's the corner, isn't it? So I just have a question as to whether you think Reichenbach's principle plus relativistic causality picks up on what Richard was saying, actually, this notion of specification of remote events. So Alice's local specification in Bell's favored definition, and Euclideus's favored definition. Look at the preface to the.
You mean in La Nouvelle Cuisine?
Yes.
Yeah.
The one in Nouvelle Cuisine, and there's a long footnote in an earlier paper, which also has the same condition. It says this is my favorite condition. But what it does is not only does it not involve the word causation, but it involves this notion of specification, of
specification of
remote
variables.
Yeah.
So I think
my question. I haven't got my question yet. So when he says that specification, if you change that wording and made it not specification of local events, but causal Bob's free actions in causing events, then the principle also requires an additional premise, namely that Bob's actions, what he can causally bring about, is a unique outcome to his experiment, as opposed to, in the Everett interpretation, I'm sorry, but we are in Oxford, as opposed to the Everett interpretation, where Bob causally brings about a superposition of outcomes. So if it's specification of outcomes, you can just specify one of them. And then that would imply outcome independence, which along with parameter independence implies Bell's inequality. But if the wording is not specification, but what can Bob causally bring about, then it does not imply outcome independence, and you do not derive Bell inequalities. So I'm just intrigued. I mean, do you think there's anything in Reichenbach that would lead to a formulation in terms of specification of remote events as opposed to causally bringing about remote events?
I think there's a confusion there in what the specification is supposed to be. It is a complete specification of the common causes. So when you formulate in terms of Reichenbach, it's clear what it is. If you fully specify the common causes, well, that's all you need to do. You don't need to go and specify everything that common cause like, right? You just need to find the common cause and fully specify that. And once you do that, you would expect, if local causality is true, that the correlations factorize.
But this isn't getting at, sorry.
It's not required that the outcomes are determined. Sure.
Thank you. This is a short question. One of your slides, you went past it rather quickly, where you showed the work that you'd done about breaking up Reichenbach's principle of common cause into two. Now, the first part was perfectly, I think it was slide 38. I made a point of it because it went to 39 very quickly. Right. So I understood the first one, but I didn't get a chance to appreciate what the second part was.
Yeah, it's just saying that what it means for the correlations to be explained by the common causes is that if you know everything there is to know about the common causes, conditioned on that, correlations disappear. Right? There's a correlation between eating ice cream and drowning. And, whoa, that's a bit surprising. People drown when they eat ice cream? No, that's because people eat more ice cream when it's summer. And then knowing that it's summer or winter, then there is no longer a correlation. Thank you.
The last question is down in head.
Yeah, thanks very much. First, I have an answer to Wayne's question. There's a paper by Moreno, I think from 2011, titled Events in Quantum Mechanics are Maximally Non-Absolute, that addresses that point to relax this tracking assumption. And I myself worked in that too. There's a paper about as well. But what I wanted to say is, I think Tim Modlin often says that the extended Venus friend experiments do not really add anything to the standard Bell inequality violation. And maybe you can say something about this. I myself, I do not agree with this because I think it is interesting for the fact that since we model the observers explicitly and their knowledge and their memory states, it tells us something about the epistemic parts of the hidden variables and what we can know about the hidden variables, because in a way we can see Alice and Bob as assigning hidden variables to Charlie and Debbie in your experiment, right? But my question is something else. So you, in the absoluteness of observed events assumption, you have two conditions, right? There's a joint probability distribution for the variables A, B, C, and D, and then the tracking assumption. And I was just curious.
Yeah, I would say really that tracking is a auxiliary assumption separate from the observed events.
Okay, so that
that might not have been clear in the original paper, but I think Matt's paper, that's formulation. I think makes it clear that it's really an auxiliary assumption.
You would not call a violation of the absoluteness of observed events?
No, I would. That's why I would prefer to say it's actually a separate assumption. I would use the word in such a way that it's certainly possible that the world is such that absolute of observed events is true, that every observed event is absolute, some single absolute event. And nevertheless, tracking is systematically violated, right? I think it would be very strange if that's the explanation that you have for the violation of the inequalities, including for reasons that I think we couldn't trust our own memories, right? because okay, in an LF experiment, it's a very strange kind of situation, but there the assumption is that when Alice opens the door and asks Charlie what Charlie observed, what Charlie reports having observed is not what Charlie saw. Then therefore, Charlie has a false memory somehow. And now that's not a mystery that we have to explain. How does Charlie have a false memory? And if that's how it's trying to explain quantum mechanics, I think we're adding a bigger mystery there.
I'm afraid that's all the time that we have listening, Gary. All right, our second talk in this afternoon session is from Matt Layfair, who is going to festively tell us about the many faces of quantum contextuality.
Yeah, thank you. So when Chris Timpson asked me to give this talk, he said give some sort of a survey of something to do with contextuality. I was like, okay. There's a lot there. By the way, we are festively celebrating 100 years of quantum mechanics. I'm also celebrating 25 years since I started my PhD. So that means I've been working on this stuff for a quarter of the time it's been around, which is quite a scary thought. So when I was thinking about what to do about contextuality, I said, well, why don't I go back to when I first started thinking about it, like maybe 20 years ago, back in 2005 when I was at Perimeter Institute. This is a blackboard that I drew, part of a blackboard that I drew, because back in those days, what they liked to do at Perimeter Institute was do publicity photos where people stood in front of blackboards that should have said written things on. It didn't really matter what was written on them, but so they used this in publicity shots for a long time. And I would ask my physicist colleagues, what do you think this thing is? And they would all say something like, if they weren't quantum foundations people, they would say something like, oh, it's some group theory thing in the standard model or something like that. But it's not. It's the fundamental building block of the original Peirce-Becker theorem. And it is also Rob Clifton's statistical proof of contextuality. So I've been thinking about that for quite some time. And I went back to some of my early talks on this. It's kind of scary. That I am probably in the first generation of researchers where I can find talks that I gave right at the beginning of my career online, right? So I can embarrass myself and watch all the things that I said in the past. And so I looked at some of the things I said, and what I realized was that I was a lot clearer when I was younger. Everything was to the point, you know, my talks had a point, and now I'm trying to do this survey, and I'm 25 years more confused, and I have 25 times the amount of things to say, and usually 1/25 of the time to prepare the talk. So I'm going to try and make a coherent whole out of this, but we'll see how it goes. Also, before I start, I'd like to thank the John Templeton Foundation, not only for this conference, but also for funding the Southern California Quantum Foundations Hub, which allows us to do this kind of fun research in California. Okay, so here's kind of the theme that I want to make for this talk. So I want to do a little bit of history, not too much because I'm not a historian, but just to set the context. And here's the sort of trajectory that I think research in quantum contextuality has taken. So it starts out, to my mind, really as a theorem about quantum logic, a theorem about truth values in quantum logic. That approach to quantum foundations is not so popular anymore. So that kind of view has fallen out of favor. At around the same time, though, it was viewed as a no-go theorem for hidden variable theories. And the no-go theorem for hidden variable theories inherited a lot of baggage from here, which I think is responsible for some of the confusions and debates that surround it. But in more modern times, it's gone to be a robust indicator of non-classicality, and I want to explain what I mean by that. By the way, as a no-go theorem, you know, you can tell I'm talking after Eric here. The Cauchy-Specker theorem has always played kind of second fiddle to Bell's theorem, and since somebody mentioned Tim Maudlin earlier, whenever you say to Tim Maudlin, oh, I'm interested in contextuality, they'll say, oh, well, Bell's theorem is a type of contextuality, just study that, it's more interesting. So there we go. Right, so I'm not a person who likes to read outline slides, so there it is. I'll just start with the background. So those of you who know about this stuff will be very familiar with this stuff, but I assume there are some people in the audience who are less familiar with it. So let's start with the timeline. So to my mind, things start out with quantum logic. So von Neumann, in this community, is often treated as public enemy number one for his theorem for hidden variables. But he also did a lot of interesting work in the foundations of quantum mechanics. So he points out, so in his book, and then later with Birkhoff and von Neumann, he points out that we can view the method of projection operators in quantum mechanics as a generalization of a Boolean algebra, and he proposes a generalization of that as somehow the algebraic structure behind the quantum logic. That's the proposal. Other people pick up on that. In particular, Mackey uses it as an axiomatic, or he's the first one, I believe, to use it as an axiomatic foundation for quantum mechanics. But before then, when he's hearing about this, there's a natural notion of what's a probability measure on the projection lattice. Okay, what's the generalization of a probability measure from Boolean algebra to a projection lattice? And he wonders whether there are any such things other than those given by the Bohr rule. He's wondering this when he's visiting the University of Chicago, and he's talking to Siegel, who has a graduate student called Cadderson, who immediately proves that there are other measures to be dimension 2. So that's it's actually quite easy to prove, but apparently nobody realized it before that. Okay, so there's still an open question what happens in higher dimensions. And in 1957, Andrew Gleason proves that there are no non-quantum probability measures on the projection lattice in real or complex Hilbert space. That's important. Okay, so that theorem, which is really sort of the start of the mathematics of contextuality. So let's suppose pH is the set of projectors on the closed subspace of a real or complex Hilbert space that has dimension greater than or equal to 3. Then we can define what we might call a probability measure on it. So what we should have is that if two projectors are orthogonal, then the probability assigned to their sum should be the sum of the individual probabilities. And if we should assign the probability 1 to the identity projector, because that's the trivial measurement that always gives the same outcome. and that's, at least in finite dimensions, that's enough. So if you make those assumptions, then what Gleason showed is that there exists a density operator such that the probability measure is just a trace of the projector times some density operator. And so therefore it's quantum, it's in quantum mechanics. Okay, so Gleason definitely thinks he's proving a theorem in quantum logic there. But in Bell's review in 1965, so some people have pointed out to him that you could get a no-go theorem for hidden variables from Gleason's theorem, and he comments on it and dismisses some of the assumptions. I'll talk about this in a little bit. Okay, I didn't mention the non-contextuality part, but it's important, right? So what's non-contextuality here? It's the fact that this probability measure is only supposed to depend on the projector. So when we consider the same projector in two different measurements, it always gets the same probability. Okay, now that's not necessary, but it's sort of natural assumption from the point of view, from the sort of logic point of view. So then Koch and Specker come along, and I can't write the letter C apparently, but they do the same job as what Bell's argument did, except they do it with a finite set of projectors. And then there's a whole array of simplifications, right? So making simpler arguments, people trying to set records for the lowest number of vectors involved in a proof. Personally, I'm not particularly interested in that, but it is true that it is useful sometimes to have smaller proofs, because when you're trying to think about them, how the structure of them, it's a bit easier. I'm not going to go into a whole bunch of, I mean, there's a whole bunch of other kinds of proof of contextuality that people also came up with. Okay, so just to review this stuff, what does Bell say? Well, let's take the set of projective measurements on H. So sets of projectors that sum to the identity. Then we can do a similar thing. You can say, well, let's define what we mean by an outcome deterministic hidden variable theory. It's basically going to assign a definite outcome to every possible measurement. So given a specification of measurement and one of the projectors, that's one of its outcomes, that's going to be assigned the value 0 or 1. And clearly, for every measurement, exactly one of those projectors has to be assigned the value 1, the rest 0. And that's given in this condition here. Now, suppose that this F here happens to be independent of n. So again, it's a function of the projector only, and this is the non-contextuality assumption, right? Then this is a function from the projection operators to 0 or 1, satisfying this condition. And the Gleason's theorem then implies that this is, because this is a special case of Gleason's assumption. So it must be a trace of some density operator times the projector. But pick any density operator you like, you can always find a projection operator such that, or I should say trace pi rho, sorry, trace pi rho is strictly between 0 and 1, right? So for example, if you choose the pure state 0 of a qubit, then you choose the plus state, which is an equal superposition of 0 and 1, then you'll get this probability of half. So therefore, you can't have both that this function gives you 0 or 1 and that it's the trace of some density operator. Okay, so that proves that something has to go wrong. So what does Bell say? Bell says, well, basically this is an unreasonable assumption. So the results of observation may reasonably depend not only on the state of the system, including hidden variables, but also on the complete disposition of the apparatus. Okay, and he has an example in mind, which is de Broglie-Bohm theory, which he explains how this works in, where it's exactly like that. So not only is the assumption that this is independent of m, not justified, but even that it has value 0 or 1, right? Because you may need to specify the state of the apparatus in order to have full knowledge of what the outcome is going to be. So that's his view on that anyway. Now, I'm not going to now present the 1967 Cauchy-Specker proof, but I think it is, for those of you who haven't seen it, probably not many, but it's instructive to have at least one proof of the Cauchy-Specker theorem in this talk. So let's look at the 18-ray proof, which is the smallest one that we currently know. So what we have here is that all these phi's here represent one-dimensional projectors or rays in Hilbert space. And if they are grouped together in these sort of colored hyperedges here, then that is a complete orthonormal basis. Okay, so if we try to apply the Cauchy-Specker non-contextuality, then what we need to do is find a way of choosing in each orthonormal basis one of the outcomes to be the one that occurs, and we need to do it such that in any one of these sets only one of the outcomes is given to occur. So basically we have to color some of these dots in black in such a way that there's exactly one black dot in each of these sets. You can try to do it, but believe me, you will always find at least one basis where you can't do that, and we can prove that in this way. So here I've written out the sets again. Oops. Okay. So here I've written out the sets again. So these are all the bases that we have. You can see there are 9 bases. In each one, one of the phi j's has to be assigned the value 1, the rest 0. So there's going to be a total of 9 rays given the value 1 in each of these bases. However, if you look, you can see that each of the phi's appears exactly 2 times in the table. So by a non-contextuality assumption, whenever I assign one of them the value 1, there's another one that also gets assigned the value 1 somewhere else in the table. And so there'll always be an even number. So that's why you can't do it. It's a contradiction. Of course, the remaining thing is to show that this actually occurs in quantum mechanics. And so here are the 18 rays in real 3-dimensional Hilbert space. So if you normalize those, you get the bases. Okay, so now both Bell and Cauchy-Specker framed what they were doing in terms of hidden variable theories. But here's the reason why you might want a finite proof if you're thinking about quantum logic, right? So as a result, so if I write out this very long proposition here, what does this say? This statement here says, in a long-winded way, that in this basis, phi 1 to phi 4, exactly one of these gets the value 1, and exactly one of these is true and the others are false, right? So this encodes the idea that in this basis, exactly one of these is the outcome. So you just take all those statements and you take the conjunction for all of those 18, sorry, not 18, all of those 9 bases. And due to the Cauchy-Specker proof, this is a contradiction in classical logic, in classical Boolean logic. It's just a contradiction. It always has truth value false. But in quantum logic, it's not just not false, right? Because in quantum logic, something can be, doesn't have to be true to be not false, right? It can be indeterminate. Here, it's actually satisfiable, because if we use these assignments, then we find out that each of these, then each of these terms is true. Okay, so it can be, so you have something that's a contradiction classically that's actually true, or can be true in quantum logic, and that's kind of interesting if you're interested in that. Now, of course, the reason why I'm pointing this out is not because I think quantum logic is great, because most people have sort of gone off that idea these days. But I think that a lot of the way that some people think about this theorem has a hangover here. So in particular, the outcome determinism, so the idea that you're trying to assign values 0 and 1 has persisted very strongly in the literature as, but for some people, that's like a really crucial part of the Cauchy-Specker theorem. But we need to get rid of. Okay. So as a theorem about hidden variables, you might think, okay, well, can I test it like I can with Bell's theorem, right? And there's some strong concerns about that in the form that we've given it so far. Okay, so there's a few of them. So first of all, the way that I've stated it so far, and historically the way it was stated, depends on quantum mechanics. So it's a theorem about assigning outcomes to projectors, right? But when I do a measurement in the lab, which I haven't done for more than 20 years, but anyway, as far as I know, measurement devices in a lab don't generally come labeled with projection operators. So they're not a projection operator, it's some device, right? So how do we know that they're measuring the right projector, or even a projector at all, right? So this is unlike Bell's theorem, where when you're deriving it, when you're testing it, it doesn't matter if you measure any particular observables, measure whatever you like. If they're local observables and you get a violation of Bell inequality, then you know that you've shown non-locality. Okay, so we can't do this right here. It's not device independent in this kind of way. Then there were concerns about finite precision measurements. So Adrian is in the room here. So this started with a paper by Mayer, then Adrian Kent, Michelin Kent, and John Barrett, who's also here, worked on this. So what they argued is that if you tried to do a set of Cauchy-Specker measurements, then if you have finite precision in your measurements, then you can always reproduce it by a non-contextual model. And it's based on a proof that there are sets of bases. So I can find sets of bases actually in any Hilbert space, such that the vectors are dense in the unit sphere of Hilbert space. So that means that I can find a non-contextual set of outcome assignments to a set of vectors that are dense in the set of all unit vectors. So therefore, if you sort of try to measure a specific basis from a Cauchy-Specker set, but you have finite precision, then your measurement device could like give back to the answer to an arbitrarily close by basis, and you'd never show contextuality. Okay, so that is a big problem, right? So, and then the other problem is outcome determinism, of course. So one of the outcome assumptions is that every projected measurement is assigned a definite outcome. So as soon as you drop that, you have a non-contextual probability assignment. Guess what? It's the quantum one, right? Because that's what Gleason's theorem shows. Okay, so that seems like it's going to kill the whole thing. But of course, no measurement done in the lab is ever a perfect predictive measurement. There's always some uncertainty about what we're doing. In reality, every measurement that we do is a and part of the nature of a non-predictive nature of a POVM can arise from the fact that we have uncertainty about which measurement we're performing. And certainly not appropriate to assume outcome determinism for POVMs, although some people have in some approaches. So if you wanted to test the Cauchy-Specker theorem in any of the ways that we've thought about so far, up to this point in the talk anyway, your best bet is to just sort of reject outcome determinism, okay? instead of saying anything about non-contextuality. Okay, so obviously what we want to do is try and fix these problems. And so there have been several approaches to try and fix these problems. I'm only going to talk about time. So I'm going to talk a bit about Spekens contextuality and then a bit about its robotification and how it's related to some other things. Rolf Spekens introduced the generalization in 2005. It achieves the following things. So first of all, it operationalizes contextuality, no longer depends directly on quantum mechanics. As a sort of side effect of doing that, we get contextuality for preparations, transformations, as well as all kinds of measurements, including theorems, and we remove that determinism assumption. At this point, it wasn't yet experimentally testable because it still depends on, and I'll explain this in a minute. But the remaining difficulties will take around about 2015, although there's still ongoing work with this. Okay, so this part I'm going to go over rather rapidly because Eric already talked about it. So I'm going to ignore the transformation parts just for simplicity. I'm just going to consider prepare and measure operational theory. So we have a set of preparation procedures, a set of measurements, and for each measurement, a set of outcomes. Okay, so the theory must specify a probability of obtaining any outcome of any measurement given any preparation. So for all preparations, all measurements, and any outcome of that measurement, we have to have some specified probability. And when you sum over the outcomes, that must form a well-defined probability distribution. I'm going to make a notational note here. When I talk about operational theories, I always call the probabilities prob. And when I talk about ontological theories, I call them PR. So you can distinguish between what's a prediction of the operational theory and what's a prediction of the ontological model. Okay, so then again, just as Eric had, an ontological model is supposed to say, well, let's try and explain the experimental results in terms of some actual physical properties that the system has. And so those are the ontic states that live in an ontic state space. In my equations here, I'm going to just write it as if lambda is finite, but all this can be done in more generality. So preparation procedure corresponds to some probability distribution over the ontic state. A measurement and an outcome of that measurement correspond to a response function. They're just conditional probabilities, but for some reason in the literature, it's traditional to think of these as functions on the ontic state space. So lambda goes in here. So I'm thinking of this as a function of lambda. But the point is that these must be well-defined probabilities. The idea is that when you prepare the system, you do something that affects lambda. Lambda is the properties of the system, and so that's the only thing that the measurement device has access to. So there's no direct dependence on the preparation here. And then we just use the law of total probability to say that the predictions of the ontological model, we just average over the ontic space. And then we say that the model reproduces the operational predictions if these ontological predictions are the same as the operational ones. Okay. So then we can now define an equivalence relation on preparations and measurements. So we can say that two preparations are operationally equivalent, so denote like this, if for all measurements and all outcomes, they always give you the same probability. And then similarly, we can take measurements along with one of their outcomes and define an operational equivalence relation on those if for every choice of preparation, that outcome of that measurement always gives you the same probability. Okay, so those are equivalences. There's no experimental procedure you can do to tell these preparations apart if you don't know what they are already. And similarly for the measurements. Okay, so The Spekens non-contextuality assumption is that, so we say that a model is preparation non-contextual if whenever you have this operational equivalence, the probability distributions in the ontological model are the same. Otherwise, it's preparation contextual. And measurement non-contextuality is the same kind of thing. If I, yeah, okay. Where am I? Yeah, okay. So it's the same thing applied to the response functions. That should say measurement, sorry. Okay, so we call the operational theory itself non-contextual if it has a non-contextual ontological model. Otherwise, it's contextual. Now, what's the justification for all this operational equivalence mumbo jumbo? So Spekens likes to justify this by appeal to Leibniz's principle of the identity of discernibles. Right? So the idea is that we have two things, two experimental procedures. There's absolutely nothing you can do to tell them apart. Right? So to some extent, all of their properties, at least all of their operational properties, are the same. And so therefore, that should be because they are the same. A sort of slightly different version of the same justification is in terms of fine tuning. So the idea is that suppose that two preparations are the same, but are the same operationally, but they're distinct ontologically. It means that they do different things to lambda. So they prepare different distributions of lambda. If I just, suppose my response functions were just like generic random things, right? A bunch of like any old parameters you like, even if they were coarse-grained, if you have enough of them, you'd expect to be able to see that difference. The only way of avoiding seeing that difference is if these response functions are all chosen in such a precise way as to not reveal this difference. Okay. Now, there could very well be a reason why that's the case. Well, one reason why it's the case is because you want to reproduce the operational predictions, right? So you can just say, well, I just put that in by hand. But there doesn't seem to be a fundamental reason for imposing it. Okay. So you have a fine tuning. That's not necessarily the end of the world. Fine tunings are things that we should either eliminate or explain in some way. It doesn't mean that the theory is necessarily bad, but the explanation is missing. Okay, so I'm not going to go through this in excruciating detail. Suppose we have a theory which has a model in quantum mechanics. Okay, so we have a Hilbert space. Every preparation corresponds to a density operator. Every measurement corresponds to a PAVM. Then our operational probabilities will be just the Bohr normal probabilities. And since the same density operator always predicts the same probabilities, if you happen to have two preparations of the same density operator, then those preparations are operationally equivalent. Similarly, if you have two PAVM elements that are the same, and that tells you that if that's the case, well, what it tells you is that these probability distributions can at most depend on the density operator. They may depend on less than that if you don't happen to have a homographically complete set of measurements, but at most they can depend on the density operator, and the response functions can at most depend on the PAVM element that represents them if we have a non-contextual model of a quantum situation. Okay, so for lack of time, we're going to skip the proof here, but we dropped outcome determinism. It's no longer an assumption, but as a result, but the thing that we gained was a notion of non-contextuality for preparations. And from that, you can derive that if your model is quantum, it's a model of quantum mechanics, that projective measurements must be outcome deterministic. Okay, so it's no longer an assumption, but a derivation. It doesn't hold for arbitrary measurements, it doesn't hold for arbitrary theories, but it holds in quantum mechanics, in model of quantum mechanics. So therefore, if you take a proof of the Cauchy-Specker theorem, it's also a proof of Spekens' contextuality, because you can first prove the outcome determinism and then run the Cauchy-Specker line. Okay, so we recover those theorems. Again, I'm going to skip the proof because it's because I'm running a little low on time. Okay. The other thing you do is you get a much simpler proof of preparation contextuality, at least, right? So this is really the simplest contextuality proof you could possibly have. And it's a proof of preparation contextuality. So basically what you do is the CHSH experiment in time, right? So here are the qubits. This is the equator of the Bloch sphere. And you prepare one of these 4 states here. And then you do the measurements. So these are the basis vectors for the measurements. Okay, so if you consider the mixture of these 2 preparations and the mixture of those 2 preparations, they both correspond to the maximally mixed state. So those preparation procedures, I call them P plus and P minus because they correspond to the positive parity or the negative parity of those bits. But because they represent the same state in quantum mechanics, in a non-contextual model, you have to have, these are the probability distributions. I forgot to change the notation here. And these probability distributions must also satisfy the same thing. And so Stecken showed that that means that these must satisfy the following inequality. This is basically a sort of graph of the CHSH inequality in time. If you compute the quantum value for these states and measurements, you get a larger value. And so that's a proof of preparation contextuality, which is involves the smallest number of vectors you can have. So what have we achieved so far? So first of all, framework doesn't depend on quantum mechanics, just depends on the existence of operational equivalences. We're not assuming outcome determinism. However, we're still not experimentally testable yet. The reason is you're never going to make the exact preparations and measurements that you're targeting. Okay, not going to get exactly these preparations and measurements. Instead, we'll go here. Right. So if these are the probabilities that you're targeting, maybe you'll actually get something like that, right? With finite precision. So the operational equivalences that we based our proof on, which are these ones, aren't going to hold exactly among the preparations that we actually do. And if you don't have the operational equivalence, there's no argument, right? The other thing is that if you want to use preparation non-contextuality to justify outcome determinism, to do the Cauchy-Specker theorem robustly, then you basically need to try and experimentally verify that when you prepare psi and measure a basis that includes psi, then the probability is 1. And in any real experiment, that's not going to be exactly 1. And so you won't get outcome determinism for those measurements. So those are problems. So then there are different approaches to robustification. Here are some of the things you can do, right? So you have to change something. Okay, so one thing you can do is you can change the operational equivalences, right? And I'll show you that in a minute. To my mind, sort of from a foundational point of view, and this is true in approaches by Hussey and Marvian, slightly different approaches, this is the best thing to do. It doesn't change anything else about contextuality, but it changes the operational equivalences. However, from the point of view of applications, there are other approaches that have been proposed. And this one I'm calling intermediary, because it's just a thing that I came up with in a paper that we were doing, not because I think it's great, but because it's useful for proving the relationship between this one and this one. But anyway, so what you can do, you can give up the original operational equivalences and use something else, or you can invoke an assumption stronger than non-contextuality, right? So give yourself more power. The other thing you can do is you can start thinking about unphysical preparations. Don't think it's a great thing to do. That's why I don't like this one, but it turns out It's equivalent to this one. So let me just explain that a little bit. So you try and do these 4 preparations, but you actually end up doing these ones. Now, if I take a 50-50 mixture of these two and a 50-50 mixture of those two, they no longer correspond to the same point. Okay. Well, Puse's idea is to say, yeah, but look, there is a mixture of these two and a mixture of those two that are operationally equivalent. So use that instead, right? So why not use the operational equivalences that nature gives you as opposed to the ones that you presuppose? So what you do is you do the experiment to your best of your ability, and then you find P and Q, they're not going to be a half anymore, such that you have this operational equivalences. Note that you might say, but I did these preparations. Yes, you did, because you did these preparations, and these are just mixtures of them. So you have the data, the exact data for what you would have from those preparations already. You just compute it from your actually observed data. Okay, so well, then you need to derive a new inequality because you don't have the CHSH inequality anymore. Your operational equivalence is slightly different. You derive a new inequality and you show that it's violated. And that to me is like the conceptually simplest way of robustifying. By the way, I'm not going to explain the Marvian version because it involves more complicated kinds of measures and inequalities, but it's similar. Okay, should we change the operational equivalences though? I'd say yes, but unfortunately, it's going to it's not going to help you so much when you try to look at the applications of preparation contextuality. So for example, this is one of the applications. So it's called parity oblivious multiplex signals, again, proposed by Rob Speckens. So suppose Charlie generates 2 random bits, which he hands to Alice. Okay, so you have 2 bits, probability quarter each of them being like this. What Alice has to do is send a message to Bob, and we require that he gets no information about the parity of the bits. So he shouldn't be able to distinguish whether it's 0, 0 or 1, 1 from whether it's 0, 1 or 1, 0. The probability of guessing whether you're one of these two versus one of those two should be half exactly, which is just random guessing. Okay, then Charlie is going to ask, after getting the message, he's going to ask Bob to reveal one of the 2 bits. So with probability half, I'll say, tell me what the first bit is. Probability half, say, tell me what the second bit is. And classically, the success probability is 3/4 here. Optimal success probability, the reason is that you just send one of the bits. That's the optimal strategy, right? So if Charlie happens to ask for the bit that was sent, you'll always win, but if it's the other bit, it's 50-50. And you can show that greater than 3/4 requires preparation contextuality, and the quantum mechanics allows our friend 0.85, which you may recognize from the Bell inequality, with the same kind of value on CHSH. Okay, the problem here is like, okay, well, let me, in the inexact case, let me apply the Pusey method. Well, if I try to apply the Pusey method, then I have to say, well, after I finish this whole task, let's pretend that what Charlie really wanted to do was prepare these 4 bit strings with these probabilities, right? I can't change the task afterwards because I'm trying to do the task from the beginning. So it doesn't work for the applications. So this is what Chaturvedi Saha did. And by the way, there's an equivalent of this approach for measurement contextuality, which goes by the name contextuality by default. And some people are fond of that approach. So I think it's one of the reasons why this is worth considering here. So what you're going to do is say, well, we have approximate ontological equivalences. Sorry, we only have approximate operational equivalences, so we should only demand approximate ontological equivalences. So basically, you define some distance measure on your set of preparations. And then you define a distance measure on the set of probability measures. And you demand that if the preparations are close in some reasonable sense, then the probability distribution should be close in some sense. I'm not going to be specific about what these measures are, but this is the basic idea. So that's by far the easiest way to robustify a preparation contextuality proof. And this actually allows you to generalize the parity oblivious multiplexing to the case where you're allowed to leak a bit of the information. However, the problem is that you're not testing preparation on contextuality anymore. You're testing this stronger thing, which, is it justified? It's hard to say. The intermediate approach is kind of amusing. So what you can do is you say, okay, let's take each of my preparations and imagine that I prepare it by doing a mixture of a good preparation and a junk preparation. Okay, the point is that the good preparations should satisfy the operational equivalence exactly, but the junk preparations can be absolutely anything. Okay, so the idea here is, one way of thinking about this is, take these experimental results, and within the convex hull of these 4 points, try and draw a rectangle, right? Because if you draw a rectangle inside those, probabilities will satisfy the operational equivalence exactly. Now, then you have to take a convex combination with something else. And if you draw the largest possible rectangle here, then the junk preparations will end up being something outside the set of preparations you can perform. They may even be outside the set of quantum preparations. So that's why you may involve unphysical preparations. Okay. Okay, so you do that. So you find the largest possible value of P such that that's true. And then if you could physically implement all these preparations, of course, then the probability distribution for this guy has to be the same convex combination of these guys. So we'd need to be able to write this where for Q is equal to P. And if the model is also preparation on contextuality, it should satisfy this ontological equivalence. And then what you do is that you show these equations can only hold the smaller values of Q. So again, we don't throw out the standard notion of preparation on contextuality. That's good. Only use the original operational equivalences, but this thing will typically be unphysical. So arguably considering unphysical preparations is worse than the other deficiencies. But one of the reasons for introducing this is it turns out that we're going to get the same value here as you do in the distance measure approach. They're equivalent. And that's a useful mathematical stepping stone. Okay, but then the question is, well, does it even matter, right? Can't we just test all 4 of these in a single experiment and be done with it? So the question I posed is that if your experiment is good enough, can you infer that if one of these methods detects contextuality, then so will the others? So just do one of them, and then you know the others are also working. And so last year we published a paper showing that that's true, provided your errors aren't too big. So provided the probability of distinguishing P plus from P minus, the 2 operationally equivalent preparations, providing that probability is, so if you just guessed, the probability would be a half. So this value here quantifies how large your error is. So if you have a small enough error, then any one of these violations implies all the others. So you don't even need to decide which one you prefer. My collaborators have told me they've published the paper, they've improved the bound. I haven't seen the proof, so I'm assuming they're right. How much time do I have? I've gone over time. Oh, okay, so I'm going to, I want to just say that, I started off talking about measurement contextuality. We want to justify proofs of measurement contextuality as well. We know how to do that. So this is like work by Penrose and Merton showed that you can robustify these proofs by measuring the predictability of measurements given certain preparations. You basically do the measurements you have to do to establish the preparation on contextuality used to prove outcome determinism. So basically, you end up testing how close to getting this probability 1 when you prepare a state and then measure in that basis. And then you'll get some additional factors of your inequalities involving those predictabilities. And you can combine that with any of the 4 robustification techniques, combine those two together, and you'll get a way of robustifying the measurement contextuality. We have not found equivalence thresholds for these methods in the measurement case. I'd like to do that because people like to argue more about how to test measurement contextuality than they do preparation contextuality. Okay, I've gone over time, so I'm going to skip this section. This is just to say that this kind of contextuality has sort of become a workhorse of understanding non-classicality in all kinds of quantum phenomena. There's a list of papers there which do some of that. Should I skip? I want to do this because it's controversial. Okay. So generalizations. Okay. So what have we learned here? So there's arbitrarily many no-go theorems you could propose, right? What makes a good assumption for a no-go theorem? So the non-contextuality suggests the following idea, right? So let's find some property of your operational predictions of your theory that always holds, okay? Demand that the same property holds when you include lambda at the ontological level. Now, a good explanation for why that property holds operationally would be that it holds in every state of reality. Otherwise, we have a fine-tuning just like we did in the argument for non-contextuality. So really, this is the same kind of argument as we used to establish non-contextuality. So it suggests that generalization is a good thing to look at. So there are 2 frameworks which do this. It looks like Schmidt, Selby, and Speckens got there way earlier, but it took us 3 years to get this paper published, and theirs isn't published yet. So, well, they actually came out around the same time. They're slightly different frameworks because I'm trying very hard to avoid too many causal assumptions in here because I wanted to capture fine-tunings that have to do with time symmetry. But there's additional structure here that lets you do some more things. But anyway, roughly speaking, they both managed to encode that idea. But the problem is, von Neumann rears his ugly head, right? So what happens is if you adopt this notion, then you end up saying that von Neumann's no-go theorem for hidden variables is, right? Which is apparently we're not supposed to think that because we're supposed to, according to John Bell, it's not only false but foolish, right? So non-contextuality was supposed to be weaker than von Neumann's proof. But let me just briefly review how that goes, right? So suppose you have 3 Hermitian operators such that C is A plus B. Then it's true that the averages of the operational probabilities of those 3 quantities satisfy this equation. They do so for any state that you prepare, any density operator. Okay, now because this equation holds for all density operators, if we generalize non-contextuality in this kind of way, then we say, well, we should have the same equation when we condition on lambda. But recall that these are projective measurements, they're Hermitian operators, just ordinary projective measurements. So preparation on contextuality implies that all of these probabilities should be 0 or 1 because we have outcome determinism in that case. So now we have all these probabilities 0 and 1, and this equation holds. That's von Neumann's assumptions. Von Neumann's no-go theorem then tells you that this is violated. Should we be worried? But one thing to realize is that it's not really just von Neumann's proof, because if you really wanted to robustly implement an experiment of this, you couldn't just use this operational equivalence because your experiment won't give it to you exactly. You have to replace it with something else that's inferred from your experimental statistics. Also, you would have to include terms for all of the predictabilities where you attempt to prepare the eigenstate and then make a measurement in that basis. And that's not what you would normally do here. You'd need those terms in your resulting inequality. the resulting inequality would be a horrible monstrosity that would not look very much like von Neumann's proof at all and require you to measure far more things. So maybe it's okay, maybe we've somehow resurrected von Neumann in a way that's okay. By the way, I should say that the observations behind this, Rob Speckens had many years ago, but he, as far as I know, never talked about it in public. Maybe for obvious reasons, I don't know. So prospects. So this is basically the summary. So where do we go from here? So I think we've only just started talking about equivalence of robustification schemes. So there's more to be done on that. I think so this is about this whole list of things here, right? So it's a good way of producing paper to find something that people think is non-classical and then try and prove if it has something to do with contextuality or not, right? But you can't keep going at this forever. You want to sort of identify some common features, like the sort of minimal features that something has to have in order to be a proof of contextuality. And there are some ideas. A lot of it has to do with information trade-offs or uncertainties, right? So in our work, for example, on the uncertainty, qubit uncertainty relations, people often think, oh, uncertainty is a quantum thing. Necessity of uncertainty is a quantum thing. But in a non-contextual model, it turns out that you must have more uncertainty than you do in quantum mechanics. It's the other way around, right? So these kind of trade-off relations and the way they work in non-contextual theories is, I think, behind quite a few of those implications. Okay, and then finally, should we be worried about zombie von Neumann? Maybe I want some input from some of the philosophers on that question. So thank you.
You have about 4 minutes for questions. If you have a question, put your hand up. David Wallace.
I'm intrigued by your in preparation. Could you say a bit about how the Zeno effect connects to this?
Yeah, so the Zeno effect is, so let me tell you the background a bit, right? So Speckens, I and some collaborators have a paper about Mach-Zehnder interferometers, doing them with Speckens toy theory and showing that that's all nice and classical and non-contextual. So then they come to the question of what kinds of things in quantum interference are sort of genuinely non-classical. We have some other papers about that, but one thing that I always thought was that if you do interaction-free measurements, and you do the Zeno version of interaction-free measurement where you can boost the probability of, detecting the bomb without exploding it basically as high as you like, I thought that that'd probably be a proof of contextuality. So based on that, I started looking at the Zeno effect. And indeed, what you find is that if you want to be able the state to rotate to an orthogonal state in a finite time, then you can't have it freeze as well. There's the probability of it freezing is limited. I can't remember exactly what the bound is, but it can't be go to 1. So basically, that tells you can't do the interaction-free measurement with perfectly, right? So I think that's an interesting result, and yeah, I'm lighting up at the moment.
Thanks, Matt. Good talk. So obviously, as you mentioned, any violation of sort of a cognitive notion of non-contextuality, you can say is equivalent to a violation of Speckens' generalized notion of non-contextuality. But the reverse obviously isn't true. Right. Therefore, the kind of the set of Cockenspecker contextual scenarios is far smaller than this set of sort of Speckens generalized scenarios. I was just wondering, and linking again to this kind of the zombie von Neumann risk and things like that. Do you think that's a benefit of this approach, a disadvantage of this approach? I mean, given we're in a room with philosophers, do you think it maybe says something about the relative sort of validity or viability of looking in that kind of direction where you're doing this sort of underlying ontic assumption and probabilities and things like that versus things that maybe are more immediately contradictory and apparent? Sorry, that's a fair few different things I've just thrown at you there.
Yeah. So, I mean, so to some degree, since there are fewer of them, and since a Cauchy-Specker proof implies a Beckens proof, to some degree, those are like the strongest. That's the strongest kind of contextuality. But it's really just there's nothing you can do experimentally with it. I know that people say that there are other methods of testing it, but I
was proud to point you to chat section 4 of Padroni's review article. I think is the one where they go through all the methods. It's
most of those I don't buy most of them. Okay, that they're really testing contextuality anyway. But then, that's, as I say, this is controversial. This is one of the reasons for trying to do the robustification work, right? Try to gradually connect these things and maybe diffuse the controversy by showing that there's some degree of equivalence. That's the goal of doing that. But the ones that involve sequential measurements, I think they're pretty hopeless, to be honest. But that's anyway. Yeah. So I mean, it is a strong notion, but I mean, again, it's also fairly well motivated to some degree because everything seems to either be like in a theory type of approach, right, which is very classical in some ways, like it's just a kind of Hamiltonian mechanics with a restriction on what you can know, or contextual. I mean, I don't have proof that that's the case, but it seems that those are very closely related notions of classicality and non-classicality, and at least the existing in a classical theory with an epistemic restriction seems to be really well motivated. So to the extent that those two seem to be compatible with each other, I think it's a good notion. But yeah, I mean, obviously, we can debate about this for much longer. Yeah.
I'm afraid that's all the time that we have. Let's thank Matt again.
Cool.
We have a coffee and tea break now, and we'll be back in here 1/4 to the hour for a panel discussion.
Okay, I think we should get started. So welcome back, everyone, to this panel discussion. Our brief is rather broad, although we're told we should try and keep the discussion lively just to get the audience agitated. So you bounce up and down and get warmed up in case you're feeling a bit chilly. Brief is really to ask the question, what quantum? I've always been a bit concerned that quantum has changed from being an adjective to a noun. Quantum what? But essentially, it's to ask the panelists. I guess you know at least three of the panelists. So Guido, Elise, and Simon have all spoken today. Jos was chairing the first session. Anthony Valentini is giving a talk on Sunday. He regrets giving a talk, the first one after the conference dinner on Saturday evening, but at least he's here and you're all available to hear him this afternoon. But unlike most of you in the audience, unlike the rest of the panelists, I'm not a historian of science, nor am I a philosopher of physics. I'm a theoretical physicist. Somehow they've let me in to come and be involved in this conference. Certainly, when I was doing my PhD in the 1980s, it was in nuclear reaction theory. So we were told from day one, you go and buy the textbooks on quantum mechanics, the 2-volume books by Messier, Schiff, Mersbacher, and the usual. And you're told to, it was the shut up and calculate, which we had to do in order to get our PhDs. But almost secretly, with other grad students, we'd had to form what was called the Carlsberg Group for obvious reasons for Bohr's Institute's funding. But certainly our supervisors at that time, it was coming to the tail end of when foundations of quantum mechanics and philosophy of physics were seen as a career killer. Certainly, those, for example, Hugh Everett and David Bohm in the 50s, were that we still talk about their work now because it's very relevant and important. But back then, it wasn't the sort of thing that people talked about. And there were very few physicists, serious physicists, who were steeped in philosophy in the way that the early pioneers of quantum mechanics were. Maybe John Wheeler or Eugene Wigner, but not many others. Clearly, this has changed now. It's much more acceptable. So the idea of this panel is to ask how our views, what was discovered 100 years ago in physics that may or may not have changed our view of reality. And well, okay, or change physics, because our view of reality may not have changed. And since then, how much have we progressed, and are we in a better state now than we were, say, equivalent to the attendees at the Solvay 1927 conference? So I'm going to ask each of the panelists to give a brief statement, just a few minutes of where they stand on this issue. We'll have a discussion, and I want to make sure we leave enough time for the audience to be involved as well, to ask the panelists questions. So maybe we can start with you, Anthony, because we haven't heard from you today, to give your starting statement.
Thank you. It would have been helpful if I'd heard the purpose of the panel beforehand. I mean, what I have to say, I'm not sure how relevant it is. I've taken this as an opportunity to just make a couple of points that I think are relevant on this occasion. I was tempted to take this opportunity to explain my physical motivations for being interested in the pilot wave theory of Bohr and Bohm. It's always seemed to me that it provides an explanation for what I call the quantum conspiracy, that the world seems to be non-local, but we can't use the non-locality for practical signaling. And it explains that by viewing the Bohr rule as a state of statistical equilibrium. So this conspiracy is really just a feature of that state. Also find it interesting because then it offers the possibility of this new non-equilibrium physics with phenomena outside the domain of quantum mechanics. It also addresses, I think, important issues in cosmology, potentially in quantum gravity, so on and so forth. I could talk about that, but I'm not. That's 1 minute gone. I thought on this historic occasion, I'd like to make a point about the importance of history and of getting the history right. The question, I think the question, so I'm being relevant to the theme, which quantum is the title of the conference.
which quantum, what quantum, which quantum, what quantum, what quantum does one subscribe to or prefer or feel is compelling? Often depends, at least in part, on what history one subscribes to. For example, we seem to be celebrating Heisenberg's discovery of quantum mechanics in 1925, and that's why this conference is taking place in 2025. Well, one could argue that, well, why are we not celebrating de Broglie's discovery of quantum mechanics in 1923, and we should have had this conference 2 years ago? Now, well, it depends on, I mean, there is a line of thought that says that, look, de Broglie had a simple pilot wave theory for one particle in 1923. With Schrödinger's help, he constructed a many-body pilot wave theory presented in 1927. We know now that that reproduces quantum mechanics. This was independent of the work of Heisenberg and Bohr and so on. Why isn't that the discovery of quantum mechanics? Now, historical arguments do play a role in the way physicists view these things. I think we can't get away from that. History is important. The problem is, are we getting the history right? And I think this is particularly a problem among physicists. For example, Bohm was criticized for instance, by Heisenberg in the 50s for introducing the structure into quantum mechanics. Well, you could say that, well, actually, sorry, he was just putting back in what de Broglie had before Schrödinger got involved. And perhaps that structure should never have been removed in the first place. I have argued that, in fact, I would say that Schrödinger, when he took up de Broglie's ideas and removed the trajectories, that was a mistake that actually created the measurement problem. I would argue that. But look, my point here is not to argue about these specific points. The point I want to make is how much our view of quantum mechanics depends on the view we have of the history. And physicists in particular, I think, should try to do a better job of getting the history right. And I would say that the 3 superb talks that we had this morning show how hard it is to get the history right. That's supposed to be a compliment by how they say, okay, just how
one of those backhanded.
No. And I had some experience myself working with Guido on and off for 10 or 12 years on our book and finding so many mistakes also by major historians. History is hard. And perhaps I can end with a little anecdote, which you may have heard, about the historian and the brain surgeon discussing what they were going to do when they retire. And so the historian says to the brain surgeon, yeah, well, what are you going to do when you retire? And the brain surgeon says, I think I'm going to write a history of medicine. And then the brain surgeon turns to his and says, well, what are you going to do when you retire? And the historian says, I think I'll take up brain surgery. So I'll leave it there.
Thank you. Okay, so from one non-Copenhagenist to another.
Okay, yes. Well, if it's going to be pilot waves was the great discovery, then I'd have to say the Everett interpretation. But unfortunately, we're only in the 70th year or something. No, so my candidate is a bit framed on terms of my talk this morning, in fact, that I think the crucial discovery that was made that in a way carried almost everything with it is the discovery of a vector space structure to state space, and in particular that it be finitary or discrete structure anyway, replacing a smooth manifold by a countable, at most countably infinite vector space structure over the complex numbers. So I think one way that the reason I defend that point of view is because if you think abstractly what is physics mostly up until 100 years ago, it was looking at, well, this is one way to frame it, representations of a space-time group in terms of functions on manifolds. And basically all of classical mechanics and classical field theory fits into that category, either with the Poisson, well, usually the Poisson bracket structure, giving you the Lie brackets and so forth in the space-time group. Now, to do all of that, but not on a smooth manifold, but to do it on Hilbert space, a complex Hilbert space. It seems to me it captures most of what was fundamental, including complex numbers, Planck's constant, non-commutativity. All of those things come with that move. And if this is anything, if there's anything to this, the story I sketched this morning is the story of the discovery of that initially real, discrete structure to state space. And it doesn't come in the Wien regime. It doesn't come with the photon. It comes with the Rayleigh-Jeans regime. It is there that we see the evidence of discreteness, which is otherwise invisible. So it took us up to 25, and Einstein's discoveries, assisted by Bohr's, and a correct analysis of the Planck combinatorics expression. That Planck combinatorics expression in Dirac is just the dimensionality, finite volume, frequency range, dimensionality of the Hilbert space, the relevant Hilbert space. So it carries also that extraordinary story, because it was a beautiful. I didn't say it's not that I told it so beautifully, but it is a beautiful story. Planck comes to this. He has this expression. It's there in his 1900. 25 years later, people finally figured out what it meant. And that was the journey that, of course, took us also through to Schrödinger. Schrödinger wasn't aware that he was looking for representations of space-time groups on a complex vector space, but in fact, that's what he was doing with differentiable operators representing p squared and so forth, x. I think there's a case to be made. All right, that's said enough.
Okay, thanks, Alan.
Yeah. Well, Yes, I took the question a little bit more literally or historically. If you ask what quantum, if you look back at the 25 years before Heisenberg's paper, you first have a quantum of action in Planck. Then you've got a light quantum with Einstein 1905. And then he transplants it to the structure of the atom in his paper on specific heat. Bohr extends that and talks explicitly about the quantum rules for the energy states of a hydrogen atom. And then of course there's all these other players who play a magnificent role. But that's a lot of debate all the time about what is quantum. Is it something in the nature of light? Is it something in the absorption and emission of light by matter? Is it something about the structure of the atom? Is it something else altogether? There's all this confusion about what all these multitude of quantum phenomena, and people are still wondering about what exactly is quantum here. And I think one of Heisenberg's major breakthroughs is in his Umdeutung paper, where he says what we should do is generalize mechanics. It's actually a failure of classical mechanics, and what we should construct is a quantum analog of classical mechanics. So we only have to find out how to do that. Now that sort of settles the problem in a more or less definitive way. So from now on, it's quantum mechanics. It's a new theory of motion, and the kinematics and dynamics as well. And that's how the theory, and so it's much more general than just the theory of light or just the theory of atoms. It's the theory of motion that is quantum. I thought that was a breakthrough in Heisenberg's work. And Schrödinger, of course, strongly disagreed with him, but what he built is also a theory. And so that's what changed the route from 25 onward. Now, of course, there's a lot more developments later on, but let me just stick to making it.
Thank you. Okay, please.
What was the question again? What? Quantum? I think I'll just say a few brief things. The first is that, hopefully, as was illustrated a bit in some of the historical work done this morning already, is yeah, there is a convenient fiction in celebrating anniversaries of this kind, because really it's such a continuity of interesting ideas and I mean, for instance, even Heisenberg's reinterpretation paper of 1925 that we're ostensibly celebrating here. He'd been speaking about these things with Pauli for some time. And so we could use this as an excuse to celebrate the 100 years of everything for the next, long time, which would be great. Next year will be wave mechanics, 1927 will be the Solvay conference, whatever. We'll just keep the party going. Things I sort of from a contemporary perspective take away, and why I think it's a really fun time to be a philosopher of physics, is because looking at this history, you see a very rich and very nuanced spread of perspectives about how to interpret the experimental data, but how also to interpret the formalism. And it wasn't just epistemic and ontic. There were a suite of views in between, neo-Kantian views or more or less positivist views that were motivated by looking for space-time continuity or visualizability and all this. And I think we've lost that a little bit, at least in the philosophy community. We've lost that and have really become narrow about particular questions. But when you speak with physicists, and I was talking to Lucian a little bit about this a minute ago, what you even consider quantum or genuinely quantum phenomenon is disagreed on. And this word, and even how we employ the word entanglement, is being used at what counts as a real test for something being genuinely quantum mechanical. And we see in the history that mistakes about this. But we're making them now as well. And by we, I mean the physicists, not me. You got to risk something, faint hearts and so on. But it also means it's a time, if we learn from the history, that we can really be careful about, okay, when we're using terms like causality and terms like contextuality and terms like entanglement in a particular context, what do we really mean about that? And if we're clear about that, then maybe some of these conversations, as the technology increases, right? So at Helgoland, the big conference there were some fantastic talks on quantum metrology, and just the incredible degree of precision that is being seen is just meaning that we can ask in even more fine-tuned ways, what do these limits look like? I suspect the answer is going to be what I think it always has been, like the world just is quantum mechanical, get over it. There is no classical world. There's only something sort of emergent that looks classical and so on. But getting clear about these questions. For instance, when we talk about I don't like an absolute measurement, or what was the term used? I don't know what that means. I thought the lesson of quantum mechanics is that there is no such thing as an absolute anymore, and that's not the sense in which you all mean it. I'm just picking on you because we're friends, right? To be seen. I lost my train of thought after that. We can get precise about that, right? So Zurich and others who are working on quantum Darwinism are saying like there are plateaus in certain cases where if you're measuring devices of a certain scale, there's a amount of redundancy of the measurement out in the that can account for why we get intersubjective agreement of a certain degree. So we can get more precise about these claims, and yeah, I think that's it. Yeah, so it's a fun time to be an historian, but also thinking philosophically about these questions.
More to be done. Yes. Okay, Guido.
Well, I think that it's useful to reflect that we disagree now about what the crucial ingredient was in discovering quantum mechanics. The historical actors disagree even more, and well,
we don't quite realize how much they disagreed intellectually about what was going on. I mean, Heisenberg cordially hated Schrödinger's wave functions, and yeah, he really thought they were just a mathematical artifact. Sure, yeah, they're convenient for calculating transition probabilities, but what's out there? Transition probabilities and yeah, wave functions. You can use whatever wave functions work, give you the right answer. That's why he was so cavalier about the collapse or move in the cut, here and there. Heisenberg and Bohr, disagreed, heartily about, a number of things, famously in 1927, where's Ray? Yeah, there you are. It's Heisenberg, breaking out, crying, because when Bohr was criticizing, uncertainty, and yeah, you see, Bohr sort of embraces, certain aspects of waves. Superposition principle is really crucial and sort of complementary to other things. Heisenberg and Bohr disagree about how to think about the cuts and so on and so forth. And then yeah, von Neumann, Dirac, really believe in collapse as an objective, physical process, and all these guys in Copenhagen, Göttingen, it's not quite clear, or reject it. In Everett's collection works, there's some lovely notes, taken by Wheeler. I can't remember whether he was talking with Peterson or Stern, and one of Bohr's associates, and there's this little note. Bohr says, Wigner and von Neumann, all nonsense. They really sort of disagreed among themselves, what the crucial aspects were, and I think it's very useful to keep that in mind if we want to ask this kind of question.
Thank you. Yes, so they disagreed, and the disagreement is still continuing 100 years later. I guess that's a good thing. But I think, at least you're right, that this community will argue about in the meaning of non-locality, contextuality, what is entanglement, and so on. For the wider quantum physics community, what I find encouraging, there was, of course, you will probably all know there was the big survey done by Nature that was published back in the summer on interpretations. What the most encouraging thing, other than the whole suite of different interpretations, was that down near the bottom was only 2% of those surveyed thought that quantum mechanics wasn't in need of an interpretation. I find that very encouraging, even though we're not there yet. At least we should try. I always say, if you really are a dyed-in-the-wool operationist, Copenhagenist, and you don't care, then I'm going to call you an engineer. Right? Not a physicist, but though I suspect, John Bell probably would agree with that sentiment as well. But so before we come to the audience, maybe a few minutes of discussion amongst the panel. Can I just throw this out there? So we've the talks that we've heard so far today. The one word I didn't hear was decoherence. You did say it. Sorry, you did. Actually, you did. Okay.
Talk. I'm sorry.
Not in the talk. Okay. But we're thinking about how far we've come in 100 years. For me, as a physicist, I think work of Zay and Zurich and others who really developed decoherence theory in the 80s and 90s is hugely important. Not to mention the work by people like Bowman, Everett, 2 or 3 decades before them. So, if a physicist or a philosopher of physics were today to be transplanted back in 1927 in the Solvay conference, they would have a lot more to say on the subject, I believe, than the people there. And I sometimes get the impression that even among philosophers of physics, there's the feeling that you know, the debates that were happening 100 years ago by, you know, with Bohr and Heisenberg and Schrödinger and others, are still the debates that we're having now, but slightly more subtle and contextualized. Is that the case? I'm hoping you will disagree with me on that.
Well, can I just put in just a quick comment about what the founding fathers thought? You know, we ought to perhaps listen to that a bit. So it's hard to impute to Heisenberg the view that the fundamental discovery was non-commutativity. So that was the one thing he disliked about what he had achieved. So it's a bit of a hard one, but Dirac certainly plumped for that. Non-commutativity, Q numbers, that was the fundamental discovery that was made until 40 years later, he said, no, I don't think that anymore. I now think it's the transition amplitudes. So interesting reversal from Dirac. Bohr would say complementarity. I think Heisenberg might say the uncertainty principle. He may well say something like Pauli, I think, was on saying the uncertainty relations. Was he? Anyway, so does anyone else know? Guido, you, come on, other experts now.
For Schrödinger, it's certainly entanglement.
Entanglement for Schrödinger. Yeah. Yeah.
And I agree.
So
not straight away, not until after EPR.
Well,
during that year.
Well, Christoph Lehner and I just wrote a paper on it. Schrödinger was worrying about entanglement in 1926. Well, as were several others, but not as much. The others were probably not worried as much as Schrödinger was. And Schrödinger realized in November of that year that it meant that his whole interpretation of wave mechanics was untenable. And he writes as much to Bohr and several others. But it's only after the EPR paper that he published the thoughts that he had developed over these many years and coined a name for it, entanglement. But he also wrote that this was the characteristic trait of quantum theory that differed from classical modes of thought. So yes, it was very important for him, but it was at first he just thought it was an obstacle or it meant that his own interpretation of quantum mechanics was untenable. But later on, he started to realize that it was also a problem for the Copenhagen interpretation.
You know, one thing struck me, your question about, you know, where do we stand now compared with 1927? I mean, one thing I found striking, the work we did with Guido on the Solvay conference, is just how many of the essential worries and debates that we have today were already there. So, you know, you have a few examples. I mean, in the general discussion, there's a debate between Dirac and Heisenberg about whether does the collapse occur when an observer makes an observation, or does it just occur there microscopically? And Heisenberg is on the side of that it's the observer, and he gives an argument. I mean, I won't go into it. It's a simple argument, which is essentially a forerunner of Wheeler's delayed choice experiment. He has it's a photon emerging from an atom. You go this way, that way. He's got two mirrors and makes them interfere. And he says, you know, there can't have been a collapse back then at the atom because afterwards I can make them interfere. It's only when the observer, you know. Then you had, you know, some discussion about some results, I think, the structure of molecules using the exclusion principle. And you can see that people are worrying about what seemed like a sort of wholeness. And that was this compatible with relativity. And in fact, I think Einstein makes a comment, one of the few comments he made, you know, anyway, but the configuration space, if the arena of physics is configuration space, then there's a problem with non-locality. Of course, there was a lot of debate about de Broglie-Bohm theory, the reality of these trajectories. Dirac seemed to think, he had his interesting view that he felt that quantum numbers somehow reflected the free will of the experimenter. This is where the free will of the experimenter comes in. A whole lot of I was struck by really just how much of the essential points were already there, and it's often expressed very clearly and succinctly. And of course, the essence of the EPR argument is there in Einstein's contribution to the general discussion. He's got the particle hitting one slit and diffracting, and he argues on the basis of locality. Why don't I sometimes see a particle at different, two particles, one here and one there? But if the wave is spread out over the whole backstop, how do I, when I look at it, why do I see one particle just in one place? And he was arguing that de Broglie was right to have a trajectory. Anyway, there's so much there, and in a way, it's a bit depressing. You think, well, after 100 years,
but was Einstein back then, before in 27? Was he worried about locality, or was he still concerned about the uncertainty principle?
It was that argument was locality. In fact, Lucien, who's wakey Lucien, he's awake. Lucien has a paper, I think, in 1995.
We'll get the microphone round soon.
Formalizing how the Einstein's 1927 argument is formally the same as the EPR argument. You can make it
Einstein
logically the same.
Yeah, Einstein accepted the uncertainty relations as early as 1926. That's not what the issue is.
Okay.
But just on that same thing that Anthony was saying, I think you were quoting maybe the same correspondence in your talk with Pauli. Pauli's bothered by the notion of the state. Like, this doesn't seem like the kind of state when we talk about a state in classical theories. And this again is a valence in contemporary philosophy of physics. And how do we interpret the quantum state? Or maybe it's just assumed that this is the thing that we're interpreting. But whether or not we should even call it a state is questioned early on by Pauli and others.
To get back to Jim's comments, there is, so much more that we are talking about now, and different questions. I mean, we had a talk from Eric, we had a talk from Matt. The way we talk about non-locality now, since Bell, is completely different. Notion of contextuality, and the idea of distinguishing quantum theory not just from sort of classical theory, but sort of super quantum theories. So that's a sort of different kind of landscape in which we are asking questions and getting at least partial answers and getting insights about what quantum theory is. That has sort of transformed the debate in significant ways.
Can I just put in a vote also, though, for a rather old-fashioned view that it really is H? If we think of the Great Revolution in the 17th century, it was gravity with G. So we got a fundamental constant, and it came with an absolute revolutionary development of really the beginning of theoretical physics proper. So in the 19th century, it's C, Maxwell. Surely, huge, great, wonderful discovery. You could say K, Boltzmann's constant, stat me. 19th century, late, early 20th. And then comes H. There is a case that somehow H really is the signaler of a fundamental change in the world.
Simon and I are good friends, so he won't mind me digging.
Go on.
If we were in the physics lab at the Cavendish and we did an experiment, and you had plotted 3 or 4 data points, and then drew a curve through it and extrapolated a law from them, I think you'd get into trouble. And it seems.
You mean how does it first appear?
A lot of these kinds of arguments, and going back to this question, the importance of history. We often look back. I mean, it's inevitable. Sorry, Sammy. That we look back, we try to discern some sort of pattern that's going to hopefully be a guide to the future. What should we be doing? What is the future likely to hold? It's natural, and we do that, and fine. But think about what you're doing. You get people who say, like Pauli famously made a claim that, the future development of physics, psi is going to be this mysterious thing for centuries to come. as if you can somehow see centuries into the future on the basis of one or two data points. You know, as you've done, oh, there was a constant. There's this guy, and so what is the idea? Are you suggesting that for the rest of history, the development of physics is going to be there? Periodically, we're going to discover a new constant. There's going to be a revolution, and this is going to go on forever.
He's got you there, Simon. It's got you there, hasn't he?
I mean, but it's very common to try to draw these themes, and we all, I'm sure we all do it to an extent. But
I'm not sure. Is it possible? Are you sure there could be another fundamental constant?
Oh yeah, we've got
Not really sure anything. We've got all the constants we need.
You have Joule's constants, right? Which is completely forgotten because it's 4.2 Newton meters per calorie.
Yeah, but it's folded in with K.
Because
it's folded in with K.
Well, every physical constant can be made equal to unity by a proper adjustment of your natural units.
But that's part of the question about whether they could be. Anyway, look, I can see that my suggestion is don't go by anyone. So
I'll just throw one last question to see if anyone wants to take up before we go to the audience. That I would argue it's not Planck's constant or non-commutability or the uncertainty principle. What distinguishes what's new about quantum is entanglement. Entanglement is that concept in quantum world that doesn't exist classically, and we're beginning to appreciate just how prevalent it is, and how it underpins all the other. We've gone way beyond the split actions distance between two particles. Entanglement is what people working in even in quantum cosmology is what weaves reality together.
There are different notions.
You've already said that, had you?
Different notions of entanglement being used in different subfields as well. So, I mean,
some of them are misguided.
Yeah. So, but yeah.
Well, I mean, on that point, maybe it's useful to look at the history of quantum computation and how people have tried to argue or ask the question, what is it about quantum mechanics that makes quantum computers more powerful? Maybe we can take this as a kind of testing ground. Or, what is it about quantum mechanics? So, of course, in the early days, Deutsch would argue, well, it's superposition, parallel universes, so on and so on. And then, if I remember rightly, I think it was sometime in the early 90s, maybe people started saying, well, no, it's the tensor product structure, it's entanglement, and that's the really important point. And then there's been work, I think, when was this? 10 years ago, that it's contextuality. Contextuality provides, that's the real thing that drives it. And I think, some of the people I've spoken to in this field have said, well, it's probably the case if you ask today, what is it that makes quantum mechanics makes quantum computers more powerful? There's probably no one simple answer. And it might be that there's a lesson there, or if we're asking generally about, well, what is it about quantum mechanics that's different from classical physics? Maybe there is no one simple answer. There are various features play out.
Well, in the case of quantum computing, it's just money. They have
it. But I agree that it's a little value to ask questions like, what is quantum? What is really quantum about it? Because it's always a question that you should pose into a context. So what is the alternative? Are we comparing quantum theory with classical theory? Are we comparing quantum theory with even weirder theories, with the non-classical theories that admit superluminal signaling, for example, or theories that have quaternionic Hilbert spaces? So you should take these questions always in a context with a reference class. So what's the alternative?
So we've got about 20 minutes or just under now, so lots of hands going up. How many? Do we have another spare microphone?
Just got one.
Got one. Okay. Right. Okay. So let's in the front there, and then you can move back to Tim, and then it comes back up to the middle.
So, if I would make a distinction between classical and quantum, classical physics, every variable has definite value. Quantum does not, and this is Heisenberg 20. I think it's good.
Okay, good, thank you. No, it's a good.
In talking about what is quantum, I want to refer to work that Lucian Hardy did, which he was already, so I'm going to embarrass him again, because he said something which I thought was extremely profound and extremely counterintuitive at first sight, which is that the continuity of state space is the primal thing which distinguishes quantum mechanics from classical theory. So if you take a block sphere, it's a two-dimensional continuum. If you take a 2-qubit, it's a 6-dimensional continuum sphere. If you take 3 qubits, it's 14-dimensional continuum sphere. And the continuity of that, Lucian claims that this is one of his 5 axioms, and this was in his words, the most important of those 5 axioms. It's that continuity that gives quantum mechanics its properties. And so I'm going to slightly disagree with Simon that if you discretize state space, Hilbert space, if you have a discrete structure, you lose that continuity, and you no longer have quantum mechanics.
No, they can't.
I think you have an interesting theory of quantum physics, but it's not quantum mechanics. And in classical mechanics, although we have continuous, like might have the heat conduction equation, we know we can solve it on a computer discretizing it and get arbitrarily close to the continuum solution. So the continuum doesn't play a fundamental role in classical mechanics that it does in quantum mechanics. And that, for me, is actually the deepest of all of the properties of quantum mechanics.
Thank you. Did you want to respond quickly, Simon? Pass the microphone up 2 rows.
It's the continuity of the probability measure. That's what Lucian used. It's not the continuity of probability. The derivation was of Hilbert space, a discrete structure, a discrete state space. That was the derivation. But why we're arguing when Lucian is in the audience,
we're going to come to Lucian in a moment. Yes, that's it. Well, the microphone will make its way eventually to.
I'm not sure if it's. So there has been quite a lot of talk about the importance of history and getting the history right. And I think my question was really, what does it mean to get the history right? Is that even possible? A lot of the talks today were related to different kind of like aspects that have so far been mystified in the history of quantum mechanics. So, for instance, you take the fact that women have not been represented in the history of quantum mechanics. Epistemic results related to women's work have been mystified for decades. So, in a sense, what would it even mean? Is that even possible to get the history right? Aren't we just getting the history right in relation to some further question of interest always, and then it's constantly sort of reevaluated, reinterpreted, and so on. And, new evidence comes to light, and so on. Anyway, I'd be really interested to know more about that.
It is just a bit like Jim Cushing's book about how the Copenhagen hegemony. The Copenhagen got to the top of the hill before everyone else, and then there wasn't room for anyone else. So it's who's in charge, who writes the history. Who would like to comment?
I think if it's history that Guido has done, then it's correct. I suppose that I don't know who said that, but I suppose it was probably elliptical for something more careful, like doing better. Or realize that there are folks who are doing history with a lot of nuance, and you don't have to go and invent this history yourself in order to make some kind of physicsy point. Nor do you need to. Recovering some of these sources is getting both easier and harder, right? Because we are learning more about figures who have been intentionally, in some cases, written out of the history, but also harder in the sense that they're written out pretty immediately in some cases. And it's really strange. I mean, even de Broglie in his Solvay talk in 1927 says that Elsasser is the first one to say we should look for evidence of matter waves, but he himself had already done that in 1923 and 24. So yeah, maybe not about right and wrong so much as can we do it better than just Mickey Mouse, I guess is the term used. And sure, yes, of course we can.
Anthony?
Well, so I mean, this is I mean, it touches on a lot of very deep and difficult questions. I mean, you seem to be asking, in essence, is there such a thing as the correct through history? And this is something that people often question, generally just outside of physics. Some people think that so-called reality is some sort of historical and cultural construction, that it depends on perspective, it depends on interpretation. I think if you believe that there is an objective reality that science is trying to discover, then you have to believe that there is an objective history that we can find out about. Okay. That is. Yeah.
Actually, even possible because it's always the relation to always answer some other question. So to get the history right, you have to interpret it and contextualize it.
So you're saying, sorry, so you're suggesting it's not possible to be sure about the history of the past.
Well, it depends on the nature of the subject. Science is like that you will not really be able to, you'll be able to get some dates and some things right, but you will have to contextualize those because you're doing the history of the science in relation to something of interest.
Yes, and you're saying that colors your perspective. It colors your perspective, and therefore you're saying that different people with different interests will draw different conclusions about the past. No. Yeah.
No, I don't think you can get long facts right. You can get a lot of things. I think my point was more that you have to acknowledge the complexity of the interpretations and things like
Yeah.
acknowledge that complexity. So getting through the different points in it, different continuity.
Yeah. I mean, look, it is very difficult. I mean, history is very difficult, and it. I mean, I think what I was trying to get at is that there is a tendency for certainly the history of quantum physics to be talked about and summarized in ways that are clearly biased towards certain ideas or certain views about what is the correct way to do quantum mechanics, what's the real lesson of quantum mechanics, and all this. And it's surprising how often these
we're good friends, Wayne has been trying to get his question in.
Your point was really well made, but without the microphone, it's not going to be preserved for posterity. That's a good point. Yeah.
I just want to offer a thought on this question of what it is that makes the real difference between quantum mechanics and classical mechanics. So a moment ago, Kim, you said entanglement, and I think I would agree with you and Schrödinger on that. But then you also said it's not non-commutativity or uncertainty or something like that. And I think I would disagree with that. Because I think all of these things are being proposed, Planck's constant, non-commutativity, uncertainty, entanglement, superposition. I think that they're all aspects of the same thing. I mean, think about what entanglement is. Like if you restrict yourself, if I have a pure entangled state, it has to be that there are some variables that don't have definite values in that state, right? This is correlation between probabilities. If I have, if I restrict myself to some set of commuting variables, then the pure states of that are going to be product states, and what was said earlier, there won't be a continuous path through the pure state space of this. So I actually think that even like take any one of these and argue that the rest follow from that one.
Thank you. Yes, that's a good point. I mean, my point was, if we hear about quantum entanglement, would we be able to use the other properties of the quantum world, like non-commutability and contextuality and so on? Lucian, did you want to comment, or have people? Yes, the microphone's just behind you. People spoke on your behalf. I wasn't sure if you had more.
That's great. I enjoyed that. Yeah, I think I agree with what Wayne just said. I mean, it's good, and Simon's touched on this. It's good if you're going to say what's different about quantum theory, to say it in a language that doesn't use the mathematical apparatus of quantum theory. So if you can set up a more general framework and then say, we've got this principle or that principle, and that's what gives rise to quantum theory, then that certainly is a good thing. And then the kind of axiom that Tim mentioned, that there exists a continuous reversible transformation between any pair of pure states. All those concepts that I just mentioned can be stated in a more general framework and then applied to get quantum theory. So I think that's one route to take. I should add, of the various comments about what quantum theory is, the thing that I found most disturbing, in the sense that I think there must be some truth in it, but I don't know what to do about it, was Simon's statement that H bar is critical, because there's no H bar in entanglement, and there's no H bar in superposition, and there's no H bar in my reconstruction of quantum theory. And yet clearly there's something important about H bar.
I think Simon never divided by 2 pi. So
right, sorry. I'm sorry. Sorry for the 2 pi.
It's interesting to note, though, but that this approach, like starting from general theoretical framework and then finding out, like, this is a via negativa, like it's defining quantum theory in terms of what it cannot be, like by blocking off certain logical spaces, which is certainly, an acceptable way to ask about who God is, right? It's a via negativa, but it's not the only way. Via positiva.
Okay, James Lederman.
Thank you. I just want to mention an aspect of the history I think is important, and that's the fact that the boundary between physics and chemistry was very unclear during the development of quantum physics. And a lot of the confirmation, I think, that people took quantum mechanics to have came from its application to chemistry. So the Nobel citation for Planck mentions the determination of Avogadro's constant and the application of Planck's work to chemistry by Perrin and others. And then in the 20s, the introduction of various quantum numbers was done to account for spectra of atoms in a kind of empirically motivated way. And then we get Heitler in London. And I think this is really important to understand how much credence people were giving quantum mechanics because of its success in explaining the properties of matter as understood by chemists. And there was nothing like that at all in classical mechanics. There was sort of no application to the behavior of atoms from classical mechanics. And when Heitler in London come up with their explanation of the behavior of helium and hydrogen diatomic molecules, it's based on Heisenberg's resonance idea and symmetric and antisymmetric wave functions. And so I just sort of, 2 parts of my question. I mean, one is just to draw everyone's attention to the importance of chemistry for the confirmation of physics and the blurred lines between them. And the other is to sort of challenge to Anthony to say, is there really a plausible counterfactual history where all of that success that came from really not worrying at all about particles and trajectories, but just thinking about the operators, symmetrization, anti-symmetrization, ideas that were coming from Heisenberg and others, and that was what was successful. If people had taken De Broglie's picture seriously and really thought there was trajectories, can we plausibly think they would have been led to the results that they got by ignoring? I think you have to do more to show that there's a plausible counterfactual history than just point to the sort of abstract isomorphism between Bohr theory and quantum mechanics.
Well, I mean, just briefly, I mean, I think if people had been thinking more about the Broglie-Bohm from 1927, I think they would have quickly seen that it's a non-local theory, and the details of the trajectories cannot be measured for as long as you have the Bohr rule. And there would have been, I think, a pretty quick deduction that, look, as long as you have the Bohr rule, you can get by just without having to think about the details of the trajectories. The trajectories can at least give you a picture of maybe how you get an effective collapse of the wave function. but that's it. And I think if I'd been there, I would have said, look, it's telling us that we're stuck in a particular equilibrium state in which the details of the underlying physics are largely hidden. And that's a big conclusion to draw. It's telling you that quantum physics is just a special case of something much bigger. If instead we're just sticking to equilibrium and the Born rule, then I could agree that the Broglie theory can seem pretty pointless, apart from the point about solving the measurement problem. It doesn't really do much for you. I mean, to my mind, the theory is interesting because it's telling you that quantum physics is a special case of something much bigger. I hope that
Thank you.
answers.
Okay, we have time for probably two last quick questions. So there and then.
Yes.
Sorry, man.
Well, answers.
Thank you.
And answers. Answers will have to be even quicker.
Yes, I wanted to come back to the question of kind of what fundamentally is quantum about quantum mechanics, what distinguishes it from classical mechanics. There's been a lot of discussion of that here today. And I'm curious why we think that there ought to be a well-defined answer to that question at all. I can't quite shake the feeling that we're sitting here with an apple and an orange and asking what is fundamentally orange about the orange, and then
Paul Davis's question he got last night.
It's the citric acid inside, or it's the color. But really, is there much meaning to that? Is there any hope of an objective answer, or is it just kind of a question of what we prefer to think about as our favorite way of distinguishing fruits from each other?
Yes, I agree. I agree with that.
It reveals the extent to which classical intuitions are still driving our picture of physics. And so I think it's helpful for us to do sort of this conceptual analysis and get clearer about it. As long as we understand the game is not for somebody to win with like, this is the right thing to celebrate or whatever, but that it is to sort of press our intuitions.
Can we get the microphone down here for the last questions? Anyone else had a comment to make?
Just quick on the what quantum thing, because I was one of perhaps the person who came up with the suggestion. That the point was not somehow, the point is to different views of understanding, ways of understanding quantum mechanics will give different answers as to what that person thinks was fundamental. So you did come out with exactly what I thought you would, as to what was fundamentally discovered, and it would be in de Broglie, for example. Others, I think, so it fits. It fits. And it is revealing, and it perhaps gives new insights. If someone is committed to dynamical collapse, what for that person will be the fundamental thing that was discovered that was so new? Perhaps objective probability. Nobody's mentioned probability so far, but perhaps that would be the thing, and so forth. So it's an interesting interrogating the past from your own perspective, your own understanding. That's what I thought this question was about.
Thank you. It's a final question.
Yeah. I think there's some tension between two things that Jos said, which I think are both very, very suggestive. One thing you said was that what's special about the quantum is that it's a theory, not just about photons, not just about atoms. And the other thing you said was that what's distinctive about quantum theory is entanglement. I think Schrödinger, when he talked about entanglement in his 1935 paper, never said particles were entangled. He said things like knowledge are entangled. And he was focusing on the character of the quantum state. And that was his real focus in there. So it's characteristic of quantum theory that it's quantum states that are entangled. And that provoked him to think, well, what is a quantum state anyway, such that it can be entangled? And he himself was very sympathetic to the suggestion that a quantum state is a catalogue of expectations. It's not an ontological thing. It's not even an epistemological thing. It's a thing that guides you in forming wise expectations. And that seems to me to be a crucial move in quantum theory, to accept that view of the quantum state. That's something that evolved physically. In that sense, quantum theory is not a theory, but not a dynamical theory. But of course, it is its own way of being a theory because it gives you very wise advice about what to expect.
Okay. Well, when I said that in the beginning that what was discovered in 1925 was, or which was proposed in 1925 and which was novel at the time, but Heisenberg proposed a theory of mechanics. And I'm perfectly aware that entanglements, which I think is the most lasting contribution, or at least the most puzzling aspect of the resulting theory, came much later. I should, however, warn you that when Schrödinger writes his paper on the present situation in quantum mechanics in 1935, he's not presenting his own view. He's presenting what the community of theoreticians at the time would take to be the orthodox view on the theory. So that's mainly Copenhagen. And he says that in this theory, there's no proper notion of state, but there is something, he calls it the representative of the state. And that's this catalog of expectation. That's the thing that comes closest to the classical notion of state. But he's actually resistant of calling that a state, the wave function, because he has already seen that that's untenable. So that's not his own view that the quantum state does represent a catalog of expectation. He didn't solve all these problems. He was worried, but he didn't have a good answer to these questions at the time. But you're certainly right. Entanglement is something between wave functions, and not necessarily between particles.
In the Cambridge Proceedings paper, the entanglement paper, he says it's about when two systems interact. It's about the systems, the physical systems. It's not about their state descriptions only.
Schrodinger's view.
Schrödinger.
Yeah,
yes.
yeah. Okay. Yeah, I mean, until recently, in most of physics, we talked about systems, particles interacting. We said they're correlated, or their quantum states are correlated, because people use the word entanglement. Thankfully, that's now changing. Anyway, we've run out of time. I'm glad we've solved all the problems, foundations of quantum mechanics in this 1 hour. I didn't think we'd manage it, but we have, so it's fantastic. Please join me in thanking our panelists for a very illuminating discussion. Thank you, everyone. Now, Chris, you can tell me how much of it, do we have a break? We have no break, so we're moving straight on to Roger Penrose. So Roger's been sitting patiently in the wings. So I don't know how long it's going to take you to step up, but we might as well start. So thank you.
you're in full view of the audience anyway, so I don't think it'll be. Pretty much at once, as soon as people settle. I was just wondering if you found a route. Fine. Yeah, there is. So if you go out this door, let me. Okay, ladies and gentlemen, I think we're running a few minutes late, but I'm sure that's fine. Okay, so the final talk of the day falls to Sir Roger Penrose. Roger needs no introduction, I'm sure. And the sooner I shut up, the sooner he can start. You may need to sit down at some point during the talk, but we'll leave that to you to decide. So, Roger Penrose.
Thank you very much. Well, I can hope that I can do this conference justice. Let me make sure I can move things backwards and forwards. Here you see the title, which I think is correct. Now, here we have the superposition principle, which is very basic to quantum mechanics. If you have a state A and a state B, then you can form these linear combinations of A and B. Well, that's all very beautiful and nice and simple, so it seems. The only trouble is if you think of A and B as being something big, like a rock or something like that, then it means, let's say, you could have a rock here, and that same rock can be over there, and therefore you have states where the rock is here and there at the same time. And of course, this is very familiar to people, but it's the problem I want to talk about. Why don't we find rocks like that? And it's a point of view which I've had for quite a long time. It's developed in certain ways, and quite crucially in a particular way, which is what I want to get to at the end of the talk, which has to do with the title. Okay, now let's see if I can get this thing to move consistently. No, I can't. I thought I did what I was told to do, but I didn't, evidently. I pressed the wrong button.
Probably there's one that's probably blank.
That's it. No, I'm bound to press the wrong button. That's one of the things I do these days.
Well, I'm not helping much, am I, either?
I'm supposed to press the one with the arrow.
It is moving, it's just slow. Is that the next one, or have you jumped?
It looks about right, yes. Yes, the problem is what's referred to sometimes as quantum measurement. I suppose it's because somebody comes, maybe there was a rock in two places at once, and then somebody comes and measures to see whether it's here or over there or something like that. That's why it's called the measurement problem. I prefer to call it wave function collapse, because the state, which was originally in two places at once, somehow isn't in two places at once. And there is a conventional argument for this, which is very clever argument by these very clever people. John von Neumann and Landau, I think it says, I hope that's right. The idea was that if you have a state and you try to put it in one place or another, the state that you really have is much more complicated than that, because there is this horrible environment all around, and you have to take the environment into consideration, which is absolutely correct. Of course you do. And why is or is it not important? Anyway, the question, I've got this environmental decoherence. The argument is that when you take the environment into consideration, then it solves the problem. And there is a famous, very clever argument that's said by von Neumann and people. And the idea is that you say, well, the environment gets involved, the system is unbelievably complicated, there's no way you can keep track of the thing like that, so why don't you do this clever thing, is constructing a density matrix. The density matrix averages out from all the environment stuff, and it gives you a thing. And then you look at the density matrix in the right frame, and you see it's diagonal, and you see those diagonals terms give you probabilities. It's a very clever argument. The only trouble is, as far as I'm concerned, is that you have a double, what I call a double ontology shift. Your original ontology somehow is that the wave function describes reality, and then you shift your ontology to say the wave function is described by a density matrix. And when you have that ontology, you have the freedom to change your reference system until it becomes diagonal, and then you flip back into the other ontology, and you say those diagonal elements represent probabilities. So it's not really a consistent argument, because the argument, as it describes the world, the ontology of the system, is not consistent throughout the argument. And it does involve, what I say, a double ontology shift. So I don't think it really resolves the problem, even though it's a clever argument. And it has a lot of merits to it, but it's not the answer. The other alternative I've written down here is many worlds. Now, my attitude to many worlds is that it's a good thing, if you want to study quantum mechanics, to have believed in the many worlds at some stage in your life. The shorter, the better. Now, I hope I'm not being too rude to people here. But that is my view. The shorter, the better. I think it was a couple of months in my case. I can't remember how long I believed in, which I consider to be rather too long, but never mind. Anyway, that's all I can say about many worlds. I don't think it resolves the problem, because why don't we see all the many worlds and all that stuff? So let's not go into that, because I think the argument is much more what you could call down to earth, or to do with reality in some sense. Now, one way of solving this problem is to change the subject. So that's what I'm going to do. I'm going to change the subject, and that's press the wrong button, which is a good way of changing the subject. Let's come back again. That was clever me. I found a way to bring it back. Okay, how about that? I'm going to change the subject to general relativity. We're going to talk about the foundation of general relativity, and at the top we have Galileo, or one of his, somebody or other, so it's just a theoretical Galileo, sitting up there, leading Tower of Pisa, and dropping a big rock and a little rock. Of course, we know that they wouldn't drop the same rate because of air resistance. Galileo knew that too. He was absolutely clear that was the case. And there was this experiment, wasn't there, down on the moon, wasn't there, when there was no air resistance, and the chap dropped a rock and a feather, and they just went down together, as Galileo said they would. Well, we know that. Principle of equivalence also tells you we have a rather futuristic 2001 type spaceship and an astronaut there. And the astronaut, of course, doesn't feel the Earth, even though it's right there in the picture, because the astronaut is falling freely under gravity. And if you fall freely under gravity, you don't feel the gravitational field, as we all know. Anyway, that is the principle of equivalence. You can say it's got to do with the passive mass equal to the the passive gravitational mass is equal to the inertial mass. That's sort of a Newtonian way of saying it, which just looks like an equation which might or might not be true. But it's the absolute basis of Einstein's general theory of relativity. And of course, it resolves the problem. That's what general relativity does. You can say in Pisa, you could get rid of the gravitational field by dropping freely. It doesn't get rid of it in New York at the same time. You have a problem because it's not constant. And the direction of the gravitational field it varies as you go from place to place. And that was the basis of Einstein's incredible theory of general relativity. Okay. Now, this picture, I want to consider an experiment on a tabletop. You can see the tabletop there at the top. And you're going to consider, you're doing an experiment. And for this experiment, you want to include the Earth's gravitational field. Now, there's the sensible way that any physicist would do, let's say, experimental physicist, I don't mean a theoretical physicist, experimental person would do. They just put a term in the Hamiltonians to take care of the gravitational field and plug along. But then you could say, noticing Einstein sitting in the corner, peering at you, and you realize, oh no, there isn't a gravitational force, you could drop freely. I think it's the difference between the green coordinates and the purple ones. I think the green ones are the ones that the sensible physicists would use, putting a term in the Hamiltonian, and the purple one is the free fall one where the gravitational field is disappearing. And that's fine. It's just the wave function, which you've got here, a purple wave function, the green wave function, and you see there's this rather peculiar term in the middle involving the exponential of cube of the time. Have I gone backwards? No, we didn't show this one before. Okay. Oh, yes. Sorry, yes, I know what it says now. Sorry, at my age, I keep forgetting things. This is the title of a paper which I was one of the authors of, and I'm guiding you to that paper because what I'm going to say in the next few minutes is explained in that paper in much more detail than anywhere else I know. So that's really the point. I'm putting that slide up. I should put the appropriate pages up and all that stuff. I'm not going to do that. And here's the picture, which tells you, if you see this picture, you know you've got the right article. I also have this picture in my book, Passion, Faith, and Fantasy, and the New Physics of the Universe. And that's a guide to telling you at the right place in the book. It's just rather a fanciful looking experiment. That's all. Don't worry about it. Pure fancy. Okay. Now, this is the transformation. The little coordinates, I think, are the ones in the lab frame, and the big ones are the ones, the freely falling ones. And you just have this simple relationship. The time is the same in both. And I'm not doing relativity here. It's just Newtonian type theory. And the capital letter, the position vector is the capital R in the freely falling frame and the little r on the other one. And then you have the acceleration is the A. And T, of course, is the time. Now, this is this formula written again here. And you see this exponential of the term with the T cubed in it. Now, what I'm saying is to ask, well, you see, this is the term which comes from looking at it. The right-hand one is the lab one, and the left-hand one is looking at the freely falling frame. There was an experiment done recently which actually observes this T-cube plane, this by Ron Fullman and various other authors, one of which was me in the paper. I have nothing to do with the experiment. I didn't understand a word of it, but the theoretical end of it did have something to do with it. And the paper, I'm not sure whether it's got accepted yet. It's had a bit of trouble getting accepted. Anyway, that's not the important point I want to make here, except that the T-cube term is the point I will talk about. And the trouble is my eyesight is so bad these days I can't even read my own print. Perhaps it would be a good idea for somebody to read it for me, just so I can.
For a large, massive gravitating body, we put into superposition of two different locations. We obtain a quantity EG, which can be interpreted as an uncertainty in the energy of the entire system.
Exactly. Thank you. The EEG, I did put it in red, and I can't see whether it's red or not. It is in red. Gosh, it's amazing. My eyesight can't just even see it's in red. That's poor. Never mind. Yes, the whole point is that EG is the thing I want to talk about, E sub G. And you find that EG is, if you try to use the Newtonian perspective, which I call it, if I'm just putting a term in the Hamiltonian, and you want to say, well, this isn't really right. The right way is the other way, the Einsteinian way, if you like. And if you have a superposition, you have problem because you can't do both at once. So what you do is you cheat, as any good theoretical physicist would do. You cheat, and you just. But the point is that you keep track of your little cheat. You know you've done it the wrong way. You should do it the Einsteinian way. But if you do it the other way, you keep track of the little cheat, and you integrate the cheat over the whole of space, and you then get a total thing which you can regard. Okay, this is a little bit of an uncertainty in the actual energy, but you get an uncertainty in the energy, and this uncertainty in the energy is this thing EG. And the argument is that this uncertainty in the energy is related to a time scale, according to the Heisenberg time-energy relationship, so that the smaller EG is, the longer it lasts, the bigger it is, the shorter it lasts. And it's compared with, say, an unstable nucleus, where you certainly have this phenomenon that the half-life of the unstable nucleus is inversely related to an uncertainty in the mass of the system. And this is what I'm taking advantage of, but in a different context. That's the idea. Okay, so it tells you that the system has a lifetime, and that lifetime is measured by H cross over. Incidentally, I heard people talking about H bar. I know Iraq always called it H cross. For some reason, it just converted into H bar. I think H is bar with the thing with a bar on the top. I don't know. Never mind. H cross is what I'm going to call it. And so I think I see it up there. Oh, there's a horrible little T, which I forgot to wipe off when I was trying to make my slides to work. And I'm afraid, forget the little T at the top on the right-hand side. It's not there. Okay. Now this thing EG then is this, the reciprocal of it basically gives you the lifetime. Yes, I think that's all I'm saying here, isn't it? It's like the Heisenberg. Is that what it says? You'll have to see if it says more or less that, that's fine. If it doesn't, shout. Okay, so it does. I'll move it forwards. This, I should say, that when I found this lifetime some years ago, sort of the late 1990s, I think, I was reminded by somebody that Dioschi had already found this formula about 2 years earlier, which is fine. So I'm going to call it the Dioschi lifetime. It is, he did it first, so it's his lifetime. That's fine. Okay, and I have written down here more or less what I just said. I think that if you have a superposition and you find that there is this, because of the gravitational aspects of the thing, and you're doing it, say, using the Newtonian perspective when you should be using the Einsteinian perspective, and you take account of the error in doing this, integrate that over the space, do an integral by parts and fiddle around with the mathematics a bit, As I say, if you want the details, look at the paper I just showed you. I'm not going to talk about the details here. I'm talking about the general conclusion. And we find that there is this lifetime, which is basically the reciprocal of the EG thing, which is this energy uncertainty of the system. Okay, it's the Dioschi thing. And here we have the formula. The lifetime is H cross over E sub G. It's a twiddly sign, which may be that means there's an unknown constant there. Of course, it could be that it's 16 pi cubed or something like that, which is not so trivial. But I'm assuming it's about 1. So the lifetime of the system is given by this formula. Okay, that's the fundamental formula. So it's only the only thing on the slide. So you can make, and the twiddle means we're not quite sure whether there's a factor there, which might be fairly different from 1, but I hope it's not too different. Okay. Now here's a little calculation I did once. I'm just showing it really to show that I could do calculations once. And the calculation here is you're looking at a sphere which is made of a uniform material, and you're working out what the EG is, moving that sphere. That's to say the state is the superposition of that sphere and a slightly displaced sphere. And the distance you displace it is given by lambda, where lambda is also 1 is when they're just in contact. So you have one formula when they're not quite in contact, and then when they're overlapping, and then the other ones when they're separated. And that formula gives you the EG. As I say, just to show you, I could do calculations once in my life. I think it's the correct formula for this thing. Now, people here may know that there was an experiment performed several years ago. Not too many years ago now. It was called Gran Sasso. I think that's the name of a mountain or something. And the experiment was done to test a prediction made by Dioschi, which was that basically the idea is if you have a body and you're not looking at that body just as a simple rigid thing there are lots of atoms and molecules and things that start running around. And you have to worry that every now and again there's going to be a collapse taking place in that system. If the quantum system, it will collapse from moment to moment. And this collapse is sort of random over the whole thing. And it means that you have a superposition which jumps to one or the other. So the evolution is a little bit jumpy. And this jumping over the whole system will cause a heating. So the body will spontaneously heat because of this jumping of the state, superpositions to one or the other. And this is happening all the time. And so the body somehow produces this energy of apparently these motions which are apparently happening in the system. And this experiment was done to test whether this heating took place. I was always very suspicious of the heating. It seemed to me that it might play havoc with astronomical bodies whose motions are tracked very, very accurately. And if anything was telling you that the body was getting more massive, hard to believe we wouldn't see this in these experiments. So I found it hard to believe that this was the case. And I want to explain what my point of view was too, why I believed that it didn't heat. It's different from the Dioschi scheme. You need something different because if you had the Dioschi scheme, you would get this heating, which you don't get. I'm still calling it the Dioschi lifetime because that's part of the scheme I want to talk to you about, but it is not the model which I want to talk to you about. So let me move forwards. As I say, sometimes it's a good thing to change the subject. I'm changing the subject, and the subject here is special relativity, basically. So this is a space-time picture with time going up the picture, and we have the thick line is a body, and this body is split into two parts. Sorry, I hope I'm saying it right. The body becomes put into a superposition of two locations. That's what I'm saying. Somehow, you bonk it with something which is quantum thing, And so it's put into a superposition of two locations. And as you go up the picture, the dotted line or the dashed line represents the history of the one branch of the body and of the other branch. So it's split into two, quantum superposition of the left-hand dashed line and the right-hand dashed line. And then one of them disappears. That's the open spot. That's what I call Q. And the other one becomes the whole state. It now becomes a decline. So it's the entire state. So the collapse has happened. So that would be the picture of a collapse taking place when the body moves substantially. That is, the two parts of the body move away from each other. And you're considering a situation like that. Now, I want to consider that from the perspective of two different observers. There's the P, curly T, and curly S. And the curly S one is for an observer moving rapidly, very, very high speed, comparable with the speed of light, a little bit less, to the left, right to left, I think. And so the simultaneity surfaces are these lines, the various, this is the observer S, I guess, moving to the left. And you see the sloping lines are the simultaneity lines for that observer. And according to that observer, the system behaves very peculiarly, because when you go up, it's a superposition of two locations, and then one of them becomes the whole state before the other one has disappeared, you see. That's for the one moving this way. And that means that the one that had disappeared still has a probability of becoming there. So somehow it's become a possibility of becoming two states. Well, probability, I should say, of becoming two states. That doesn't make any sense. It's even worse for the observer T moving very fast to the right, and then you see the simultaneity lines are sloping up that way, and the one of them has already disappeared by the time that the other one still has a probability of disappearing. So the whole body might just vanish, and that doesn't make any sense. I'm trying to indicate with this picture that it doesn't make any sense to say that you have a superposition of two world lines of the body, because when you get to these observers, you can't make sense of it. There is a point of view, I remember I used to worry about. Philip Pearl was one of the people involved, where the collapse is really described by the amplitudes changing with time, and one of them increases while the other one decreases. And if they don't know much about each other, which they shouldn't, if this is like a relativistic picture, then you have trouble keeping the norm constant. So you say, well, don't worry about that. Just look at the ratios between the squares of these amplitudes, and that should give you the probability that you want. It doesn't actually work even then, because for one thing, that it's nothing like what I'm saying the probability, the decay should be like. It's like an unstable nucleus, and the unstable nucleus has a lifetime, and this lifetime does not depend on time. It's a fixed thing. If you haven't seen the decay in an hour, then you still have a same expected lifetime for that system. The fact that it hasn't decayed yet doesn't mean that the lifetime changes. The lifetime is invariant. If it's gone, of course it's gone. But if it hasn't gone yet, you still have the same expected lifetime. And that picture doesn't agree with what I was just saying. You take the view that these amplitudes are what one of them gets much bigger than the other, and so in effect the collapse has happened. I had another much more complicated argument against it. It really doesn't work in the scheme, because of things like this: relativistic picture, special relativity, doesn't give you a sensible answer. Okay, so how do you make this sensible? The only way to make it sensible, as far as I can see, is to say that the reality was really all the time, even though the one had disappeared right up there at this point Q, the one at Q star, becoming the whole state, was the whole state in a sense all the time. So even though the collapse took a while to happen, it was as though the collapse had been determined in a certain sense right at the beginning. So the reality of the whole branch the collapse doesn't just give you the collapse at the end, it tells you the whole branch right from the bifurcation point here, right to where the observation, which isn't an observation, the collapse happens, that thing has now become the whole reality. Does that make any sense? Well, I'm trying to argue that it does make sense, and that's what I'm going to try to argue for. Let me move on. I hope I can do it without messing this up again. No, pressing the wrong button. Here we are. This is a sort of version of the same picture in a sense. It's from an article I wrote some years ago. At the bottom of the time is sort of going up more or less upwards. At the bottom of the picture, you have a laser which has fired a high energy photon at a beam splitter or half silvered mirror, whatever you like to call it. And one branch of the photon goes down, the other one goes horizontally and hits this little, like a dust or whatever it is, little tiny body. And as it hits the body, it gives it an impact. And since this is in a superposition of taking place and not taking place, then the body starts to move or starts not to move. And as you go up the picture, I'm saying the body is in superposition in two places at once as you go up the picture. And by the time finally the collapse happens, and that the quantum reality is indicated by the swirly line at the top, the quantum reality says that this thing has disappeared, but the classical reality follows the route of the space-time right from the branching point, and it goes right down to the beginning, and the whole reality, say it's the space-time picture I have is that the space-time is a sort of continuous thing. It doesn't break off in this way. It's a continuous thing, and it has to go back to the origin point to make sense. Okay, so that is the picture I'm having, and I get what the next slide is, but let me see. Yes, this is really talking. I have talked about these two terms, classical reality and quantum reality, without explaining the key difference. The key difference between classical reality and quantum reality is that classical reality, you can ask the state and say, hello state, hello system, what is your state? And the system can say, my state is X. It might be like this glass or something like this. And you see, it's a classical object, and it would say, yes, I've got a circle at the top, and I'm more or less cylindrical here, and then I thin down at the bottom, and I have a flat bottom. See, so it's nice description. It gives you classical reality is something you say, hello state, or hello system, what is your state? And it says, my state is X. That's fine. Quantum reality, you can't do that. Well, you can do it, but it looks at you blankly and says, I don't answer questions like that. You say, what is your state? As I say, it looks at you blankly. But if you have a more different kind of question, you can say, I have an idea your state might be X by now. Hello, state. Is your state X by any chance? And then if you get it right, it will say yes with certainty. So that's what quantum reality sort of distinguishes it from classical reality. It has this thing you can't ascertain. I like to use the words, you see. Quantum reality, classical reality you can ascertain by an observation. Quantum reality you can confirm. You can't ascertain it, you can confirm it. And the condition for confirming is really a statement due to Einstein. And he made this statement like this, Einstein, what I'm calling Einstein's dictum. He didn't call it quantum reality, but this is really my criterion, quantum reality. And he says, if you can perform an experiment on the system, which does not disturb the system, and the experiment with certainty will give you an answer yes, say, then that state of yesness about the system is real. What I'm saying, it's quantum real. I think Einstein was addressing the issue of whether the wave function is in some sense real. It's as complex as we all know, but that's not the point. Is it real? Is it really there? Or is it some kind of fiction? And he was trying to argue it's really there in a sense. The argument he was using is a quantum reality argument. So you might have some system where you know by now, let's take a spin half particle. That's a good example. I always like spin half particles. You can say, see, the spin state might be pointing any direction. You might say, in classical reality, if it was a classical reality, you could say, hello, spin state, which way are you pointing? And it would say, I'm pointing this way. But quantum reality, you have to make up your mind which direction to choose. And if you have, in this experiment, you set it up, you have good reason to believe that it should be spinning this way. I say right-handed, I shouldn't be right-handed. About that direction, that's what I mean by that way. Right-handed about that direction. And then it will say, if I got it right, yes, with certainty. You do the experiments 100 times, it's a yes every time. That means, gives it an element of reality. I'm just inserting the word quantum reality. It's an element of quantum reality. You can't ascertain which way that spin is pointing. There's no experiment that can do that. What you can do is you confirm it. You can say, if my experiment should by now have said that it's spinning that way, then I can do this experiment to confirm that. Every time gives you the answer yes, without disturbing it. At Einstein's criterion, I'm adopting that, but I'm inserting the word quantum reality. Okay, now let me move on from there. And I want to consider this picture. This picture is an EPR situation. I have at the beginning, time is going up the picture, and I have Alice and Bob, they're space travelers or whatever it is, and they are each given a spin half particle in a sealed box. And the particle was originally in the spin 0 state and split into 2 spin half states. So Alice is given one in her box, and Bob is given the other in his box. And they're not allowed to look. If they look, it ruins the experiment. They just sit there with the box. And after a long time, when they're a good distance away from each other, Alice decides to look at her particle, and she chooses the direction in this picture up to the right, and the particle says, no, you got it wrong. And that measurement makes it spinning down to the left. Yes, to the left slightly. You see where the arrow is pointing. I can't say it really this way. But you see the way it's spinning in the opposite way to the way she tried to measure it. Now, when does Bob's state become the opposite of that state? It has to be the opposite. But if he happened to measure it, he didn't know which direction Alice has chosen, of course, because that's the idea. He measures the direction of the spin he's chosen, and we know that if he had chosen the opposite direction from Alice, he would have got the answer, well, the state would be the opposite of Alice's, and so since Alice happened to have got it wrong in this case, it happens to be the way that Alice's one is pointing. So that is Bob's state. But when does that happen? When does his state become certainly the opposite of Alice's? Well, that's the curious thing, you see, because you could imagine this picture drawn by observers moving rapidly in either direction, approaching the speed of light. So what you have to say is that Bob's state has to be, by the time the past light cone, you see Alice's point up there, you measure her past light cone, it intersects Bob's world line, and at that point, it suddenly becomes the opposite of hers. You might say, well, a load of nonsense, mightn't you? Well, I'm not saying it's not a load of nonsense. I'm sort of saying that is what quantum reality does. Now, you see, it would be terrible if you could ascertain what the state was. If Bob could, the hello state, which way are you pointing? And it gives you the answer. That would wreck everything. The whole point is that he can't do that. You can only choose a direction and see whether he got it right or not. It seems a bit of a stretch of the imagination that somehow his box has got a state which must have already, retrocausally in a certain sense, become the opposite of what, well, the same as how his state is measured. Imagined her state was, she got it wrong, and so it was the opposite of hers, and therefore Bob's state would be in the direction that Alice had chosen to measure. But that happens in this curious retrocausal way. It's not causal in a sense that you could send a message. See, people don't like retrocausal. They say, no, you can't have things going backwards in time or past light cones and all that stuff. But I'm saying, if it's quantum reality, you have to do that. You have to allow that. But it's not a kind of reality, as I say, quantum reality, you can't ask, you can ask the state which way you're pointing if you like, but it's no good. That's not the kind of measurement you can make. You can choose a direction and say, is your state, does it happen to be spinning that way? And if you got it right, it says yes. It takes a little while to get your mind around to see that this doesn't give you problems with causality. You can't send signals faster than light. You can send quantum reality faster than light, but that's not a signal in the ordinary sense. It does have sort of secondary implications, such as things like Bell's inequality, and other things which may be or may not be important. One doesn't know. I think it is important, but it's not ordinary kind of reality. There's something funny going on here. And I think that's probably the last slide. Let me check. It is the last slide. Yes. Thank you very much.
Thank you very much, Roger. Okay, we have time for questions. So do we have a?
Somebody should point to the question, maybe.
To pass it to the left behind you then for the first question. Then.
Thank you, Roger. You presented two stories. One story when you have this one dust particle which was hit by a photon in a superposition, and so you have two lines.
Yeah.
And then you answer my question, which I wanted to ask before, because in GRW we know what's happening when there is a collapse. There is a tail, and there is a small thing on the other part. And you said no, it doesn't work. In this case, it's only go on one part. This is what I understood. You said that it will go if the dust. There are two options. If it's go on one.
That's classical reality. Yeah. I'm sorry.
This is classical, or but
which picture are you referring to?
But then you considered similar thing about EPR.
Yes.
And then you said it's happened on a past light cone.
Maybe I could get back if I can.
Yes. So here
sure.
it's a past light cone.
That's it. Yes.
But the previous one, you said if you go before, or with
but that's because I hadn't even been considering really the speed of. Well, I'd have to remind myself what that picture showed.
Here it's a past line cone, but in the previous one.
Have I got the right picture?
Yes. That one. Yes. Yeah. Yes.
That one.
Like here. Yes. And here you said it's made it at the splitting point, not in the not in the past. You could do the same here. It looks like.
You could. I mean, you could have a classical situation, which there's a black ball and a white ball, and somebody comes and gives. You say, Alice is given in the sealed box, one or the other. Bob is given in the sealed box, one or the other. And this is purely classical. Alice eventually opens her ball and she finds it's white. That means she knows, or Bob's state has become black. And then you say, no, it was already that way around, right from the start. But you can't do that with the quantum picture because it's not like a classical situation where it's one way or the other. I mean, it's a whole sphere's worth of possible states. I mean, it looks superficially like that. And I think maybe that's the point you're making, that we do have, I say that the choice is made right at the beginning. Now, the EPR situation doesn't really work that way because you just have two states which are entangled. Alice's state and Bob's state, they're not one or the other. One isn't spinning this way and the other spinning the other way. That wouldn't give you the right answer. It's an entangled state.
Even in this case, you can arrange more complicated photon, which first disentangle them to put the dust in the superposition, and then make another kick to put it back. So you will supposed to see the interference. The dust, if the dust is small, you can split it and then put it back to interfere again. Will it interfere, or because you said that it's only going on one of them, and then interference will not happen? But if you'll consider a very complicated experiment, you'll split the dust, and then you put it and you put it back, make another interference, make Mach Zehnder with the dust. So
I'm not sure I understand your question, but what I'm saying is that this is a classical picture, and I'm going now on to the quantum picture. The quantum picture is more correct, if you like. It's more correct because, well, it's a different system. I haven't got spins in this one at all. The system is different. It's just a yes or no here. I mean, is it on the left side or is it on the right side? The other picture is genuinely quantum because you've got the spin state is entangled, and whichever one is, the other one is opposite to it. It's not one or the other. It's more subtle. It's not the same.
Okay, thanks. There are more people.
Yeah. Hi, Roger. I have two questions. Oh, is this on? Oh, hello. I was curious first. So this applies, e.g., applies to a spatial separation or superposition of two different locations and two different masses. I was curious if it also somehow applies to, say, superpositions and polarization of a photon that's in one place, a single photon with two polarizations, or something that's a superposition of spin states, for example.
I'm afraid I didn't follow most of what you said. You're talking about photons, are you now?
I'm curious if e.g., if this collapse, this time scale that is correlated with e.g., can also be applied to other superpositions that aren't dependent on a spatial superposition.
Sorry, what's the question?
So you'd only considered superpositions of a particle or something in different spatial locations, and you define the EG being the energy.
Well, EG does depend on.
But of course, you can have superpositions of things other than different spatial locations.
Yes. Yeah. You don't need. EG thing I was talking about depends on spatial displacement.
Right, exactly.
And that's what you're worrying about, is that it?
Yeah, so my question is, does this also claim to describe other sorts of superpositions that also collapse eventually?
You mean, do I get an EG if we're looking at other kinds of superpositions?
Right. Mm-hmm.
Yes, okay. No, that's a fair question. I don't think you need to, you see. I don't quite see why you have a paradox there. If you're looking at photons, I mean, I'm speaking off the top of my head a little bit because I should have worried about this problem, but you see, I'm arguing it is to do with spatial displacements. That is the reduction of a state. With the photons, you may not get a reduction of a state. So you're just doing quantum mechanics, ordinary quantum mechanics. Yeah, but if you see, the reduction of the state only comes about when you start moving big things around. That's what I'm saying. You can have photons behaving quantum mechanically, sure. Of course they will. And since there's no mass displacement in that situation, according to the scheme, sure, they just go according to quantum mechanics. There's nothing reducing the state in this, unless you come and look at it. Then if you come and look at it, then there's you looking at it, and you're a body, and there's all sorts of things can happen. Moving proteins around in your head, or goodness knows what. I mean, as long as it's an isolated system without any mass displacements, there will be no reduction of the state. That's what I'm saying in this model. But it could be wrong. I'm not saying it's not. I'm not saying it's necessarily correct. But I'm saying that this model says that the collapse of the wave function only comes about when you have mass displacement.
Okay, thanks so much. And my last question is, say you have something like a neutrino that's in a superposition of mass eigenstates as well as in spatial location that's moving super relativistically. Would the collapse happen in the frame of the neutrino or of the observer?
Well, you see, the criterion was stated in a way which referred to more or less in a Newtonian way. You're sort of looking at moving masses around. But if you're looking at a body which could be collapsed, more or less collapsed, I think you could say use the same criterion, because still a change in the mass distribution from one to the other. And the argument would be that the collapse takes place with a lifetime, so it's not it's like as I say, an unstable nucleus becomes one or the other. But if there is a distribution of mass which is different, if it's simply a question of something like photons, well, there is a bit of mass even there. The photon has a gravitational influence. So I'm saying it's a gravitational effect, if you like. Necessarily depends on gravity coming into the story. If gravity doesn't come into the story, there's no collapse. That would be the picture. Yes.
Okay, would you say then that the collapse would happen in the frame of the neutrino or the super relativistic particle?
It would happen. Well, you see, the neutrino has an energy even if it doesn't have a mass. I mean, you're talking about the one neutrino which we don't know has a mass.
Sterile neutrinos?
There is one left, isn't there? I'm told that one could be massless, which is rather a nice idea. I'd rather like it to be massless, but that's just a bias.
Okay, so we don't go on to. Do you have a question? So if you raise a hand, so that and then I think Jos at the front. No, you didn't. Okay.
So I think it's two short questions. I think one is I've got the same puzzlement as Liv. So clarifying. So here, when you're talking about the classical reality, is this in fact what you are proposing? That the collapse should act retroactively, or are you in fact proposing that also in this case the collapse should be along the past light cone, and this is just a sort of pedagogical exercise in between?
Well, I'm saying that anything retrocausal has to be in quantum reality. Classical reality doesn't have any retrocausal aspect. I mean, indirectly, as I say, like Bell's inequality, there are indirect effects which you could see at the classical level, which are not even relativistic. But that's sort of a second order effect. I mean, it's a subtle issue. The fact that you have these quantum level phenomena which behave in a seemingly, if you call it that, seemingly retrocausal way, it has to be the case for the picture to make sense. It doesn't enable you to send signals into the past. I'm not, perhaps I haven't quite got the gist of your question.
Well,
have I answered it or not? Perhaps not.
Perhaps not. Yeah, the question was, whether this is the slide where you've got, the mass that gets, displaced into a superposition, and then you've got it triggers the collapse, and you were saying, okay, in order to make this, in order not to get any problems with relativity here, the idea is that the whole, one component sort of never existed. The collapse, makes it the case that, it always was the case that the mass was displaced this way. And then, later on in your final slide, instead, when you're talking about the quantum reality, you've got the collapse along the backwards light cone. And I don't. What I'm not clear about is why you've got both. Are you proposing that there's a somehow double description in terms of classical reality and in terms of quantum reality, and this is what happens in the classical reality, and that's what happens in quantum reality? or yeah.
But the quantum
why did he show us both? I mean, couldn't you just have one of them? Either there's only one component that's always been there if the collapse happens, or the collapse happens along the past light cone. One of those two proposals would be sufficient.
My two pictures, I think, have probably confused people. Is that right?
Yes.
That's what you're saying. The one picture is really a classical picture. That was the one with the body put into a superposition of two locations.
I think the fact that you say you put the body into superposition suggests it's not entirely a classical picture.
That's true. Yes. But it's a quantum picture. Yeah. Okay. No, it's talking about classical things. The second one is more subtle in a way because you're talking about systems which are individually quantum, whereas in the other one you're thinking about systems which are individually classical, and you're looking at one superposition of the two classical systems. And perhaps it's confusing to show both. It evidently is confusing to show both those pictures, but I don't think they contradict each other. Is what I'm trying to say. The first one, the body itself is a big macroscopic thing. In the second example, we're talking about classical particles. So it's a little bit more along the line of thinking about what quantum mechanics looks like, if you like, than the first one was. I'm not sure if that answers your question. I'm not sure.
Okay, I think was there a hand up there? Well, whoever you're pointing at should raise their hand so I know who's. Up here, right. Thank you. Yes, sorry, you're right. They're obscured from my view.
Thank you. Yeah, so I'm still trying to press on this question of what happens in the picture of the mass superposition. Suppose it's just in a superposition that's only slightly separated and it's recombined very quickly.
Okay.
Is the thought that it still follows one path and not the other path, or does it have to be in a superposition for quite a while and quite far apart to do that? How do the physical scales get in there?
So you've got a classical body, a big body.
You've got a big body, but in a only just a little bit localized, and then is the thought that it still has a trajectory? Is the thought that every classical body has a classical trajectory?
Oh, I see. I don't know that I've been saying anything like that. Well, it's not a classical body if it can be put into a superposition of two states. So it's not quite a classical picture.
But if I understood right, in the picture you've drawn, it does. There is a fact of the matter that in fact, splitting it follows one path and not the other. I'm just wondering how it knows at the splitting point.
I saw the difference between the two examples is that this is one body, say one particle in a superposition. So each state is a definite thing. It's either here or there.
Yes.
In the second case, it's two particles, each in a superposition, entangled with each other.
That's
yeah. I think that's my understanding too. I'm just trying to press further on this first picture. How does your superposed classical object know that it's going to be superposed enough that it should have a definite path at this point? Is there something retrocausal going on there?
You're worrying about whether it has a definite path. I think my pictures are evidently confusing people. Confusing me now too.
We are running over time, but we did start late. I'm looking at your desperate faces. You're all heading for a drink, aren't you? But let's have two quick final questions. So, but both in the same row. So Tim first.
I want to offer my interpretation of these two diagrams in an attempt to answer Guido's question about why we're not using light cones in this one. And I think in the case of EPR, we are talking about two particles in space-time.
Yes.
So it's kind of legitimate to say, well, maybe there was quantum reality information going on past light cones. But I don't think you should think of this as two trajectories in space-time. These are two space-times in state space. And that is the picture that you very much, you focused on in your books, like Road to Reality. And there are no light cones in state space to communicate. So I think these are just two space times, and that's why there's no light cone to connect them.
The space times which are pretty close to each other. You see,
right? Yes, very close to each other.
They're wobbling it a little bit in the middle, but the light cones were pretty well defined.
Right, but the light cones are in the trajectory. They're not in the space trajectories. There are no light cones in that space of trajectories. That's my interpretation of trying to answer Guido's question.
Thank you. Would you pass the microphone? No, to your right, Tim.
You made me think I read too many books because one of the books may contradict the other one. So.
Okay, so we should make this probably the final question.
Okay. Yeah, I'm still wondering about this question that Lev started and Guido. And here's the way I would put it. So there's a precursor to the EPR argument that Einstein gave in, well, a version of this in Sole, but also but a nicer version in Letters, where he imagines you've got some system, you put in one of two boxes and you separate it, and one goes to Tokyo, one goes to London. You open up one, you see the particle there, it's not in London. And at first people didn't see that as obviously comparable to the EPR argument because it's only one system rather than two. Recent scholarship has emphasized no, it actually is analogous because the local observables are entangled in that case. That actually is an entangled state between local observable yes or no particle in this box and local observable particle. Now, is the difference between the two diagrams? You're imagining, something in here, something massive enough that it's never going to be in a superposition of different places. But if I had something small enough, I could actually have it being on a superposition of different trajectories.
I think that's what I'm saying.
Okay. Okay, good. That clarifies things.
We're talking about the first picture.
Yeah, the picture is on the screen now.
You've got a body in a superposition of two locations.
Right. But we know, we do think that some things can be in the superposition of two locations because we can get interference, right?
Oh, sure.
Yeah, but you're saying if it's massive enough, it can't be.
No, I'm not saying that at all.
Oh.
No, I'm just saying that the body and persistent being two places, but then you have to, when the collapse happens,
right,
then the reality becomes the whole trajectory of that body. That's the point. You have the body put into a superposition of two locations, and it can be a whacking great, but big body, such as a grain of sand, and that grain of sand would be in a superposition, but then it rapidly becomes one or the other, and then that means its whole history can become one or the other.
Okay, and I guess I don't understand why it's not analogous to the Bell thing. Why is it not analogous to the case of two systems and you collapse onto the past light cone?
Are you talking about the second picture then?
Well, to both Guido and I, there seems to be it seems to be one should say the same thing about both pictures.
The second system was considered, well, Alice and Bob are supposed to be classical bodies, and then they each have this spin-half particle. And it doesn't, you're worrying that I haven't drawn a trajectory for the spin or something. I'm not quite sure what. Because the spin is what you're looking at here. Of course, you could take the old EPR where actually Einstein was talking about an energy, what was it, momentum, and I use the spin version better, the Bohm version.
Okay. I guess the idea is both of these seem like similar situations. You've got in both cases entanglement of local observables separated.
No entanglement. This is just a single body in a superposition.
Right, but that's but that
Right?
is,
There's no
but
entanglement here.
There's no entanglement.
that's actually what I'm saying that there is. If you look at local observables here, you've got Hilbert space of local observables here, local observables here. There is entanglement because there's a superposition of one particle here and zero here, and one particle here and zero here. I'm saying that is actually an entangled state.
What? Entangled state would involve.
Show of hands, who agrees? Show of hands, who doesn't agree? Okay,
Well,
you're in the majority. Good. Wonderful. Okay, I think we should end it there. Thank you very much. Oh, did you want to make
a show of hands for anybody who didn't answer?
Who didn't? There were several who didn't raise their hands. We have to draw the session to a close. Several thank yous. First of all, thanks to all our speakers today. It's been a fascinating first day. Thank you for people who joined us online, live streaming. And on that note, thank you to the AV guys at the back. You've done a great job. These don't normally go smoothly, but today they really did. So thank you. And last but not least, let's thank Roger Penrose for a very stimulating lecture. And I believe drinks and nibbles outside.